Welcome everyone to the KDD Deep Learning Day for this year. I just want to point out that there's the website link on this webpage. It's also from the main virtual conference page. That's where all the program details are, all the speakers, their bios, their the topics of their talk, and somebody posted that in the chat as well. So yeah, thanks, Sean. And I encourage you to go there. I'll just give a quick overview of what the plan for the day is. So when we started thinking about this workshop, deep learning is already fairly famous. So what does a deep learning day even mean at this point? So we decided to focus on identifying what sort of the boundaries of deep learning are in terms of understanding where it fails, but also potential directions where it hasn't quite been pushed as much as we would like to be pushing it, or maybe it's been pushed, but not in the right way. So we identified 4 different themes around which to center to identify these boundaries. The first one, perhaps the one most relevant to KDD, is how do we scale up deep learning in real world applications? Second one was how do we actually evaluate and debug these systems that are essentially becoming part of software that we use every day? Third was trying to understand the fairness, transparency, and other ethical implications of using deep learning in sort of socio-technical systems. And finally, looking at the theoretical side of this also, understanding the limits and pushing the understanding of theoretical understanding of deep learning. And so our idea was to focus on these 4 different themes, but for each of these themes, try and identify methods, not just that are just new papers in these areas, but more specifically, ask the people to focus on, what are the flawed research processes or practices that we should be thinking about revisiting? What are some unjustified intuitions or assumptions we have about systems when we use them? What are some of the negative results that are actually informative about deep learning not working? And what are some of the open problems, right? So the talks you will hear today will not necessarily be focusing on only one of these. There'll probably be some combination of some of these, but that's kind of the theme of what we wanted to do today. Not just hear about the latest research, but or the latest results, but more focused on these kind of things. Okay. For a quick overview of the day, this is what it's going to look like. All the times here are in Pacific time. For the first section, we're going to have a bunch of talks on scaling up deep learning, followed by evaluation and debugging, followed by a panel for both of those first 2 themes. The panel will have sort of general questions that are cross-cutting, but also if there are questions that were not covered for any of the talks during their session, you could probably ask them during the panel as well. Most of the panel, the invited and contributed speakers will be on the panel. In the afternoon, after a break, we are going to have a session on fairness and transparency, followed by theoretical understanding, and finally in Q&A. So that's kind of the rough structure of the day. I'm going to quickly go through each of these sessions just to highlight the talks that we're going to have there. The first talk, right in a few minutes, is going to be with Eric Xing, Arun Kumar, Don Song, and Deepak Agarwal. We're going to be talking about different aspects of what happens when you scale up deep learning, or how to scale up deep learning, and things along those lines. We're going to have a short break after this session, followed by the next session, which is going to be on evaluating and debugging. How should we be testing these systems? What are some of the flaws in our current evaluation benchmarks and things along that side? We're going to have Besmira Nushi from Microsoft Research, Daniel Kang from Stanford, Saket Gurukar from Ohio State, and Aleksander Madry from MIT, talking about these issues. Then following this session, we're going to have the panel for both of the invited speakers, followed by what will be the lunch break in Pacific time, but for every other time zone, it'll probably be time you go and see your family or have fun or something. In the afternoon, Pacific time, we're going to have the session on fairness and transparency, where we have James Zhu, Harmanpreet Kaur, David Madras, and Martin Wattenberg giving talks on different ethical implications and interpretability and things of that nature, followed by a short break. And finally, we're going to have a session on theoretical understanding late afternoon with Jason Lee, Andrew Stolman, Tianlong Chen, and Yasaman Bahri. This will be followed by the second and the final panel of the day, which will include speakers from transparency and the theoretical understanding, followed by some short closing remarks. So that's kind of the sort of plan for the day, and we're pretty excited about it, and I hope you are as well. Finally, I want to thank all of the other organizers who've been working on this for the past couple of months. Hima, Xiang, and Baharan are the main organizers, and then especially want to thank all the student co-organizers. Like, the program that we've put together wouldn't have been at all possible without Sushin, Harvanit, and Dylan. So you'll see most of us today during the day, so I just want to introduce us up front, and you'll probably see us all in the chat. With that, I will let Sean take it away and introduce the first session, which is going to be on scaling up deep learning.
Great. Yeah, thanks, Mir. Hi, this is Xiang Ren. I'm a faculty at University of Southern California. It's my honor to be hosting the first section of the day, which is covering the scaling deep learning topic. So, one thing I want to just have a quick note before we start is, like, for the audience, feel free to leave your questions to the speakers on the chat box, and then I will keep track of them, and I will make sure that if we have time, we will go through these questions at the end of the talk. And our tech person will also make each of the speakers the co-host, so that you can share the screen. So I think we're working on that now, Eric, so you can share screen in a minute. So I think Samir is helping with that. With that, I will get started with our very first talk of the day. So it's my great honor to welcome Eric Xing for giving us a talk on the topic of scaling deep learning. So Eric Xing is currently the president of the Zayat University of Artificial Intelligence. He's also the CEO and chief scientist at the Pattern company, and also he's keeping his position at CMU. So Eric got his PhD from UC Berkeley, and his main research interests are the development of machine learning and statistical methodology and large-scale computational system and architectures for solving problems involving automatic learning, reasoning, and decision-making in high-dimensional, multimodal, and dynamic possible worlds in artificial, biological, and social systems. So Eric is a board member of the International Machine Learning Society, and in 2014, he served as the program chair of the ICML, and in 2019, he served as the general chair of ICML. He's also the associate department head of the machine learning department at CMU, and a fellow of the AAAI. So welcome, Eric. Are you able to share your screen now? I think you are the co-host now. And you are muted, though.
Can you see my screen now?
Yes, I can see your screen and I can hear you. Perfect.
Great. All right, let me get started. First, I want to begin by thanking the organizers for inviting me to talk about scalability issues in deep learning. I will quickly jump into the topic. Today, I'm going to talk about the utility bills of deep learning and how to mitigate that. So let me get started. So as we can see, deep learning nowadays is a dominant approach, in many applications. Here, I just gave you a few examples, ranging from computer vision, natural language processing problems, all the way to, drug design and the game playing and so forth. And we recently see some very significant trends, in deep learning research. One is the emergence of these so-called all-purpose monster models, which is growing in size, very dramatically and in a very fast pace. In the past 3 years, we saw almost 10,000 times increase in the model size in the number of parameters. Right. Another trend often seen in industrial companies which builds deep learning systems is that they stitch together multiple units and components into a big system to do multimodal data processing and many advanced applications. So with these trends emerging, obviously, we are facing growing model complexity, pipeline complexity, data sizes, and modality, and so forth. And they raise a number of challenges in computing and in implementation, which I listed here. Right? We can see that all these applications and the developments requires a lot of computing, a lot of memory and the hardware network bandwidth. It also requires a lot of engineering hours, to develop and debug the system. And also it requires a high skill set from the developers. Just to give you one example, I believe there is now already an arm race between companies to really, obtain or develop, hardwares that is capable to undertake, the very specific and high demanding computing task. Even a modest-sized deep learning model nowadays could use hundreds of hours, using the latest, NVIDIA GPUs. And in fact, the NVIDIA GPUs are also growing, its generations very fast. We are already moving away from A100 to V100, and there are other several, startups developing, a mega scale chips such as the wafer chip from Cerebras, which has, nearly 1 million cores on the chip to allow you computing large models, maybe without using distributed technology, right? So all these actually, require significant investment from organizations and companies. And also there is a challenge in managing these resources, economically and wisely. So you can see that there is a big utility bill, even going beyond the hardware, right? You need to pay for engineering hours. You need to also pay for electricity, for running the hardware and cooling the hardware. There is also software lifecycle, maintenance. There are also issues on environmental, footprints such as carbohydrate emissions, and carbon dioxide emissions, greenhouse emissions, and other things. I guess most of the community in deep learning are not paying too much attention on this utility bill because it is the company or the big players who carry the bill. Researchers usually are not too worried about it, or they choose not to do it if they don't have the resource. And this is not a sustainable way to grow both machine learning and deep learning. So my question is how we can predict and mitigate the cost of deep learning as we see just now. For example, how to effectively train the model, what's the best training strategy, right? How to pick and deploy hardwares to allow training happening efficiently, and how many lines of code, in addition to the model itself, we need to develop, to distribute or deploy the system, right? How to tune the model, and also maybe how to automate composition, parallelization, tuning, and all that, given that we have so many projects and so little time and resource. So toward this cost-conscious deep learning, I'm going to talk a few ideas, that could lead us to think about plausible solutions. So these ideas include how to automatically parallelize machine learning training and inference, how to automatically schedule in training tasks, how to tune big or small models, and also what's the mathematical foundations behind all this. So let me begin by auto-parallelization. As we all know, machine learning and deep learning are largely relying on a type of iterative convergence algorithm, which asks you to update the model parameters iteratively like this until they converge. And the computation of that delta is actually the main task, for every infrastructure and hardware. When the data become big, you need to sometimes use a technique known as a data parallelism to split the data onto different nodes. Therefore, they can get computed in parallel and then aggregated. If the model becomes too big, you may need to also split the model parameters so that it needs to use a model parallelism technique to distribute the workload. And there has been a number of system artifacts developed for these kind of applications, such as the parameter server, and also recently more popular, the all-reduce architecture. But on the other hand, behind these two main architectures, there are also a large number of problem-specific artifacts and specific issues that needs to be addressed underlying the problem of computing, memory management, and communications. Then there is a big space of solutions that needs to be implemented depending on what problem you are solving. Therefore, the existing universe of system artifacts is really bewildering, and it's hard to use and generalize. And that actually is one of the major problem or issue causing deep learning to be difficult, at least at the system and implementation level when they become very big. It is very diverse in terms of the model. Therefore, you cannot oftentimes find a system that can carry different types of a big workload, depending on the model architectures and depending on the models. And here I have a little graph showing you the type of design space people are facing. And secondly, even if you know how to choose, then there are separate code bases and APIs for all these different solutions. Therefore, you need to put a lot of effort in learning them and also using them. It is not very interoperable between all these different systems. If you want to do an optimal partition, you need to use a technique known as a mesh TensorFlow. But if you want to probably use a all-reduce technique, then Horvath provides the best system. So how can you combine all these different technologies in a single solution? Right? And last but not least, even the existing solutions sometimes have deficiencies. For example, you may run into heterogeneous models where some techniques are only working well for a part of the model, but not for the entirety of the model. And also sometimes there are specific characteristics inside the model, such as sparsity, which can be hard to deal with by a general purpose system. So in order to bring a universal and more convenient and generalizable solutions into distributed machine learning, I guess one need is to start developing a universal representation of the distributed machine learning strategy. And here I make a proposal. Here is an example of a strategy which consists of a collection of tuples. They could be specifying how to make partition, how to choose the system architectural topology, how to develop a bridging model between different nodes, how to compute and pass the messages, and also how to aggregate the messages. Just to give you a more concrete example, a parameter server can be realized by making instantiations of all these different aspects in the strategy to have a rigorous definition. And this is a graphical example of how a parameter server look like under such a uniform definition of the parallelization strategy. And here is a different architecture called all-reduce. You can see the differences between this one and that one could be just within a subset of the aspects. In here, the topology chose a ring structure, and previously it is a star structure. But you can use the same bridging model, and you may be able to also use the same partition of the model or the data and so forth. Right? So that suggests that the different strategies are not entirely different. Some parts may be reusable. If you nuclear it and make them a standardized building block, then there is a possibility of assembling a strategy just from those standardized spec instances like this. You begin with a computing infrastructure and a model design, and then you just navigate through this matrix of aspect instance choices, and then you stitch together a collection of tuples, and then you come up with a strategy. So this is the idea behind a standardization of model parallelization and data parallelization and other type of parallelizations. When you are having various different type of models, or maybe even a model with a very heterogeneous data structure, then what you can do is to hopefully have a system automatically picking all these different components and come up with a strategy composition. So this is the idea behind what we would like to call a compiler, for machine learning distributed strategies. And in our recent work, we implemented such an idea called a strategy builder, which basically take the input as a model representation and the resource representation, and go through this building process and come up with a very optimized code to realize a distributed machine learning strategy. These components can be pre-made, or if you don't find what you need, you can customize it using the standard wrapper to deposit it into the library. And at the end of the day, you can start composition. So how to automate composition is also a very interesting strategy, because some advanced models like a big transformer may require different sub-strategies for different parts of the model. So therefore, one can benefit from a definition of a cost model in terms of the performance of the strategy. And therefore, you can build a model-based optimization procedure or use a strategy simulator to pick the best strategy automatically if you're rather not doing it manually. So that's how, at the end of the day, the system look like. It will take model representation and the computing resource representation, go through different types of strategy builders, and then provide an intermediate representation of the strategy specification. And then the system representation can accommodate not necessarily homogeneous, but also heterogeneous structures. For example, you can use a parameter server to handle the bottom layer of the neural network where parameters are very dense. And you can use a OREDUCE to handle the top part of the neural network where the parameters are very sparse and so forth. So this is to contrast a traditional approach that we are doing now, where your system configuration and your model enters a black box and then come out with a homogeneous design of the distributed strategy, which has to be used all over a big model, which is obviously suboptimal. So here is a comparison of the AutoDisk technology that I described versus the Bespoke distributed machine learning based on either specialized system artifacts or hand-tuned strategies. And you can see that in different types of deep learning models, the AutoDisk technology does have an advantage in all these cases by saving time, sometimes up to 60% better in terms of goodness. Then, let me jump into the next aspect of cost saving issue, which is how to schedule multiple tasks or even within a single task of computing. Again, back to our distributed learning algorithm. We started off by looking into the data. And then one thing we often do is to start partition the data into mini batches, and they got deposited into different computing nodes, right? And then a gradient or some type of update will be computed. They get averaged or aggregated, and then they get sent back to every node to have an update. Then this whole thing repeat. Therefore, two critical tuning knob or maybe design space that people could leverage to either improve in the performance or do a bad job is to choose the ideal batch size and also the optimum learning rates. It turns out that this is not very easy because empirically people observe that deep learning training scale not so nicely, in fact sublinearly to the performance. When you increase the number of GPUs into your system, you don't get that kind of a good throughput or results you expected in terms of a linear return, right? And therefore, what people do is maybe they suspect, maybe my batch size is too small so that I didn't make optimal use of every node. Why don't I just increase the batch size? it turns out that even if you increase the batch size, you still don't get perfect linearity. In fact, sometimes when the batch size become too big, you get adversarial results where the results are worse than the smaller size. So here I want to say a few more words about the statistical efficiency, and the impacts of the batch size beyond the throughput. It is known that the statistical efficiency does not go with the batch size very linearly, because your learning rate and also the quality of the gradient really resulting from the batch could directly impact the statistical efficiency. And this is basically the gap that people empirically observed between a perfect statistical efficiency as a function of the batch size versus what you actually get in practice. And the gap is the actual computing you have to pay to train without a good return. Right? So just to sum up, when you change the batch size, you could increase the system throughput sometimes, but at the cost of dropping statistical efficiency in most cases. Therefore, there is an optimal sweet spot where you want to find to make the training performance ideal. But unfortunately, as you are moving along the training, even the size or even the position of this optimal spot itself is also changing. Therefore, at different stage of the training, your ideal batch size is also different. So all this actually points to a fluid resource requirement, which could compromise your system's utility. You have to basically prepare for the worst case scenario in your system resource allocation to adapt the peak need. And then when the peak is gone, your system will be underused. So we looked into this problem from a more theoretical perspective, and we found that it may be beneficial to go beyond just optimize throughput in our machine learning distributed computing as we do oftentimes, but to look at a new metric which we call goodput. The goodput is a new definition of the system performance that combines the system throughput with the statistical efficiency. And each of them could be parameterized with system-free parameters so that you can start to model the throughput and the efficiency. So I want to say a few words here. For example, here is a particular formula you can use to model the system throughput. And here, the gamma is a learnable parameter that you can train on the observations you had of the existing throughput as a function of your system resource. And as the graph on the left show, this model is fitting the system throughput quite nicely, which means that you can actually predict the throughput ahead of time when you want to deploy or withdraw resource. Likewise, you can also model the statistical efficiency, using a parametric approach. This particular parameter here is reflecting the magnitude of the preconditioned gradient noise scale, which is often reflecting, the amount of statistical efficiency you are going to get. And once again, we see that with a bigger, batch size, sometimes we have a drop in the statistical efficiency, which validates our empirical observation. And also the model can fit the real actual statistical efficiency quite nicely, which make it useful for making predictions. Now, knowing the being able to predict both throughput and the statistical efficiency really helps a lot when you want to come up with the ideal allocation scheme for resources. We begin with the given amount of hardware and also the computing task, which can be in the multi-tenant setting, meaning that multiple users are training multiple models. And then what you do is to use the model I just described to make a prediction of the job scalability, given different resources and different batch sizes. And then you aggregate all these predictions from different users and different training tasks to have a global optimal resource allocation scheme, okay, based on all these predictions and based on the good metric. And then you go back and reallocate resource. Therefore, you can see that this scheme is not just elastic or adaptive. We call them co-adaptive because you are simultaneously adjusting the resource and also adjusting the training procedures so that they can lock hands in hands to achieve optimal performance. So this system is called AdaptDL, which was recently published at OSDI. And here again is a comparison. You can see that the AdaptDL is achieving 2 or 3 times faster training time than existing systems or hand-tuned systems, where the hand tuning is really taking advantage of being a single job and also having a lot of special knowledges about the work. One more thing that I want to mention before I wrap up is the task of tuning, which also plays a big role in making the machine learning costly. There are a lot of things in deep learning that we need to tune, as we all know. Right? For example, the hyperparameters in those models, the neural architectures in the deep learning models, and also the system resources I just mentioned. Right? So all these can be subject to change when you change certain type of parameters. And typically what people do is to hand tune it, based on a lot of experiences, or maybe just based on an ad hoc technique. So our goal is to ask, is there a way to more principally and also automatically improve both intrinsic and extrinsic metrics? And maybe you also want to do it automatically because these tasks are highly demanding and also time consuming, right? So one approach I want to introduce here is called black box optimization. So black box optimization is a technique where you don't actually know the function you want to optimize, but you can query it. And then you can learn a model for the return and also for the uncertainty, and then accordingly query next time or choose the best strategy. So this scenario is a perfect fit for the type of tuning that I mentioned in our deep learning training tasks. And here are some examples of this technique being used. So let me say a few words about how this black box optimization can be realized and designed. First of all, we need to begin with a search space, for those parameters. It could be a continuous space of the hyperparameters. It could be a discrete space of the model architectures. And then you need to also define clearly what the query means, which in our case is the task of training a model. Then our objective, of course, is to achieve a maximum, say, performance, or lowers the cost in the training, right? And typically how people do those search, well, what we often see are either a grid search in one dimension or high dimension, or maybe random search. And sometimes a genetic algorithm could be used. What I'm going to talk about is an approach called probabilistic Bayesian optimization, which is an instance of the model-based approach because it gives you a lot of appealing features in terms of cost saving and in terms of predictability. Here is a high-level picture about model-based optimization using the HPO as an example. We begin with defining, our goal is to use a probabilistic acquisition model to intelligently plan queries and then perform efficient optimization, right? So this probabilistic acquisition model is essentially, a distribution of different scenarios of query and rewards. Okay, you can see all these curves. So it is a Bayesian prior, for the model. And then there is also an acquisition function, which is taking advantage, of the uncertainty modeling resultant from the acquisition model, and then calculate a utility of each query, taking into account both the return of the intrinsic value, of the training, and also the amount of uncertainty you have to experience in using this query. Just a few more words about this acquisition function. Oh, by the way, both the acquisition function and also the acquisition model can be simultaneously learned using a nested, iteration loop, right? You put the acquisition function, inside, the learning procedure of a probabilistic acquisition model, and then you are going to use a type of a reinforcement learning type of dynamic, to query and creating the Y return, and then you add this one more data point to improve your estimation of the probabilistic acquisition model, and so on. The acquisition function is the key of informative and accurate prediction of the utility of the query. So here is an idea. in defining the acquisition function. As I said, the probabilistic acquisition model is modeling the uncertainty of the query and the return match, right? And there are many of these possibilities. And therefore, this defines a posterior distribution, of the function of query and return. And you can basically optimize, a collection of samples from each of these from this posterior, so that you can get an optimum query point, for each of the instance of the posterior of the probabilistic acquisition model. And so the optimum query points itself becomes a set reflecting uncertainty. And then you can now define which one is best by doing the following thought experiment. So in your current estimation of the acquisition model, you get this collection of optimum query points, which has a disperse. You can calculate the entropy over that. And then if you choose one of the points or choose an interpolation of the points and generate one more data into training the acquisition model, you will have a new posterior for the acquisition, which actually has a different level of entropy. So the difference of the entropy, which models the kind of captures the information gain you have as a resultant of the query, could be used as a definition of the acquisition function. Right? So use that, we can now implement an automatic program to do HPO. And here is a panel of the comparison of the results. You can see that across different choices of the models, our approach based on model-based optimization, it's not always the best, but it's consistently among the one or two bests, in different HPO strategies. And the same technique, MBO, can be used not just for NAS, for HPO, but also for NAS. All you need to do is to now define some kind of a distance functions between different model architectures, such as using a optimal transport function. And then your model can be now projected into a points of the search space. You can also define another neural network model, a Bayesian neural network model, to model the probabilistic acquisition model itself, so that you can define multiple objectives, not just a single one, such as computational cost plus performance of the model and so forth. And obviously, this technique can be also used for resource scheduling optimization. So now, before I wrap up, I want to maybe make a quick observation. So we've already seen that all this parallelization, scheduling, and tuning technique I just talked about could be realized through a pretty sophisticated and automatic system. One commonality they all have is that each of them is based on a model-based approach. Either model the utility of a distribution, the utility in terms of a good put, of job scheduling, or utility in terms of the uncertainty and the rewards, over a acquisition model. So that highlights the need of having, a mathematical understanding of what we are doing in deep learning, so that we can predict, the cost and also the rewards. Right. So that leads to me to conclude this talk by introducing, a latest result we had toward this direction: how to understand, deep learning or machine learning training and design in the principled and a unified way. So cost-conscious they are really were asking for more principled and predicted deep learning. Making the task predictable really, can not only, save your cost, but also can improve, the result to value or the time to value kind of iteration. Without that, you are really looking like doing the alchemist experiments. You mix everything together. You put, I don't know how many transformers together into, or attention has together into a big transformers. And then you actually have a little idea about the cost of training. But having the principles behind it is like you are now doing chemistry using a periodic table. You can kind of have a sense, about what, utility and cost, entails. Right? We're not there yet, but hopefully there will be more attention into this direction so that we can build on this knowledge to productionize, chemistry, or in this case, deep learning in a more systematic way. So back to our machine learning and the deep learning world. we are now still in a universe of many different artifacts of algorithms and heuristics. And that directly already point to one difficulty we already see, which is that to compute, for example, this update is going to be very difficult, and thereby, optimizing batch sizes, learning rate is almost impossible, right? Therefore, you can only do the kind of optimization I just mentioned for a few well-known models, but not too many. So there may be a need to develop a standard model that could cover as many as possible our current instances, or maybe even future instances of machine learning and deep learning models. And here is a proposal of such a model, which we call the standard equation. So it contains 3 parts. The first part is an expectation of what we call the feature or experience function over the distributions to be learned for the data. And this experience could include not just the data examples, but also many other complex experiences, such as logical rules, such as rewards, such as adversarial experiences. And in our paper recently published, we have specific mathematical formulas to show how to encode these different type of experiences. The second term is called divergence term. It is kind of like the likelihood of target objective that we use in machine learning, which defines a mechanism between the teacher model and the student model so that they can get close to each other. So this is the driver of the iterative program, which tells you the fitness of the model being trained. It could be a cross entropy, Jensen-Shannon divergence, or other type of divergence measure. And the last term is called uncertainty term, which governs, which is a self-regulation term to govern the amount of uncertainty, resultant inside your model. Right? It turns out that by plugging in different instantiations of these 3 terms, you can recover most of the well-known algorithms nowadays. Just like this tree is showing, it is using the standard equation to unify many existing learning algorithms and paradigms. And here is just a table showing you how these equation instantiations look like, and how this small number of hyperparameter should be instantiated. So what's the utility of that? Obviously, the standard equation, in my opinion, provides a very straightforward blueprint to do more complex multimodal machine learning, say from all experiences. For example, what if you are running into experiences of all this kind? You have not only data, but also you are interacting with the environment, and you are getting rewards by interacting, and you also have a knowledge graph setting up constraints. So in the case of having a standard equation, what you do is to now develop a linear combination, or maybe using a kernel trick to have a nonlinear combination of all these experiences together, so that using the same standard formula, you can seamlessly learn with multiple experiences jointly. So the standard model also provides you maybe a potential to develop a master algorithm, regardless of what learning paradigm you are actually instantiating, because in the root, their appearances and mathematical form are symbolically identical to each other. So here is an example of how this master's algorithm look like, right? It is look like a EM algorithm or a teacher-student algorithm, where in the E step or in the teacher step, what you do is to combine knowledge from the experiences with the current version of the teacher model. And then in the M step or the student step, you try to draw the student closer to the teacher so that you update your current model to be learned, and then you iterate. There could be many ways of making this approach more expressive and more powerful by introducing advanced techniques such as kernel tricks, such as proximal gradings and so forth, which I'm not going to have time to cover. And also having this standard equation is providing a very clear roadmap to design data-centric principles for compositionality inside the machine learning model. For example, you can come up with Legos, which are designed around different building blocks in the standard equation, such as the different instantiations of the experiences and the losses and algorithms. You can use a data pack that is a data frame universal across all these different Legos, so that you can avoid the complexity or the tediousness of doing data cleaning or data reformatting across different parts of the model. And then this assembly line enabled by our recent software package Forte is allowing you to wrap, either homemade or standard library functions and APIs, into a universal interface so that they can be combined like this to come up with a complex design. And that combination in a systematic way also make it easier for, say, tuning algorithms, for resource schedulers, and also for automatic distributing algorithms to start understanding the work better and then do the optimization of the resource and the work. So to wrap up, I talked about a number of directions into understanding, predicting, and mitigating the cost of deep learning. And along with that, we developed some mathematical formula for each of these subtasks, and also a standard model that provides a blueprint for designing complex machine learning models, for real-world applications. The softwares I just talked about are all deposited, published in this open source consortium called Castle, which has a number of existing implementations already, alongside with the paper that is published or in the preparation to describe their mechanism, principle, and also usage. Some of the papers were already receiving some good recognition, such as a best paper at the OSDI and a best paper in ACL, but I hope more results are to come. So I'm going to wrap up here. Thank you very much for your attention.
Thank you, Eric. Thanks for the great talk. So for the interest of time, we can take one question here. I see, Aaron, you post some questions on the chat. Why don't you unmute and go ahead?
Okay, I can do that. Thank you. Thank you, Eric. This was a fantastic talk. I'm familiar with some of your latter work from Jiting's talk here. So he's one of my colleagues now here at UC San Diego. So the main question I have for you is, where do you see the industrial landscape evolving? The Google and Facebook folks tell me they're working on new tools that supersede Facebook and TensorFlow soon. JAX is almost halfway there. Do you see them open sourcing some of their scalability and parallelism techniques that they use internally that they're not open sourcing? And secondly, I see the homogenization claim that the Stanford faculty are making. I'm a little suspicious of that. Do you see that happening?
Well, you probably, the Google folks are in a better position to ask whether they open source or not. I wish they could. I think, the trend is that we want to, open source all this technique for a better exchange. But on the other hand, the position taken by Google and Facebook versus the position taken by, researchers like us can be different, because in their hand, they have resource and data, and they may be less sensitive to the cost issue. And but for the researchers, we are really limited by the cost bottlenecks. So I hope that on the research side, we should develop some kind of autonomy and less dependency, on those big companies' resource in terms of defining the agenda and also the style of the work, so that we can have more space to innovate. Because if everybody is go toward the path of gigantic big models, in a sense, there is a bottleneck due to policy or other type of business operation or company strategy, which could create kind of challenges, additional challenges, and maybe limitations of academic research.
Got it. Thank you. Totally agree with that.
Thank you. Well, thanks again for Eric. I think if we have more questions, we have a panel at around 11, which will Eric will be also there, and then we can have more question answers. So thanks. And let's move on to the second talk. So I think since Arun is here, that's great that I can just introduce. So the next talk will be a contributing talk for Arun Kumar. So Arun is an assistant professor in the Department of Computer Science and Engineering, and also Data Science Institute at University of California, San Diego. He is a member of the Database Lab and Center for Network Systems and athlete member of the AI group. So his primary research interests are in data management and systems for machine learning and artificial intelligence-based data analytics. Systems and idea based on his research has been released as part of the Arpage MADIB open source library, shipped as part of the products for Cloudflare, IBM, Oracle, and Pivotal, and used internally by Facebook, Google, Logic, Blocks, Microsoft, and other companies. So he is a recipient of 2 SIGMO Research Paper Award, a SIGMO Research Highlight Award, and the Distinguished Reviewer Award from SIGMO and VLDB, and the PhD Dissertation Award from UW Madison CS. So let's welcome Arun. Feel free to get started.
Thank you, Xiang. Do any of you want to play the video that I sent, or shall I play the video? I have a recorded video because my Wi-Fi can get unreliable. So, Xiang, you're muted.
I mean, feel free to play it on your side if it's ready.
Okay, let me see. Just let me know if the resolution gets choppy.
Mm-hmm.
I'm going to start playing this. Thank you for having me. Can you see the screen?
Yes.
Okay. Hello, everyone, and welcome to my talk. My name is Arun Kumar. I'm a faculty member at the University of California, San Diego, in both computer science and data science. Thank you for having me at the KDD Deep Learning Day. It's great to be here. I'd like to share with you some thoughts on what I see as some damaging delusions in deep learning practice and deep learning systems and how to avoid them. A little bit about my research. I'm not in the deep learning or machine learning world. I've never published at any of the ML venues. I publish primarily in the data systems world. I work on new abstractions, algorithms, and software systems to help democratize ML and AI data analytics from a data management and systems standpoint. By democratization, I mean improving the efficiency of the systems and the tools and the algorithms, reduce their resource costs, and also improve the productivity of the practitioners involved, the data scientists, ML engineers, and others. I really bring together these worlds of data management and databases and principles from those worlds and straddle the whole system stack. Okay, it seems like the video is chopping up for...
Yeah, so I can ask Dylan, which is our student coordinator, to try playing that. Let's see if that works better. So Dylan, do you want to start from?
They say you can share the screen instead of sharing the window. Let's restart.
Yeah, the black boxes are due to pop-ups over the window.
Oh no.
Mm-hmm.
So
I think we have a new version.
Okay, so Dylan, can you restart? From those worlds and straddle the whole system. I'd like to share with you some thoughts on what I see as some damaging delusions in deep learning practice and deep learning systems and how to avoid them. A little bit about my research. I'm not in the deep learning or machine learning world. I've never published at any of the ML venues. I publish primarily in the data systems world. I work on new abstractions, algorithms, and software systems to help democratize ML and AI data analytics from a data management and systems standpoint. By democratization, I mean improving the efficiency of the systems and the tools and the algorithms, reduce their resource costs, and also improve the productivity of the practitioners involved, the data scientists, ML engineers, and others. I really bring together these worlds of data management and databases and principles from those worlds and straddle the whole system stack to help democratize ML and AI. More precisely, I build practical and scalable data systems for ML analytics that are inspired by the principles of relational database systems that we've been studying for almost half a century now. But I exploit insights from learning theory and optimization theory also, which are at the root of what ML computations are about. So why am I here to speak at the KDD Deep Learning Day? I want to share a little bit about 2 kinds of delusions that I'm seeing, modeling related and systems related. But first, some background on what we've been up to in the large scale DL space. We've been collaborating with public health scientists here at UC San Diego for almost 3 years now in building deep learning models to predict activities from time series data, from accelerometer data that are almost terabyte large, labeled data that they have had, that they have collected. They had prior hand-tuned physics-based features and random forest models that gave some 76% balanced accuracy for a binarized version of this prediction classification task. We built deep learning models using state-of-the-art CNN and LSTM hybrids that gave almost 92% accuracy. This is now the state of the art in their field. We published about this in public health journals. How did we achieve this lift? Our secret sauce was not fancy ML algorithmics, new model architectures or whatever. We just did model selection with deep learning tools that was done with a high throughput manner so that we could explore different configurations and achieve this sort of lift. We found that the parallelism of our existing systems was a poor fit, and so we set about on this journey to understand DL system scalability. My friends, the reason I'm here today is to bust many DL delusions and to slay DL practices so abysmal, DL systems so dismal, they even turned my hair gray. Let's start with some modeling delusions. Now, all of you are applied ML experts here at KDD. You know that the test error can be decomposed into bias variance and base noise, where the bias variance trade-off is determined by the complexity of the model's hypothesis space and the feature space as well, between underfitting and overfitting. Test error varies non-monotonically. But more recently, we saw in the interpolation regime where the model complexity grows even higher, especially in deep learning, test error can actually go down even more if you're able to afford a lot more complexity. Of course, the base noise is something that no model can mitigate because of discriminability of examples. Model selection to tune these bias variance noise trade-offs is inevitable in any applied ML task. You need to configure data representation, neural architectures, and hyperparameters. That is how you navigate this trade-off space. We saw the same thing in our public health use case. So we had trained different kinds of models, almost 100 plus models, varying all these sorts of hyperparameters. Here's the simple snapshot that I'm showing here that shows two different clusters of configurations leading to different accuracies. And the ones at the bottom are the ones we ended up picking. Later, we got more label data from a different cohort. So we are working with different cohorts of people who are breast cancer survivors, people with obesity, people from assisted living facilities, and so on. And so in this second cohort, we thought we could amplify the capacity even more to maybe hit the interpolation regime. Turns out it was much harder than we thought. Even after amplifying the network many times, it didn't actually go into the interpolation regime, and it was just so much slower to train, much more painful for them to deploy on new cohorts. So it's not easy to achieve this. Now, in the model selection practice in real world, we have these surveys of people at New York Sniper. They say some of them do optimization, some of them don't. But this what really caught my eye. I mean, like many of them do manual tuning. Oh my God, people, is ML even a science anymore? If you're just hand picking some random hyperparameters, just taking numbers out of a hat, that is not how it's supposed to work. You need to do rigorous model selection with proper hyperparameters. Thankfully, I think AI conferences, ML conferences are now starting to realize this and demanding this from authors. But it does make for a lot of trolling. If I had a dime for every time this happened to me, I would be a rich man by now. Anyway, another propaganda I see is like, now, label data is all you need. Just keep accumulating these vast barrels of oil. You know, label data is new oil. But all this oil is of no use if your cart doesn't work properly and if it's really sucky. You might as well just move your oil around in donkey carts. Rigorous model selection is how you ensure you do not squander the label data that you've invested so much time and effort in for your application. To summarize, model selection is often ignored by DL types. In the worlds of ML systems, databases, all stripes, are they deluded or just lazy? Or just marketing like crazy? Boy, for sure they are living stereotypes. So to avoid this delusion, perform rigorous and repeatable model selection to optimize task-specific bias variance noise trade-offs. Moving on, there's this new propaganda that AutoML is a savior. Everything will be fixed with AutoML. Actually, the AutoML heuristics are indeed useful in many cases, but they're often very easy to abuse. I've seen so many cases where they said, oh, we use AutoML to tune everything, but then ended up burning through $1 million just to build one model. Now imagine everybody doing all of this, it's not going to be economical. You need the prudence of human intuition to prune the search space and specify what to search and what to use for AutoML. And that is how you avoid this delusion. Hybrid human in the loop plus AutoML specification to rein in this bloated use of resources that takes place often with AutoML. Moving on, transfer learning is another new propaganda where they say it's the new savior. Entire deep learning has been solved with transfer learning. Actually, if you look closer, task-specific bias variance noise trade-offs do not disappear. You still need to do it. Model hubs, Hugging Face, and all these sorts of libraries are indeed helping democratize state-of-the-art deep learning models like transformers and others in many fields. But the world is far, far bigger than just a few natural language processing or image processing tasks. Now you might wonder, what does transfer learning have to do with model selection? Literally everything. Pre-trained models are just seeds for the featurization, for data representation, for fine-tuning of parameters and so on, and architectures. They help raise the bias, but reduce the variance in the overall mix to reduce the test error. So you have to do these sorts of model selection here. Now, in many cases, you have multiple modalities of data that need to stitch together. That leads to bespoke bias variance noise trade-offs that are task specific. So transfer learning is rigorous. It must be rigorously treated as another part of model selection. That's how you avoid this solution. Now, all of this model selection talk must kind of make you think, oh my God, I have to train so many models. It's so painful. And I've seen many deep learning users complain about how their deep learning system fails to scale and how it's really miserable to use at scale. That's where I'm going to talk about some systems related delusions. So many DL systems are so poor at scaling. one wonders why there is so much failing. Boring, wasteful execution is not really a scaling solution. Against DL systems, I will now start training. Now, what do I mean by boring, wasteful execution? We saw that most of these DL systems today use one of two paradigms. First is task parallelism, that's used by things like Array, Google Vizier, DAS, Celery, Asha, Determine, and so on. They place different model configurations on different workers, and they copy the entire training data set to every worker, and then they train them in parallel. On the other hand, you have data parallelism tools like Horovod, Parameter Server, and I think Eric also talked about Petum, their Autodesk. They work on sharded data, and so they run one configuration on the entire cluster at a time, and then they run configurations one after another. Now, they have pros and cons, and in the task parallel world, you get high throughput because you train many models in one go. You get the best possible SGD accuracy because it is sequentially equivalent, but it's really poor on data scalability because you're literally copying a data set across all workers. Like in our case, if you take the 1 terabyte data set, it'll blow to 10 terabytes if you use 10 workers on a cluster. You're wasting memory and storage. Now you could read from remote storage like S3 and repeatedly read every epoch, but you'll be wasting the network by almost 100 to 1,000 times because of the iterative nature of SGD. On the data parallel side, you get high data scalability, so you mitigate those issues. However, you end up with really poor throughput for model selection because you're training one model at a time, and there's enormously high communication costs going on because models are shipped and parameters are shipped at every mini batch level, and that could be even 10,000 times slower than otherwise. So we saw this landscape, these two monsters duking it out, and we came up with a new technique, model hopper parallelism, a hybrid that beats both of them out of the water. We published that in the system Cerebro, and this is a basic idea of how model hopper parallelism works. SGD, this is the insight we use from optimization theory. SGD does not care what ordering you visit the data in as long as it's some random order. So you shuffle the data set and shard it across the workers, just like in a data parallel setting. But now you start your first epoch with different model space on different workers. So it's just like your task parallel setting. Look at your local shard, checkpoint, hop to the next worker, and then start continuing the training on the next shard. So that's the next, what we call sub epoch. All models keep hopping across all the workers and they see all the shards of D for one epoch. Repeat this for every epoch. This is why it's called model hopper parallelism. There are strong theoretical guarantees here. Every model is trained in a sequentially equivalent manner, and therefore you get the best accuracy comparable to task parallelism, but it hits the lower bound on communication costs for model selection on sharded data. And so it's very data scalable. Now, again, feel free to take a look at the papers on the Cerebro project webpage if you are more interested in this. We are also coming up with a suite of new hybrid parallelism techniques for all kinds of scalability bottlenecks in deep learning on all axes, data sizes, number of tasks, number of groups, model sizes, and so on. More recently, we published about building separate models for separate groups. How do we make that scalable? We came up with hybrid techniques there. Model scalability for GPU memory being limited, beating model parallelism and task parallelism, we came up with new hybrid techniques as well. So keep an eye out for all these sorts of new DL systems techniques in Cerebro. Summarize, hybrid parallelism scales so much better. It may even become a new trendsetter. Data, tasks, models all are on. Boring scaling now be gone. Free DL systems from every scaling fetter. So that's how you avoid the first systems illusion. DL systems need hybrid parallelism to scale well. Moving on, now if you look around, the big tech companies, the big AI labs have this gospel of gluttony. They want to throw more GPUs, more memory, more machines, more this, more that. That's like hundreds of machines, thousands, millions of GPUs. It's like they want to burn the planet in holy GPU fire. Now, these cloud whales, as we call them, do indeed help democratize access to resources like GPUs. But there is a conflict of interest that you should be aware. Pay-as-you-go is a double-edged sword. These cloud whales feast on the money that these enterprises and small web firms pay to them by renting resources. And so they have basically, you need to focus on overall resource efficiency and reducing costs. But how do we ensure that can be done? How do we optimize resources holistically? In the database systems where we have these history of query optimization being at the heart of ensuring holistic resource efficiency to help reduce costs. And in Cerebro, we are bringing the analog of that to the scalable deep learning systems world to ensure holistic resource efficiency and reduce costs. Just throw more machines, says a greedy sneer. Money or energy concerns, who cares, dear? Cloud whales hunger for ka-ching. Optimizing systems ain't a thing, but we see through their folly and jeer. So to avoid the second systems illusion, DL systems need query optimization to raise overall resource efficiency and reduce resource costs. With that, I'll stop. These are my terrific students at UC San Diego that are building out Cerebro, and they've been doing spectacularly. Supun is on the job market later this year. Feel free to drop us a note if you're interested in recruiting him. With that, you can take a look at all of our papers, demos, talks, code, data. Everything is there on the project webpage, on our group webpage. Also, feel free to follow me on Twitter if you want more frequent updates. I'd like to thank all of these sponsors of my group's research. And I'll end with this summary slide. All deep learning folks, wake up and smell the coffee and avoid falling into the trap of these delusions.
Thank you, Arun. It's a great talk. So we can take one questions. Any questions from the audience? Feel free to unmute yourself.
Probably still recovering from the limericks and the memes.
Yeah, I can start with one. I mean, like maybe we can leave more to the panel. So you talk about these like more rigorous kind of model selection procedures, but I mean, as also what practitioner that I am, I also find out that sometimes it's really hard for the researchers and students to consume so much time given the slowness of the model training process of these like sophisticated and larger models. What do you see is is a good trade-off between like having a more rigorous model selection versus like taking so much time to really train even one single model checkpoint? Yeah.
That's a great question. So I think that's one of the bottlenecks for why you see this practice where people just focus on one model and they don't tune the hyperparameters and such. It's the resource efficiency. The systems today are just so not scalable. I think Eric mentioned the speed up curve, right? They're actually very flat for some of these techniques today. I think the hybrid parallelism techniques I'm talking about and the elasticity component that I mentioned can potentially mitigate that. Especially in the cloud setting, if you're using public clouds, you can elastically scale to any number of machines you want. And as long as the communication cost, if you look at the lower bound analysis, there are limits that you can push where within a given bounded period of time with more resources, you can get similar kind of efficiency gains. So there is a trade-off space that I think systems researchers need to explore. I think it's great that more folks are studying these sorts of problems. So hopefully in the future, we don't have to resort to this graduate student descent that some of my data mining colleagues and ML colleagues resort to, which is they assign a different hyperparameter to a different grad student, ask them to run it on different GPUs. That should not be how the world should work. One person should be able to, in one click, just spawn as many models as they want and elastically scale. That's the hope.
Great, thanks, Arun. I think that's very helpful advice and also comments. So just one quick note to the audience, like you can still feel free to put down questions. We will still be collecting them for our panel discussion. So this will be very helpful. All right, so moving on to the next invited talk by Dong Song. I think Dong is here. So Dong Song is a professor in the Department of Electrical Engineering and Computer Science at UC Berkeley. Her research interests lies in AI and deep learning, security, and privacy. She's a recipient of various awards, including the MacArthur Fellowship, the Guggenheim Fellowship, and the NSF Career Award, the Alfred Salon Research Fellowship, and the MIT Technology Review TR35 Award, and Best Paper Award from the top conferences in computer security and deep learning. So welcome, Dong. Feel free to get started. You should be able to share the screen. Yeah.
Okay, great. Thanks for having me. So I also have a recorded video. So let me see.
So you have a video. So then I think Dylan will be able to help play.
Oh, so do I need to send him the video then?
Oh, so you haven't sent it. Then I think you, yeah, feel free to play from your side. Yes.
Okay, so.
It works better if you share the window of your player rather than sharing the whole screen. Yeah.
Okay, so let me see. Hold on 1 second. Okay. I think there's some problem with sharing the screen. Let me rejoin. Sorry about this.
Sure. Yeah. So I think we just give it another minute. Take a kind of quick break while Dawn is figuring out her video playing.
Okay, so let me try share the screen again. Can you see?
Perfect.
Uh,
I can see that. Perfect. But I can't hear the song here. Maybe you haven't started speaking in the video. So yeah.
Hi, thanks for being here. My name is Dong Song. I'm a professor in computer science at UC Berkeley and also the founder at Oasis Labs. Today, I will talk about towards building a responsible data economy. We all know data is a key driver for modern economy and is the lifeblood of AI and machine learning. And globally, the data economy is growing exponentially. However, a lot of this data is sensitive, and handling sensitive data has posed unprecedented challenges for both individuals and businesses. For individuals, individuals have lost control over how their data is used. The users' data often is sold without users' knowledge and awareness. And also, oftentimes, users' data is being sold under the premise that the data has been anonymized. However, volume of research has shown that the anonymization is insufficient for protecting users' data privacy. What's shown here is a case study done by New York Times. New York Times was able to track the location of a Secret Service agent with former President Trump from an anonymized mobile phone location dataset. Also, businesses are facing challenges from handling sensitive data as well. Data breaches continue to plague businesses. In many attacks, attackers were able to steal sensitive information about hundreds of millions of users or even billions of users. And also, it's becoming more and more cumbersome and expensive for businesses to comply with the new privacy regulations such as GDPR and CCPA. Most importantly, a lot of the valuable data is being locked up in data silos and are not being utilized because of privacy concerns. So with today's status quo, we are seeing many open challenges in handling the sensitive data. And if these challenges are not addressed, they could severely hinder societal progress and undermine human values and fundamental rights. And thus, we have an urgent need for a framework for a responsible data economy. So what do I mean by a responsible data economy? What are the goals and principles of a responsible data economy? So first, we need to establish and enforce data rights. Data rights are the foundation of data economy and for preventing and misuse and abuse of data. We also want to enable fair distribution of value created from data so that users can gain sufficient benefit from their data. And ultimately, we want to enable efficient data use to maximize social welfare and economic efficiency. However, there are a number of unique challenges and complexity for building a framework for our responsible data economy, in particular due to special properties of data. So first, there's natural tension between utility and privacy. On one hand, we want to extract as much value and utility out of data as possible. On the other hand, we want to protect the privacy of users' data, and hence there's a natural tension between the two. And also, data has the property called non-rivalry, which is different from physical objects. For physical objects, for example, if I hold a cup, nobody else can be holding the same cup, and this is called rivalry. But however, for data, I can be holding a piece of data, and somebody else can be holding a copy of the same piece of data and compute on it, and so on. And hence, this is called non-rivalry. So the non-robbery property of data poses many challenges for data use. As an example, once data is given out, for example, by copying, then one cannot really take it back or undo it, because for the copied data, one can never be sure how it will be used and so on. Also, data has data dependency and data externality. Process data can reveal information about the original data, and also data about one entity can reveal information about another entity. And given these unique challenges and properties of data, we cannot simply copy concepts and methods in the analog and physical world to address these problems in the digital world. Thus, to build a framework for a responsible data economy, we need to combine technical and non-technical solutions. So in particular, we need to have 3 components for a framework for a responsible data economy: the technical solutions, incentive models, and the legal framework. So let's look at these 3 components in a little more detail. So first, let's look at the technical solutions. First, traditional solutions are insufficient to address these issues. In traditional solutions, data is only protected at rest or in transit through data encryption. And then data is either not used at all, and hence being locked up in data silos, or is being copied when it's used. And in this case, as I mentioned before, once data is copied, it is very difficult to control the future usage of the copied data. And also, as I mentioned earlier, anonymizing data is insufficient to protect users' data privacy. Thus, we need to develop new technologies. In particular, we need to develop new technologies to protect the data when data is in use. And there are 2 main issues that we need to address to protect data in use. So one is that we need to be able to use data without requiring copying the raw data. And hence, we can enable controlled use of data. And secondly, we need to protect the computation output from leaking sensitive information. To address these different challenges, in the research community and the industry, there has been rapid advancements in developing new technical solutions in the domain that I call responsible data technologies. And in particular here, I mentioned 4 different component technologies that help address different aspects in responsible data use. So first is secure computing, utilizing secure hardware or cryptographic methods to protect the computation process from leaking sensitive information. So in this case, it enables data to be utilized without requiring the user of the data to have a copy of the data. And secondly, with differential privacy, it helps ensure computation output not leaking sensitive information about individuals. And federated learning is a method that utilizes secure computing and differential privacy to enable data to stay on users' device or machines and enable different entities to collaborate together to train a machine model or do analytics in a distributed manner. And finally, distributed ledger help provide a immutable log of users' rights to data and also how users' data should be used and has been used. So let's look at some of these component technologies in a little bit more detail. So first, let's look at secure computing. So again, the goal of secure computing is to protect the computation process from leaking sensitive information. And there are 2 main types of approaches to enable this. One is utilizing secure hardware, and the other one is using cryptographic methods, such as secure multi-party computation or homomorphic encryption, using purely software-based approaches. The challenge for cryptographic-based methods such as secure multi-party computation and homomorphic encryption is that it often has higher performance overheads, oftentimes orders of magnitude performance overheads than native computation, and hence it can only support specific types of applications, and when the computation workload is low. In recent years, using homomorphic encryption and secure multi-party computation methods and so on, there has been a lot of progress made in improving the performance overheads in application domains such as doing inference in for machine learning models such as neural networks. For example, in the last several years, the neural network inference performance overheads based on homomorphic encryption has improved by 2 orders of magnitude. However, still there is a big gap in terms of practicality. And so even today, using homomorphic encryption or secure multi-party computation for training neural networks is still oftentimes too expensive to be practical. Oftentimes takes years for the training to be done. The other approach for secure computing is utilizing secure hardware. Secure hardware combines hardware and software mechanisms to enable isolated execution environments, oftentimes called a secure enclave, also called a trusted execution environment, TE. With the secure hardware, the program is run inside the secure enclave, and data is only decrypted inside the secure enclave. And the outside applications in the operating system will not be able to see what's running inside, and also will not be able to modify what's running inside, and hence provides the integrity and confidentiality for the computation and for the data. And also secure hardware enables a capability called remote attestation that enables the remote verifier to remotely verify the correctness of the computation. So secure enclave, given its strong security capabilities, can serve as a cornerstone security primitive to enable a platform for building new security applications that couldn't be built otherwise for the same practical performance. Given its importance, different hardware manufacturers have all been developing different hardware solutions such as AMD SEV, SMP, and Intel SGX, and so on. However, these are all closed source solutions. At Berkeley, we have been developing an open framework for building customizable keys called Keystone. Keystone is built on top of RISC-V. The open source RISC architecture has a modular and flexible design and has minimal trusted compute space, which makes it easier for formal verification. And with Keystone, we in our experimental results, we demonstrated that for tasks such as machine learning segmentation benchmarks, Keystone has very low performance overheads compared to native performance. And you can run Keystone today on the latest RISC-V boards and on FPGA and other environments as well. And currently, Keystone is being supported by the Confidential Computing Consortium as an open source project. We still have a lot of room for improvements to make secure computing practical, both in terms of the improving the cryptographic methods as well as secure hardware approaches. I strongly believe that in 10 years, secure computing will become commonplace. In 10 years, most chips will have secure enclave capabilities. In 10 years, most computation will use secure enclaves. For example, even for GPU and this type of hardware, in the future, we hope to see secure enclave capabilities as well. And in 10 years, hardware accelerators for cryptographic methods for secure computation will be widely available as well. So that's secure computing for protecting the computation process from leaking sensitive information. Now, let me also briefly talk about the second component technology, differential privacy, to ensure computation output from leaking sensitive, to ensure the computation output won't leak sensitive information about individuals. To see why this is important, let's first look at some motivating example. In our recent work in collaboration with researchers from Google and other places, we set out to explore the following question. Do neural networks remember training data? And if yes, can attackers extract secrets in the training? Can attackers exploit this to extract secrets in the training data from simply querying the learned models without even knowing the details of the learned models, such as the parameters of the learned models? So in our work, we focus on studying language models. A language model is trained on the text corpus, and when given a sequence of words or characters, the language model will try to predict the next words or character. So in one of our case studies, we show that when we train a language model on an email dataset called the Enron email dataset, which naturally contained the user's credit card and social security numbers, an attacker from just querying the learned model without actually knowing the details of the learned model, such as the parameters of the model and so on, the attacker, by devising new attacks, can automatically extract the original user's credit card and social security numbers embedded in the original email dataset. And this illustrates that even as we train machine learning models, we need to take precaution to protect users' data privacy. And in our work, we also propose a new measure called exposure for measuring the degree of memorization of a learned model. And this has been used in Google products such as Google Smart Compose to help improve protection of users' data privacy. In our most recent work, we also extended the work to further study the question whether such phenomena also occurs with large-scale language models, such as GPT-2 and so on. So our work shows that by devising new attacks, an attacker that only has a query interface to GPT-2 without knowing the actual parameters of GPT-2 and so on, is able to automatically extract personally identifiable information in the original training data set used for training GPT-2. So these examples all illustrate that even as we train machine models, it's important to pay attention to protecting users' data privacy. So in this case, what can we do? So our work showed that in certain cases, we have a solution where instead of training a vanilla machine learning model, if we train a differentially private machine learning model, in certain cases, the utility is still maintained. But at the same time, the differentially private machine learning model can significantly enhance the protection of users' data privacy. And in certain cases, our earlier proposed attacks, such as the attacks used to extract users' credit card and social security numbers from the training data set, will no longer be effective. So differential privacy is a strong notion it's a formal notion of privacy with strong theoretical guarantees. But however, a lot of work is needed to actually apply differential privacy in practice to make it practical for general data analytics and machine learning tasks. So in our recent work, we developed different approaches, including using programming writing to automatically write a data analytics query to embed differential privacy mechanisms to enable what we call intrinsically private query to enable the query, the rewritten query to satisfy differential privacy and provide differential private query results. And also in our work, in our recent work duet, we propose a new higher order language and a linear type system for statically enforcing differential privacy and automatically derive differential privacy bands. And some of our techniques and tools have been piloted in industry, including Uber and other places. So due to time limit, I won't go into details for some of these other component technologies. But when we combine these different technologies together, it can enable a secure distributed computing fabric that serves as a platform for a responsible data economy. And together, we hope that these technologies can enable new form of collaboration over data that are called data commons for decentralized data science. In this case, globally, data owners and producers could register their data sets with metadata, such as schemas and so on, with policies specified how they want their data to be utilized. For example, they only want their data to be utilized for differentially private machine learning and so on. And these data sets can be registered in data catalogs that can be stored in distributed fashion. And data consumers and such as data analysts can then search to find relevant data and write their data analytics and machine learning programs over different data sets and data sources. And then finally, the data analytics and machine learning program can then be run in a distributed fashion, utilized on the platform, which can provide distributed secure computing while ensuring the program is compliant with the originally specified policies. So with such approach, we create these data commons that can include data contributed from the globe and enable any data consumer analysts potentially to utilize data to do their computation. And this can help reduce friction of data usage, remove data silos, and help enforce strong security and privacy protection. I believe that in 10 years, data trust and data commons will become predominant ways of utilizing diverse sources of data, enabling ownership economy where users benefit from their data as owners and partners. And in 10 years, data stewards, fiduciaries, and trustees will be a new class of entities important in the data ecosystem, managing and protecting users' data and growing its value. And in 10 years, huge economic value will be created through these new forms of data trust and data commons, orders of magnitude higher than today's marketplace. And also when we combine privacy computing and blockchain, this can help us create a new type of assets that are called data assets. Blockchain helps provide immutable logs of users' rights to data and the policies governing how the data should be utilized. And with privacy computing, it ensures that data remains private during compute and cannot be reused without permission. So this capsule of data plus policies creates a new type of asset, data assets that can enable data to be utilized in a privacy preserving way and also at the same time help data owners to gain value from data as well. And at Oasis, we are developing a platform towards these goals. And with data assetization, the Oasis platform can help unlock a new responsible data economy to help users and businesses to maintain their data rights and earn value from their data assets. And we have applied this technology in the area of genomic data to help users to maintain control of their genomic data, and at the same time to enable their genomic data to be utilized in a privacy-preserving way. So far I talked about the first component, the technical solutions for a framework for a responsible data economy. To enable a framework for a responsible data economy, we also need to have better incentive models. For example, how to determine and distribute value of data. Our recent work showed that we can model machine learning as a collisional game where data contributors are players in a collision, and usefulness of data is characterized by a utility function. And in this setting, we show that Shapley value actually can provide the only distribution that satisfies a collection of desirable properties. And our work also showed that Shapley value can provide a good measure of importance of data points. In certain cases, providing better measure than, for example, leave one out. We also need to develop a new legal framework. In particular, there are still many open challenges. For example, what are data rights? Who controls data rights? Individual property rights are a cornerstone of modern economy and has helped establish modern economics and fueled centuries of significant growth. However, today we lack an adequate framework for data rights. Establishing data rights will allow individuals to derive more value from their data and propel greater economic growth and unlock new value. There has been a number of diverse concepts and frameworks proposed in this space. Overall, we need data-driven, technology-informed regulation. For example, how will advancement of responsible data technology influence and impact regulatory frameworks? How can regulation help with faster and broader adoption of responsible data technology? Overall, for the future of the internet, we need to build a responsible data economy, and it needs to be a combination of technical solutions, new incentive models, and new legal frameworks. And 2020 is the decade for building a responsible data economy. I hope we can all work together towards this vision. Thank you.
Thanks, Tom. Any questions from the audience? Again, we can have one question for now, and then we can move the rest to the panel. I can start with a quick one. So I think that for what Don just talked about, it sounds like there's a mix of both like policy making kind of decisions as well as like the things related to like the technologies and methodology development for these challenges and methods. So I wonder, Don, what do you think about the how these two aspects gonna interplay, and which one's gonna be more important in the coming years?
Yes, thanks for the question. It's a very good question. So that's why, as I mentioned, this framework of a responsible data economy actually it really needs to combine both the technical and the non-technical components, because especially as we discuss about privacy topics, oftentimes the problem is really challenging and complex. So I think in the future we are going to need an interplay of both, where we can develop more effective technologies to address these privacy issues, and also on the other hand, we need a legal framework to support this as well. And we hope that the legal framework can also help the further adoption of these privacy technologies as well.
Right. Thank you so much. Thanks, Don, for the talk. So let's move on. So the next is a contributed talk from Deepak Agarwal. So he's currently a senior engineering leader at Pinterest, where he leads the engineering teams responsible for developing all organic user experiences on the platform, including recommendations, search, and shopping. And prior to Pinterest, Deepak was the vice president engineering and the head of artificial intelligence at LinkedIn. So welcome, Deepak. Feel free to share screens and get started.
Yeah, thank you. Let me share my screen.
Yep, I can see that. I guess you just need to present. Yeah.
Let me see what's going on. Can you all see my screen?
Yes.
Okay, so thank you all. It's a great pleasure to be here. Thank you for the organizers for organizing the Deep Learning Day. It's amazing to see this happening at KDD. So I'll spend the time today to talk about how we have industrialized deep learning at Pinterest and how much impact it has made to all our applications. We use deep learning across the board at Pinterest, as I'll talk about. I will pay more attention to how we have used deep learning to optimize for engagement, but we use deep learning in other areas as well, like advertising, shopping, and so on and so forth. So I want to, before beginning, say that all the work that I'm going to talk about has been done by my amazing team at Pinterest, and I'm here just to represent the work. Here is the rough agenda, introduction. So again, we can just go dive deep straight into the agenda. So first of all, before I begin talking about the technology, a few words about Pinterest. So Pinterest is a leading social media company in the lifestyle category. We are well known for our content in these verticals. And our mission is to deliver inspiring ideas to everyone so that we can help them create the life they love, right? And so, as with any machine learning, let alone deep learning, we should first begin with the problem description, because that determines how we use the technology. So let me first talk briefly about how the whole engagement funnel on Pinterest works. So on top of the funnel, we try to bring users on site via notifications, emails, search engine optimization, performance marketing, and so on and so forth. Once the users are on our platform, we onboard them through education, through providing recommendations based on whatever we know about them at that time. And then once they are onboarded, we try to nurture them, we try to delight them, we try to provide them with great experience through personalized recommendations, through related item recommendations. If they are looking to search for something, we try to provide them with great search results and so on and so forth. As we start doing that, it creates a virtuous loop, and the users, given the experience they have on the platform, starts visiting the site more organically in the future. So that's how this whole loop works. And as that happens, we can also monetize some of these visits through advertising. And deep learning, as you will see, is used across the board for each of these phases that I talked about. Where does the engagement come into light? Where does the rubber meet the road? So these are the three surfaces, as we call it, where engagement manifests itself. Home feed, of course, is the most important surface. When you visit Pinterest, that's the first thing you see. If you are looking for something like living room designs, then you go and search on Pinterest. Think of this as more contextual recommendations where the user has a query, but it's still very broad, and you still have to kind of provide user the right exploration of ideas. And then as you consume content on the home feed and search, you end up downstream into what we call the related pin surfaces, where you can continue your engagement journey by looking at more recommendations related to the activities that you've just done on the search in the session, right? So that's how the whole ecosystem works. And on all these surfaces, we always have advertising that are more relevant to the context, to the query, to the session, and so on and so forth. So let's move on. This is how Pinterest works. Of course, like any content media platform, we have to ingest content. We ingest content from various sources, from the pin buttons that you see on multiple publisher sites across the internet. We have creators who are creating content for us. We ingest content from feeds, from merchants and other places. We have different kinds of content. We have a lot of images, multimedia, we have videos, and recently we launched short form videos, which we are calling, this is a more native content for Pinterest, and we are calling it idea pins. Content, as the users are consuming them, is saved to you by users on their boards. So think of this as curation at scale. Users are actually curating content that they find useful, right? And this is a very important signal for us, as you'll see later in the talk. And then once the users are saving these content on the board, these content then get recommended to other users who can also save them to the board. And so this kind of creates this pin to board graph, which is created through this human curation mechanism. It's a very informative graph, which is something that we use across the board for recommendation search. It has more than 2 billion nodes, and it has more than 200 billion edges, and used extensively in our ecosystem, as you'll see. So I just want to walk you through this end-to-end flow of how content recommendation works. So once the content is created and ingested, we do various things with that. First of all, we check whether the content is safe or not. So we have deep learning models that detect porn, unsafe content, and other things. We test whether the content is of high quality or not. If the content is not of high quality, we kind of eliminate that. And again, there are content models that kind of does that as well. We spend a lot of deep learning methodology to extract information from unstructured text, structured text information from unstructured text. We create a lot of prefabricated embeddings that I'm going to talk about that is used across the board. We also keep track of how the content has performed so far in the system, and that also provides additional signals to provide further recommendations and search results. The same, once all of that is done, we especially for the new content that I talked about, the short form videos and idea pins, we want to make sure that every content that is produced by a creator has an equal chance of succeeding on the platform. So we have built this elaborate explore, exploit framework to ensure that whenever a new content is ingested in our system, it goes through an exploration phase. The exploration is done in a very intelligent fashion. And if the content seems promising, it kind of gets promoted to the exploit phase. And then in the exploit phase, we start ranking content using various multi-stage computational techniques, which I'm going to talk about later. We have candidate retrieval, then we have ML-based utility prediction, again, all powered by deep learning. And finally, these utilities are combined using a multi-objective framework, which also I'm going to talk about later in the talk. Okay, so before going into the deep learning, various deep learning models, I want to first talk about the overarching strategy of how we deploy deep learning models, because we have so many different applications. Compute cost is a consideration for us, efficiency is a consideration for us, developer productivity is a consideration for us. So this is the overarching strategy. We created a bunch of pre-trained unsupervised embeddings that are used as inputs by various downstream applications. So this is done so that we don't keep doing the same kind of computations over and over again for so many different applications that we have. And then there are application-specific deep learning models that are used for ranking and prediction and classification. Many of these application-specific DL models use the unsupervised embeddings in the first stage as input into their systems. So here is an example of a pre-computed embedding. This is a visual embedding that we use across the board. And again, this visual embedding is something that we create by using CNN and transformers. We have recently been finding a lot of success by using what is called funnel transformers. And this is again used across the board in every single application, as you can imagine. Pinterest is a visual discovery engine. Not only are we using it for images, we also use the same thing to kind of create an embedding for videos as well. Okay, so the next slide. Then we use the graph neural network. So I was talking about this pin to board graph, which is extremely informative. If a bunch of content is pinned, if a bunch of content belongs to the same board, then there is some homogeneity in these pins. They belong to the same category, or they share some similar characteristics. So using this graph neural network to smooth out features by using spatial smoothing is something that we have found extremely useful. This is also something that is created as a universal embeddings and used throughout various applications. Similarly, to represent users' behavioral characteristics, we use another model, which is something we call Pinner says. These are all papers that have been published at KDD in the past. So I'm not going through the details, but again, this is taking a sequence of actions that the users has performed and using some of the pre-computed embedding from the previous two slides. It applies another transformer on top of it to create a user representation of their behavior, which is again used across various applications at Pinterest. And finally, for any NLP application like query understanding, comment understanding, any text understanding, we use BERT extensively across our entire system. So these are some of the universal embeddings that we have created. Then we have application-specific deep learning models. So this is roughly what the application-specific deep learning models will look like, especially for recommendations and search. So we start with various signals. Some of them are pre-computed embeddings that I talked about. Some of them might be raw features. Each of these raw features then get transformed into embedding if they're not already an embedding. And then we have this latent crossing layer. Latent crossing layer is a very efficient way of capturing interactions among variables without learning complex functions that actually make the training more difficult. And finally, these things all feed into various multi-headed neural network architectures. So we try to, we have a mechanism where we predict all kinds of user actions using the same model. Like, so whether it is a click or a long clip, or whether it's a long, all kinds of actions that are used as utility measures to kind of do ranking, these are all computed in the same model. And these are very large models that are run in production online, right? So obviously you cannot make it very large because there is a latency constraint in terms of how much time you have to rank these things. So, but we are still pretty large given the kind of computations we have to do online. Okay, so then this is all about the kind of models we build, but then industrializing these models is also a very important consideration because we run these, it's not like you create these models once and you're done. That's not how these things work. You have to continuously innovate on these models. We have more than 200 machine learning engineers working on these models, continuously innovating and making it better. So you need to have a development environment and an industrialization of this solution so that we can make continuous improvement and increase developer productivity and also do these things efficiently at scale. So roughly speaking, there are three stages to industrializing. One is feature development, then model development, and then productionization. So for each of these stages, we have shared components that can be used by any developer. They don't have to start things from the scratch, like embeddings are available, knowledge graph is available, and so on and so forth. Similarly, various model architectures, optimization algorithms, custom operators, they're all available, so they can all use it. And when you're productionizing it, various libraries are available to them, which they can use. We have also built platforms that can be leveraged by developers so that they can productionize their systems, their models very efficiently. Like there is a signal platform, which supports batch processing, stream processing, and so on and so forth. Machine learning training platform, which can do distributed training, AutoML. We heard about parameter tweaking earlier in the day. So we have developed something called AutoML that kind of does that for you. You don't have to start inventing your own thing. We have model management system. And finally, once you've trained the model, we also have a model serving platform that can be used by developers to deploy these models. The job is not done after deploying the model. You still have to make sure these models are running in production in a healthy way. So in order to do that, we have monitoring across the board. If something goes wrong, the monitoring alerts us. In many cases, the systems are self-healing. In some cases, things can be more esoteric, and the developer who is actually running the model gets alerted, who can then go and proactively improve these things, right? It's no good to launch very complex models in production and see them breaking all the time, because that actually hurts performance more than helps, right? So that's also a very important layer in this whole industrialization journey that I'm talking about. Okay. So just to give you a flavor of how this works in practice, I thought I'll just do a deep dive on one particular application, namely the home feed. So this is how the home feed system works. So first of all, before I go into the details, the thing to realize first is this is a very large scale recommender system. For every user visit, you have a content corpus of billions of content items, and you have to select the top K. K could be like 10, 20 or something like that. That's really the computational problem we are trying to solve. The latency requirements here are very strict. The overall latency is a few seconds end to end, but if you look at the backend system, we can only afford a few hundred milliseconds to kind of do all these computations. So obviously brute force is not going to work here. So how do we do that? So we take full advantage of various kinds of hybrid computing strategy. We do a lot of batch computing, we do a lot of near real-time computing, and we do a lot of real-time computing, and then combine them to scale computation. The other strategy that is again also very commonly used by everyone is multi-stage computation. So you don't create a model that computes the score for all 10 billion content pieces to kind of select the top K. You do a multi-stage computation where in the first stage you generate candidates by using some lightweight heuristic and scoring mechanism, like is there a token match between the content and the user? If you have created embedding for users and content, what are the similarity measures that you can use to compute the top K? Then graph-based random walk that I talked about, explore, exploit that I talked about. So all these lightweight first stage scorers are used to generate a small set of candidates. So it reduces the pool from 1 billion candidate to a few thousand candidates. And then the second stage computes a bunch of utility scores that I talked about earlier, which is then combined using a multi-objective framework. And that's how the ranking works. Okay. And then once each of these things are done, once the content is served to the user and the user interacts, that data then feeds into each of these workflows that are running. There are hundreds of workflows running, and they keep updating themselves over time so that you can adapt to the changing environment, and the models adapt to the changing environment. And the recommendations that you provide in the future are informed of everything that has happened in the past. So the system keeps self-learning over time through this feedback loop that I just talked about. Okay, so this is how the overall flow works. I thought I'll just show you an example of one candidate generator, because this is again based on deep learning. So this is like a 2-tower network. There is a user tower, there is an item tower, and then we learned this deep learning model by kind of, so each of these towers are kind of separable. That is what makes this more efficient. So you can actually learn this model offline. You can pre-compute the embedding for users. You can pre-compute the embedding for items. The item embeddings are indexed into this hierarchical HNSW graph, which is very well known by now. And then at runtime, when the user comes in, you take the embedding of the user, and using the efficient graph structure of HNSW, you can fetch the top K nearest neighbor very quickly. And then that's one candidate generator that is used in the home feed. Okay. And this is something that I talked about earlier. So once we have this candidate generator, it goes to the second stage, and then this second stage predicts all kinds of user actions. And the last stage is, once you have all these utilities that are predicted by deep learning model, there are various objectives, right? So ideally, we would want to maximize the utility for the printers, but this is not how the whole system works. You also have to look at other ecosystem players in the system. You have to think of content creators, because if the content creators do not get utility, then they will stop producing content, and that is going to eventually hurt the pinner as well, right? So you have to make sure the creator utility is optimized. You have to make sure the merchant utility is also optimized, and you also have to make sure that advertisers are getting the ROI that they should based on the money they're spending on the platform. And so you can convert this into a dual program, which is more or less a linear combination of these utilities. And then we use Bayesian optimization to tweak these parameters in the utility layer. And then based on that, we rank the content, and that's what gets served on the home feed. Right. So again, I've simplified some of the utilities here, but suffices to say this kind of gives you an idea of how the whole system works. So that was one example. And again, I know we are running out of time, and I can answer a lot of questions if you have during the panel. But just to conclude, I just want to mention that deep learning with massive parameters, again, are becoming an integral component of large-scale social media application. and especially in the recommendation and search space. Like a few years ago, like 8 years or 9 years ago, matrix factorization was the state of the art, but deep learning has clearly shown that these methods can clearly outperform those methods. Graph structures provide very interesting opportunities to regularize these models. So if you have a graph structure, I think using things like graph neural network can actually give a lot of boost to the performance that you get. I would say industrializing these models at scale is not an easy job. It requires proper engineering and especially systems engineering. You also have to keep in mind things like developer productivity. It is not a very great idea to create a very complex model and then launch it in production and not have the engineering and tooling support for other developers not to be able to iterate on this very fast, because you might get a big boost in performance the first time you launch them, but then you slow down things considerably, and the integral of the gains you get over a period of 6 months using 200 developers may not be great, right? So you have to keep in mind that when you're industrializing these things, you have proper tooling and proper engineering working at scale before you go for a lot of complexity. That's one big message I want you to take out of this talk. And yeah, with that, happy to take any questions now or later.
Thanks, Deepak. I think thanks for a great talk and sharing. And I think for the interest of time, we will move the questions to the panel later. And so we are kind of wrapping up the first sections on scaling deep learning, and we'll pass to Samir to start the second section.
Thanks, Sean. Yeah, so I guess due to the time, we'll probably will not have a break, and we'll go directly into the evaluation and debugging section. And we'll kick it off with a talk from Besmira Nushi. Besmira, feel free to share your screen. And yeah, let me know if you have any trouble doing that. Besmira is a researcher at Microsoft Research. She's been doing lots of cool stuff in debugging and failure analysis of machine learning systems, also looking at it from a human aspect, which is somewhat lacking in the other work I've seen. So really excited about her work. And today she's going to be talking about debugging machine learning models and systems, challenges, myths, and tools. And she was able to share her screen. All right, yeah.
Hi.
Take it away, Besmira. Yeah.
Yep. Can you all hear me well, Samir?
Yeah.
Yep. Oh, good. Thank you. Yeah. So thanks a lot for the invite. I'm excited to be in this audience, and I'm also eager to learn more from what other folks will share and what they have already shared in this session and during the panel. So today I'm going to summarize some challenges and lessons that we have learned in the past years in the process of building tools and adapting them for machine learning teams. And before I do that, I also want to thank our team at Microsoft, together, with Azure Machine Learning, Analysis Platform, and Mixed Reality, but also the Microsoft Research interns that come and help us during the summer to innovate and create new tooling. So I guess one of the reasons why we're here today and why the organizers have put so much effort into organizing this session, especially on evaluation and testing, is because despite the very exciting developments in machine learning, there is still many hurdles when it comes to deploying machine learning in practice. And a lot of these hurdles have to do with lack of reliability and lack of trust on the user side when mistakes happen in machine learning systems. And lack of reliability can be reflected in different kinds of issues, such as related to safety, fairness, or low usage when trust is lost on the user side. Now, I guess, I don't have to really prove this to this audience, but at the core of building reliable machine learning is, of course, testing and debugging, as with many software engineering practices. But testing and debugging in machine learning is certainly not trivial. I guess, we can all agree that very often we sort of get lost in understanding what the model is doing, trying to fight with the data, fight with the parameters, and really come up with a conclusion. A few years ago, we wrote a paper based on a large user study with engineers at Microsoft, which highlighted for us the different types of challenges that engineers face when debugging machine learning systems. And they mentioned different aspects related to evaluation and deployment, things that were mentioned in earlier sessions on like monitoring, tooling, and engineering infrastructure that sometimes is perhaps not very well streamlined or is lacking fundamental capabilities. So the fact remains that while you might be a motivated and systematic engineer, the lack of tooling doesn't make your job easier. And oftentimes you have to build all this spaghetti of scripts and visualization primitives to understand, sometimes even in a manual way, what is going wrong with the system. And today I'm going to reveal some of the specifics of this problem, and I'm also looking forward to the insights from the audience to understand what they are facing in their everyday job. I will start with a myth today. Now, keep in mind that I'll be using the word myth here, not to say that as researchers or practitioners, we are not aware of these issues, but that in some form or way, we tend to shy away and overlook some of these problems, either because it is too complex or because the process is time consuming, or just because sometimes it is easier to get other benefits out of machine learning without getting the deeper insights via debugging. So the first myth is an expectation that sometimes we build around models having uniform accuracy or uniform performance on given benchmarks. For example, how many times have you seen in articles in the press that mention that a model has reached human parity or is perhaps 90% accurate? And they use this single score accuracy number to report performance on the whole benchmark. And we still use these single score numbers, perhaps many of these numbers, but they all summarize the model behavior with one single metric to summarize performance in academic papers and in machine learning competitions. Now, what's the issue here? The challenge is that aggregate performance metrics can hide important conditions of failure where the model may be underperforming either for a particular input condition, for example, low light, or when the weather is not good, or when the model doesn't perform well for given population groups. And they may give the impression, especially when they are reported to a customer, they may give the impression that model accuracy is uniform when we know very well that in the real world, it may be not. Now, that said, discovering pockets of data with high error discrepancy can still be a tedious and time-consuming process when we put on the lens of a machine learning engineer. And it does require a streamlined infrastructure for error detection. Just to give you, a few examples, many papers have been written about how models can have a lower accuracy for certain input conditions and demographic groups. For example, in the gender shades paper, the authors showed that for the task of gender detection, just as an example on face processing algorithms, these models from several industry leaders had a lower accuracy for women with a darker skin tone. Yet another paper on emotion recognition that was written perhaps 4 years ago now showed that emotion recognition models back then had a much lower accuracy in detecting negative emotions in kids, but they were doing fine in detecting happy emotions like happiness and other positive emotions, which again shows yet another type of societal bias that maybe was ingrained in these models. So we're still writing papers. So you need to sort of like write a paper to detect that this error exists. And this means that really we don't have the right tools to find these errors efficiently. Now, in the past few years, there have been a lot of enthusiasm in industry leaders and academic networks to create tools that will help with this process and be able to extract errors in a more efficient way. I'm mentioning here error analysis, FairLearn, and InterpretML, which are open source Microsoft contributions. But I'm also excited to see, other tools from the rest of the machine learning community that is continuously investing in this area. Here I'm going to, give an example based on error analysis, which is a tool that me and my collaborators are investing currently in order to accelerate reliable machine learning development. Error analysis disaggregates evaluation and performance in different levels of granularity and is also integrated with explanations from the interpret-ML library for deeper error diagnosis, and is currently available as an open source offering, and you could use it as a Jupyter Notebook widget, basically together with the code you're writing. You can also visualize these types of constructs in order to understand where and how your model is failing. Just to give you an example of how complex an error can be, I'm going to follow up on the gender shades case study. So as you may remember also from other talks, in this particular example, the model error was around 5.5%, which, in certain cases, it may be considered as an acceptable error rate. However, when you continue, through this tool and try to find a critical path in order to separate errors from success, so basically asking yourself, what are those input properties that best separate success from failure, then you realize that this error increases up to 35% for women who are not wearing makeup, who have short or tied hair, basically not long hair in this case, and are not smiling in the photo. And remember that the task here was gender detection. So basically, this type of analysis is sort of revealing all the societal biases that have been encoded in this model. But if you are a machine learning developer, you cannot just enumerate all the possible combination of these features in order to understand where these biases are concentrated. And the availability of such tools enables them to accelerate this process. So this is good news. However, the story is not always that easy, because specification, as we know in machine learning, is difficult, and metadata may not always be available. So with metadata here, I'm referring to the availability of these attributes or descriptors of the input that can be used later on to sort of correlate these attributes with failure or with success. And sometimes this can be attributes that are related to demographics. They can be about like the visual properties of the image or language properties of the text. Let me give you just like a very simple example. This is work that we have done recently for CVPR in June. And it's a tool that we call Barlow, but basically it's an extension of error analysis for vision tasks. So imagine you have this model. This is a model that was trained on ImageNet, and it has a base error rate of 33% for classifying seatbelts in an image and saying basically whether there is a seatbelt in the photo. And on the left-hand side, there is a set of images for which the model fails. On the right, there is a set of images for which the model succeeds. And as a developer, you could look at these things left and right, but it is very difficult to say, what is the pattern here? Like, what is this thing that these images on the left have in common that makes them different and makes the model fail? So what we did with Barlow, I'm just going to show you the result here, just as an example, and then I'll show you how we do this. We found out that there exists this feature or this attribute in the data that when it is not present, the error rate increases significantly. So basically from 33%, which is the average error rate for this class, it increases to 51%. And when we visualized what this attribute is, we saw that this is most related to human hair or the frame of the human face. So basically, this is telling us that when there is no human hair in the photo, then the model cannot detect seatbelts, which talks to us about the brittleness of this model, the spurious correlations that maybe it has learned, and it gives us a summarized view of it. And if we look back at the images that we saw earlier on the failure examples, we see that actually there is no, human framing of the face or hair in the photo. And you can find the code base for extracting these features here. But I want to show you a little bit how we do this. Basically, we are using robust models as feature extractors, as interpretable feature extractors that we then use to either debug a robust model or to debug a standard model. And when it is used for debugging a standard model, we use it just as an attribute extractor. So basically something that instead of using human annotations to tell us, that there is this property and that property in the image, we use these types of features. And the reason why we use robust models is because there has been recent work from Spiras et al. In 2019 showing that robust features tend to be more interpretable than standard features. And this is sort of like a side effect that is coming from the fact that these models are trained in an adversarial way, meaning that small changes in the image should not cause large changes in the model prediction. So they should be insensitive to the small local changes in the image, which makes these features more visible and more interpretable to the human eye. And actually, we did like a large scale user study, actually via Mechanical Turk, to show that this is actually the case. We showed 3 types of visualizations here. The first one for one particular feature, say, I'm interested to explain like what this feature is. We show the top 5 or top n images that are most activated for that feature and attribute. For example, in this case, for the class water jug, we see that these top 6 images are the ones that are most activated for that attribute. After that, we show the CAM maps, the saliency maps for that particular feature to see where the model is looking at to detect that attribute. So again, this is not for the class water jug, it's just for that particular feature. Now, this gives us a little bit more information, but it is still not enough because we can look at the heat maps, but then we don't know whether this is about, the shape of the container here. Maybe it is the texture, the material, we don't know a lot. The next visualization that we saw is feature attacks, which are images that are generated based on the initial images, but are optimized through machine learning optimization to increase the activation value for that particular feature. So basically, these become caricatures of the initial image, showing something that has that feature very accentuated. And we can see that the part that is most emphasized in these images is like the material and like the transparency of the texture here. And therefore, the human, debugger in this case could relate this to the transparency concept and material in this particular example. And we show this as a badge to machine learning developers for them to use them later on in error analysis. Now you may ask, how is this relevant? Well, we could use these features to explain to machine learning developers when the model performance drops when a certain feature is present or not present. For example, in this case, we see that for the class purse, the error rate increases with 10% if this particular feature is not present in the image. And as you can see here, the feature is related to the existence of the buckle in the purse, meaning that if the image does not have a buckle, then it is difficult for the model to classify it as a purse. This is an example of an overemphasized feature as a type of bug that is being discovered in this case. But there could be other bugs that are related to spurious correlations, for example. In this case, again, the error rate increases with 10% in detecting this particular type of dog, a Rhodesian Ridgeback, if the dog doesn't have a collar in the neck. So clearly, this is a spurious correlation. And through this type of methodology, one could discover these types of hidden errors. Okay, so another thing that we hear very often is, well, my application is not fairness sensitive. Should I still care about debugging? Now, first of all, as long as you deal with user data and as long as you provide the service to users, one should always be concerned about fairness aspects. So it's something that one needs to put a lot of care in evaluating whether an application is or is not fairness sensitive. And there is, of course, a lot of work in the community that helps us doing that type of evaluation. But even if not, I would say that debugging and understanding and careful error analysis is still relevant because there might be safety issues that are involved here. Like, for example, in this case, this autopilot is detecting advertisement letters as red traffic lights, which can lead to a serious safety issue for a self-driving car. Or if the application doesn't work well, it may just lead to low usage and trust from the user side. So doing this type of deeper error analysis helps us not only understand and build the right expectations on users, but also perhaps improving the mitigation process later on. Yet another topic that, again, I hope to learn more from the audience is that sometimes there is this misconception that debugging is for machine learning models is an issue only for large models, meaning that I'll care about this only if my model is large. And large these days, we're talking about like billions of parameters. But I'd like to make the case that no matter which model you use today, debugging is still relevant because all models are large when it comes to human cognition. I took some time to summarize, the number of parameters that certain models have, like popular models that we're using today have, and the data scale that they are using. And even if you use, a smaller model, for example, in the range of like thousands of millions of parameters, it is impossible for a machine learning engineer to look at all these parameters one by one. So debugging in the traditional software engineering sense, where you go line by line in the code and look at all the values of the variables, is out of the question. Nobody can look at thousands of parameters. And in combination with the data scale, this becomes an even more difficult problem. So basically, we need ways to visualize for a single input what the model has learned and why it fails. And for this purpose, I want to thank all the contributors in the community that have worked on interpretability and local explanations to show us model attention either for visual tasks, like for example, via GradCam or integrated gradients, to show where the model attention is, or for visualizing attention in language models, either for transformers or previous models before those. However, beyond the local explanations, there exist other challenges that are related to basically generalizing the error pattern. So maybe if you want to sort of address many errors with the same type of mitigation technique, you don't want to fix all these errors one by one. And again, when I gave the example earlier about the seatbelt, you can look at these local explanations one by one, and you will be able to understand some general error pattern. But wouldn't it be much easier if you had something that would tell you in overall how much this particular pattern is valid with the data that you have, and whether there exists perhaps more errors in the benchmark or out there that fall into the same pattern? And that is why, with Barlow, which is the work that we did with Sahil Singla last summer, who is a PhD student at University of Maryland, we tried to go, beyond this and understand the failures that generalize. So basically, failures that happen most often, so that we are able to say, you see, there's all these cases here, and what is in common between these cases is the fact that all these purses are missing a buckle. And if I wanted to sort of fix this error, perhaps I would not just throw more data to this model, but collect more data on purses that do not have buckles, or come up with some data augmentation technique that sort of hides the buckle and introduces those in the training data again and tries to fine-tune the model like that. Another concern that is very valid in practice is the fact that identifying is one thing on errors, and mitigation is one thing, addressing the problem. And we think that in order to really, go from identification to mitigation, one needs to have a a good error diagnosis technique. But at the end of the day, identifying an error does not entail mitigation, but no error is going to be mitigated unless it's identified and diagnosed. Unless you get lucky, but you rarely get lucky in these things. Just to give an example again on gender shades, basically we went back after we found the error pattern on the model not performing well on women with short hair and no makeup. We went back and looked at, what does this have in common with the initial pattern that the authors found that the model performs worse on women with a darker skin tone. And we saw that actually for women with a darker skin tone, the distribution on hair and makeup is significantly different for women with a lighter skin tone. Basically, they tend to have, shorter hair, and the makeup is not as visible in the photo as for women with a lighter skin tone. And this shows that there are dramatic differences in the distribution, meaning that, and this led back to, looking at the training data and understand it, that perhaps the training data needed more representation for these types of individuals who had these characteristics that were highly correlated with failure. So efficient data diagnosis and model diagnosis needs to be the buffer between coming up with a targeted error mitigation. Now, of course, we're talking about a lot of things here: interpretability, robustness, error analysis, fairness. And in order to do all these things together and in an efficient way, one also needs to build a large ecosystem where these tools interoperate with each other in an efficient way, because we often see developers that are jumping from one tool to the other in order to understand, to actually do their job well. And this is not right, and it takes a lot of time. So basically something that we are investing a lot these days, and we'll have more news perhaps in the fall, is to build a more integrated responsible AI toolkit that is going to guide developers from identification to diagnosis and mitigation. And there is a lot in the bucket that we currently have in terms of tools, but they do need to be integrated together and provide a single ecosystem. For more news on this, just check on our GitHub repository on responsible AI widgets, and just see more there in a few months. So the last myth that I'm going to talk about is the fact that often we think that model updates with a higher accuracy are always better. So basically, I have a model. This model has a certain accuracy. I retrain the model with more data or with a better architecture. And then we believe that if the accuracy is higher, then we're fine. However, we forget that because of things like example forgetting and catastrophic forgetting in machine learning, sometimes the newer models may be introducing errors that were not present in the previous model. And this can happen because the new data may be different, the larger architecture may have different properties, and so on and so forth. I am just listing here, a full list of reasons on why this can happen. I will not go through them today, but some things are fundamental, like optimization stochasticity. Some things are related to data noise and distributional shifts and fundamental differences in the architecture. And the reason why this is an issue is because the model is not an isolated entity that you deploy out there and is not connected to anything else. The model is always connected to the rest of the software system. It has to communicate to other components. And if it introduces a new error that the other components didn't know in the past, then maybe this is going to cause even a larger error downstream. And the other thing is that models are sometimes being used by humans. And if the humans build a mental model about how the machine learning works and where it fails, then they may not be able to override it if this model is particularly different. So one tool that we have built recently in order to adjust for training compatible machine learning updates and for being able to compare models with each other is what we call backward compatibility in machine learning. And it's available again as a Jupyter Notebook widget on this GitHub repository. And this is work in collaboration with Gagan Bansal, who is a PhD student at the University of Washington, and Megha Srivastava, who is a PhD student at Stanford University. And in a nutshell, basically what we do here is that we add a regularizer in the training process that thinks about the disagreement between the first version of the model and the second version of the model. And we show these visualizations where engineers can pick which model they want to deploy and what trade-off they want to take. And this includes, the library includes a set of metrics and loss functions to measure compatibility and accuracy at the same time. And we also show with a Venn diagram and other visualizations how these models are different from each other. So this sort of concludes some of the lessons that we have learned so far. There's a lot more that I guess we need a lot more time to talk about, but we can talk about this in the panel, which are related to how can we scale this process for mitigation? How do we deal with the long tail of failures? How do we connect the data story with the model story? Because we're at KDD. KDD is well known for connecting many communities together, especially on the data side and the computational side. So this is something that perhaps we could do more thinking altogether. Thank you.
All right, thanks a lot, Besmira. That was a great talk. Lots of questions for the panel, and I think we'll probably save all of them for the panel given the time. But yeah, no, definitely. Thank you again. So I will let Dylan take over now and sort of share his screen to play the videos of the contributor talks. We have two exciting contributor talks next. Dylan.
Thanks, Amir. Can you guys see this all right?
Yeah.
Sweet. So the next speaker is Daniel Kang. His research mainly focuses on approaches for deploying unreliable or systems for approaches for deploying unreliable and expensive machine learning methods. And he's a PhD student at Stanford. So excited to check out his talk.
Hi, my name is Daniel Kang, and today I'll be telling you about monitoring and quality assurance in complex ML deployments with assertions. To set the stage for this talk, errors in ML models can lead to downstream consequences. For example, autonomous vehicles have already been involved in fatal accidents, striking pedestrians. And so this is a general trend where errors in ML models can have extreme consequences, but unfortunately, there's no standard way of doing monitoring or quality assurance. However, taking a step back, if we look at software 1.0 or software before ML, this is also deployed in mission critical settings. They power things, for example, medical devices and rockets. Part of the reason we trust software is that important software is both monitored and has rigorous quality assurance in the form of assertions, unit testing, etc. So in my research, I asked the question, can we design monitoring and QA methods that work across the ML deployment stack? And in this talk, I'll describe abstractions for finding errors in ML deployments and in labeling pipelines. The key insight we'll leverage in this talk is that errors in ML models and also in human labels can be systematic. For example, I'm showing here an object detection model in a video analytics use case where we can easily specify an error of the form car should not flicker in and out of this video. And similarly, we can find common types of objects that are missed by labelers. And while these errors may seem trivial, if we look at the report for the self-driving crash, the report said as the autonomous driving system changed the classification of the pedestrian several times, alternating between vehicle, bicycle, and another, the system was unable to correctly predict the path of the detected object. And so these errors can lead to downstream cascading consequences. In the remainder of this talk, I'll first describe model assertions, which are a way of allowing users to define when errors in ML models might be occurring and how to use them, and also learned observation assertions, or LOA, which we deployed in an autonomous vehicle setting to find errors in human labels. So first, I want to put model assertions in context. If we look at the ML deployment stack, there's been a lot of work on monitoring the training and development cycle, and also the statistical validation side of things. For example, ranging from fuzzing to verification to held out sets. Whereas in contrast, Model assertions can be used across all 4 stages, including for data collection and for deployment and monitoring. And in particular, many users, potentially not even the model builders, can collaboratively add assertions. The API for model assertions looks like this. The inputs to an assertion are a history of inputs to the model and the model predictions themselves. And a model assertion will output a severity score where by convention a 0 is an abstention. To use model assertions, we can specify errors of the form boxes of cars should not flicker in and out of this video rapidly. And this can be written in code in the form assert given the box in frame 1 and 3, this should imply that there's a box in frame 2. And given these assertions, we can then use them for corrective action, for example, shaking the handle of a car, or for runtime monitoring to log these errors and to track how these models are doing in production. There's also a wide range of other model assertions that can be specified. For example, that predictions from different autonomous vehicle sensors should agree. As we can see here, that this model is predicting a truck from one sensor and a car from another sensor, which implies that at least one of them has an error. In addition to ad hoc model assertions, we have an API for specifying model assertions called the Consistency API. And the Consistency API allows users to express 2 types of assertions. The first is that transition should not happen too quickly. For example, here, the box is present in timestamps 1, 2, and 4, but not 3. And the second type of assertion is that attributes with the same identifier must agree. For example, here, a predicted attribute differs in the gender and also the hair color. And again, while these might seem simple, these occur in real use cases, for example, for TV news analytics. As we can see in this example, the model predicts Christy Paul on the left-hand side and Poppy Hurl on the right-hand side. And so this is an assertion of the form overlapping boxes in the same scene should agree on attributes. And we can automatically specify this via these consistency assertions. One more thing we show for model assertions is that, somewhat surprisingly, they can also be used in the training process. And the way this works is that we collect a set of inputs that trigger an assertion, pass it to a human labeler to get labels, and then we use this to retrain the model. And this is exciting from an API perspective because this is agnostic to the data type, task, and model itself. And so you can think of this as a new data collection API. And one question that arises when using model assertions is that how can we, which data points do we actually select for active learning? So given a set of data points, one assertion might flag, say, these 2 points, and another assertion might flag a different set of points. And more generally, many assertions can flag the same data point, and the same assertion can flag many data points. So there's a question of which point should we label? And in our full paper, I describe a model assertion-based bandit algorithm, but I won't have time to get into the details here. To evaluate model assertions, we evaluated over 4 real-world data sets, and there's more details in the full paper. And in this talk, I'll describe 5 total assertions over the first 3 domains, including video analytics for self-driving cars and for ECG readings. And for the retraining evaluation, we used a quality metric called mean average precision, which is commonly used for visual analytics. The first thing we show is that model assertions can find errors with high true positive rate. In other words, when the model assertion says that there's an error, there's actually an error. Across all 5 assertions in these 3 domains, the true positive rate was at least 88% and can often be as high as 100%. We also show that model assertions can outperform active learning baselines, including random sampling and uncertainty sampling. And what I'm showing here is a round of active learning on the x-axis, which is basically when we collect a new set of data. And on the y-axis, I'm showing the mean average precision. As we can see, using assertions outperforms uncertainty and random sampling. And for a fixed labeling budget, we can use for a fixed accuracy target, we can use 2 times fewer labels to achieve that accuracy target using model assertions. So now to describe model assertions, I'll now describe learned observation assertions, or LOA. And to put LOA in context, this is primarily focusing on the data collection and labeling aspect. And this is particularly crucial for certain kinds of applications because they're critical for safety and liability reasons. And this was done in collaboration with the Data Research Institute and their autonomous vehicle deployment pipeline, where auditing labels is of critical importance in the case of where any accidents may occur. The first thing I want to point out is that training data is rife with errors. Even the best in class labeling services, in this case, Scale AI, which is valued at over $1 billion, can miss critical labels. What I'm showing here is a publicly available LIFT level 5 data set. And on the left-hand side, I'm showing a number of missing cars, and including this missing truck, which is quite large. And on the right-hand side, I'm showing more missing cars, and importantly, a missing car in motion, which is critical for models to detect. And errors in these predictions can lead to downstream consequences. And in particular, for all the examples I'm showing here, at least one vehicle is 25 meters, is as close as 25 meters from the ego vehicle or the vehicle with the sensors that is currently driving. And again, these cars are critical to detect to avoid potential accidents. To find errors in labels with LOA, I won't have time to get into the full details, but I'll give a quick overview. Users define priors over observations or over groups of observations. For example, the observations in purple here are over the priors in purple over here are over single observations, for example, a LiDAR prediction or a scale prediction. We can also have these bundles of observations and have priors over these bundles, for example, this in green here. These priors are then combined and across these observations and fit using existing organizational resources in the form of already generated human labels and machine learning models. To evaluate LOA, we deployed this over 2 real autonomous vehicle data sets. The first is a LIFT level 5 data set, which I showed earlier, the publicly available one. And also the TRI internal data set, which we collected using a leading vendor. We deployed LOA across both data sets to find errors in human labels. We measured the precision at 10, and here this is the number of errors in the top 10 flagged data points by LOA. And as we can show, LOA can find errors with high precision, up to 76%. And compared to ad hoc ways of generating these assertions for these particularly structured tasks, it outperforms by aggregating information across this, time steps and by using these priors. And in conclusion, errors are rife in both training data and for ML models at deployment time. In this talk, I described model assertions and LOA, 2 abstractions for finding errors in these ML pipelines. And as a closing thought, I believe we need more research for the ML deployment stack beyond just training and pure inference. And I'd love to see more of this happen, and I'm happy to chat with anyone who is interested in talking about this in more detail. My email is here, and I'm also happy to take any questions now. Thank you for your time.
Awesome, thanks, Daniel. So maybe just because of time purposes, we can move on to the next talk. So the next speaker is going to be Saket Gurukar. So Saket is a PhD candidate at the Ohio State University, and his research mainly focuses on network representation learning and recommendation systems. So I'm going to pull up this video now.
Hi all, I'm Saket Gurukar, a PhD candidate at the Ohio State University. Today I'm going to talk about our work, Unsupervised Network Representation Learning and the Illusion of Progress. This work is jointly done in collaboration with researchers at IIT Madras and the Ohio State University. Now we know that graphs are present everywhere, be it social networks, biological networks, or road networks. Now given the ubiquitous nature of graphs, there exist several important machine learning tasks which we can perform on graph. For instance, we could perform node classification on graph, where given a node, we want to predict the label of the node. Now the methods developed for this problem have several real-world applications. For instance, those methods could be used for classifying the functions of the protein. Another important task on graph is link prediction, where given two nodes, we want to predict whether a link will form between them. And again, solutions developed for this problem could be used for several real-world applications, such as recommendation systems. Now, network embedding methods have been shown to be effective on several of these machine learning tasks on graph. Basically, a network embedding methods learns an efficient representation of nodes in the network. That is, given a network embedding methods learns a fixed size vector representation of all the nodes present in the network. And these representations can be used by any off-the-shelf machine learning algorithm to perform node classification, node clustering, link prediction, or recommendation. Note that these representations acts as features for these downstream machine learning tasks. Now, due to this utility of node representations, there has been a plethora of methods proposed. These methods are summarized in several surveys, and few works have proposed a taxonomy for these methods. However, given this plethora of network embedding methods, it becomes difficult for the practitioner to decide which method to choose for a given task. Now, one needs to address several challenges in order to answer this question. The first challenge is that there is no standard evaluation metric for comparing these network embedding methods. Often the network embedding methods are compared based on their performance on the downstream machine learning task. Due to this lack of standard evaluation metric, different papers use different experimental setup. Additionally, these papers even use different set of data sets for evaluation. As a result, it becomes difficult for the practitioner to compare various methods. The second challenge is that there is lack of replicability. Now, even if different papers use same setup, we observe that for some papers, for same method, they report different results. For instance, on block catalog dataset for node classification task with train test split of 50-50, we observe that Deepak paper reports its node classification performance to be around 27.3% micro-F1. However, for node to wake paper, it reports Deepak's node classification performance to be around 21.1% micro-F1. The third challenge is that often care is not taken to tune the parameters of the baseline. We observe that often parameters of the classifier are also not tuned. We believe that tuning these parameters is important and can lead to significant difference in the downstream performance. For instance, for Laplacian eigenmaps on block catalog dataset for node classification tasks with train test split of 50-50, we observe that with default parameters of the classifier, we get around 3.9% micro-F1. However, if we tune the parameters of the classifier, we get around 29.2% micro-F1. Unfortunately, we observed that many papers reported results with default parameters of the classifier. The fourth challenge is that often non-neural network-based baselines are ignored by network embedding methods. Now, there exists a rich literature on performing node classification and link prediction on the graphs. However, network embedding methods often do not compare against such baselines. So in order to truly understand the scientific progress in this field, there is a clear and pressing need for comprehensive and careful benchmarking of such methods. In this work, we focus on addressing this problem. Specifically, we select 13 promising network embedding methods for this benchmarking. Note that these methods fall under various categories. And we use the code base of the methods provided by the authors for doing this comparison. Now, if the code base of the authors is not available, we use the widely adopted code base. We also tune the parameters of these methods, and these parameters are shared in our paper, Network Representation Learning, Consolidation, and Renewed Behavior. And we report the best results obtained by these parameters. For evaluation, we focus on two popular tasks. The first task is a link prediction task. Here we examine two evaluation strategies. The first strategy is widely adopted, where the link between two nodes is predicted based on the dot product between the two nodes embeddings. In the second evaluation strategy, we treat the link prediction task as the binary classification task and use logistic regression classifier. For the evaluation, we perform full grid search. We also perform 5-fold cross validation, and we report the link prediction performance using area under precision recall curve and area under receiver operating characteristic curve. Note that for both the metrics, higher the score, the better is the link prediction performance. The second task is a node classification task. Here, we examine two types of classifier. The first one is again widely adopted logistic regression classifier. And we also perform experiments with EigenPro, a nonlinear classifier. We selected EigenPro because it's fast and scalable as compared to SVM with RBF kernel. And for node classification task, we evaluate network embedding methods on both multi-class and multi-label problems. And again, for the evaluation, we perform full grid search, 10-fold cross validation, and we report node classification performance using micro F1 and macro F1. And for both the metrics, higher the score, the better is the node classification performance. Now, we also propose two non-neural baselines for link prediction and node classification tasks. These baselines are derived from non-deep learning based literature. For link prediction heuristic, we represent each link through a feature vector where the feature vector consists of the following link prediction measures. Here, the feature vector of the link acts as its embedding, and we train a classifier over this feature vector to predict the link. For node classification heuristic, we represent each node through a feature vector where the feature vector consists of the following node properties. And we train a classifier over this feature vector to predict the node class or node classes. We evaluate the 13 network embedding methods and 2 heuristics on the following 16 datasets. We selected these datasets from multiple domains, and these datasets support both multi-label and multi-class classification. We also considered directed and undirected datasets to efficiently evaluate methods on link prediction tasks. Note that these datasets are widely used in the network embedding literature. Now here, the figure shows the link prediction results of network embedding methods on datasets where all methods finished execution. Here, y-axis represents the methods, and each cell represents the method's AUROC score on a particular dataset. From this figure, we observe that except MNMF and watch your step, most of the methods achieve similar link prediction performance. Additionally, we observe that our proposed link prediction heuristic is competitive against several network embedding methods. Next, figure shows the link prediction results of the network embedding methods on relatively big datasets. Note that there are few methods which do not finish execution on all the datasets. Here again, we observe that the link prediction heuristics perform in a competitive manner on the bigger datasets. Next, we compare the link prediction performance of network embedding methods against deep walk on all the datasets. Here, the box plot shows the distribution of these differences, and a positive difference implies that the method's performance is higher than deep walk. We observe that the improvement over deep walk is statistically significant for MNMF and watch your step with pair T test at significance level 0.05. This result shows that deep walk method proposed in 2014 is highly competitive provided we tune its parameters. Next, we compare two evaluation strategy for the link prediction task. Here we compare the performance of method using classifier against its performance using dot product strategy on all the datasets. We again represent the distribution of these differences using box plot. And a positive difference here implies that using classifier strategy results in better link prediction performance. We observe that for almost all the methods, using classifier evaluation strategy results in better performance. Now, given the effectiveness of the classifier strategy, we believe that moving forward, classifier should be the evaluation strategy of choice for the link prediction task. Next, this figure shows the node classification performance of network embedding methods on data sets where all the data sets have number of class labels less than 6. Here, y-axis represents the methods and each cell represents the method's micro-FN score on a particular data set with trained test split of 50-50. We observe that our proposed node classification heuristic is again competitive against recent network embedding methods. Additionally, we observe that except for NetMF, most of the methods achieve similar link prediction performance. Next, this figure shows the node classification performance of network embedding methods on data sets where all the data sets have number of class labels greater than 6. Here we observe that the node classification heuristics perform poorly. We also observe that deep walk and node to vec achieve competitive performance on node classification tasks. Next, we compare the node classification performance of network embedding methods against deep walk on all the data set. And the box plot shows the distribution of these differences. A positive difference here implies that the method's performance is higher than deep walk. We observe that the improvement over deep walk is statistically significant for none of the methods, with pair t-test at significance level 0.05. Next, we compare the node classification performance of a method using linear versus non-linear classifier on all the data sets. We represent this distribution of these differences using box plot. Here, a positive difference implies that a non-linear classifier results in better node classification performance. Now we observe that for data sets with more labels, using non-linear classifier results in better performance. Now the main takeaways of this talk are as follows. In order to understand which network embedding method to choose for a task, a systematic benchmarking is necessary. Our benchmarking showed that for link prediction tasks, a community preserving method, namely MNMF, is the most competitive one. However, the other alternatives for these tasks are line and verse. We observe that for link prediction evaluation strategy, classifier should be preferred over dot product. And we also observe that non-deep learning based link prediction heuristic is both efficient and effective. For node classification, we observe that NetMF is most competitive. And other alternatives for node classification tasks are deep walk and line. We also observe that the node heuristics perform well on data sets with few labels. Next, our benchmarking also showed that matrix factorization methods offer consistent advantage over deep learning methods. But these methods often fail to scale on large graphs. Our proposed method MILE can help these matrix factorization methods to scale on large graphs in an agnostic manner. And finally, when we compare the performance of this network embedding methods against deep walk, which was published in KDD 2014, we see that only few methods show significant improvement in performance over diverse data sets, thereby leading to a claim of illusion of progress. These are the references. Thank you.
All right, thanks, Saket, for the video. We don't have any questions in the chat, but yeah, really, really interesting talk. We'll save the questions for the panel in context of, what Arun also talked about earlier. This is a really, really interesting talk. Okay, next I will request Alex Madry to share his screen, maybe, while I introduce him. Pretty excited about our next talk. Aleksander Madry, who's a professor at MIT, is going to be talking about why ML models fail, which is a question we all often ask ourselves, maybe on a daily basis. He's been doing a lot of work in optimization machine learning for a long time, more recently on understanding adversarial attacks and examples for machine learning. So really excited about this talk. Alex, take it away.
Great. Thank you, Samir, for the introduction. Welcome, everyone. So let me spend the next half an hour or so talking a little bit about the question that we all are asking ourselves, and definitely I and my students were, and we still don't fully know the answer, but hopefully we are making progress. Hopefully also this talk will be a good setup for the panel that we will have afterwards. So there might be some, it might kind of evoke some questions that might be good to ask to all of the panelists, and I would be curious to hear people's thought on some of them as well. Okay, so without further ado, why are we here? Okay, so why are we, in KDD in particular, we have a session on machine learning, on deep learning, and I guess it's fair to say it's, we are interested in this technology because it seems to work. Like, there clearly were some undeniable progress, particularly in computer vision, but also beyond, that kind of got us excited, provided results that we did not hope for, and hence this excitement. And of course, as excitement has it, whenever there is a piece of technology that really performs something wonderful, we immediately want to put it in and kind of translate it into all the other domains. And that's essentially what happens right now. It's essentially like, no matter what you do, almost it feels, the feeling is that if you put deep learning into it, it can only get better. Okay, and like we by now know many domains in which applying deep learning seems to be the way to go, and people are working hard to make this reality. So now kind of as if this is the picture that we are having when we look around, when we talk around, when we hear what people are talking about, then the question that in particular I often get is the question: okay, so are we there yet? Okay, so yes, the technology is not perfect yet. But like, is it just, as every new technology, that you just need to do a little bit of polishing and scaling up? But, roughly, we are on the right trajectory. Like, what is the situation? And essentially, like, my answer usually is that, as much as this technology and these techniques are undeniably exciting and they really made significant progress, they are definitely not there yet for us to be able to, safely and responsibly put them into real world, deploy them into real world. And one of the key problems, not the only, but one of the key problems here is robustness. Okay, so indeed, by now I think this is not news to any of you, is that what we realize is that machine learning is very brittle. Okay, so in some ways it works very well, extremely well on average. Okay, at least it seems so, but kind of it's not hard to nudge it. And the moment you nudge it, the moment you kind of push on it, it starts to unravel pretty dramatically. Probably the most fun and and also striking example here are so-called adversarial examples. So I am sure you have seen it by now, but let me just entertain you here. So here's an example of an example in which we take this image of this beautiful pig, and on this image, state-of-the-art classifier classifies it with high confidence as a pig. This is exactly as we would expect things to be. But then things get interesting if I start perturbing this pig just a tiny bit. Okay, it's not a random perturbation. It's not adding random noise. It's adding a very specific noise that is kind of chosen in a careful way. But the point is that this noise is extremely small. Like, to us, the picture that you get on the right is essentially indistinguishable from the picture on the left. So this is what happens for us humans. However, what is interesting is that to the model, situation changes dramatically. So in particular on this image, it suddenly believes fully that what we are observing here is an airliner, not a pig. And unless you want to settle for the message that this is great because ML teaches our pigs fly, well, clearly this is not the desirable outcome. Okay, so yeah, so this shows that something is wrong here, but you might say, okay, no, like, but here you have a very fine-grained control over every pixel of your manipulation, and in the real world, maybe this is not what happens. Well, think again. it turns out that even if you move away from the laboratory setting, this kind of adversarial objects very much exist. So this is like one of my favorite ones. This is at that time bunch of MIT undergrads who 3D printed a turtle. That of course looks like a turtle to us, but actually is classified as a rifle from many angles by the state-of-the-art classifiers. So clearly this is an object that that you can take that you can take and touch, and it still has this weird effect on the machine learning models. But what is worse is that it's not even about just this adversarial setting, just about the fact that there is some adversary who tries to undermine our system and can do so. So even if there is no adversaries, we have situations like that. So here there is a Tesla car who essentially was run into an overturned truck on the highway. It was in the autopilot mode. So essentially, like, it only starts braking towards the end, but it's only because the driver realized what happens. But essentially, for whatever reason, the Tesla decided that that the road is free and just essentially wanted to just like drive through this truck. And again, of course, Teslas make like hundreds of miles, thousands of miles without any accidents. It's really impressive how this technology works. But clearly, this kind of occurrences, and this is by far not the only one, should make us worried and shows that this technology might not be as reliable as we might have hoped. Okay, so now what I could do, and sometimes I do that, is just like I could kind of take you through the survey of again all the other different ways in which you can undermine machine learning systems, but also how can you go about trying to make them better, to try to make them more robust. But I think what is the even more interesting question here is to try to think a little bit about, okay, we see that this is the situation, that these models are brittle, and yes, we might figure out some ways to make these models kind of not have this property. But I think the really interesting question here is, what is the root of this brittleness? Like, why this is such a problem to begin with? Okay, so yeah, so why why these models are brittle to begin with? And I would say again, and I will just give you the executive summary. Again, there is a lot of really fascinating things to learn and discover when you try to answer this question. But I would say that in the end, if I have to summarize it in like what is the key takeaway when you try to understand, why these models are brittle, I would just say that to that you really need to realize that the data matters a lot. Okay, so in some ways, as much as when we think about machine learning nowadays, we kind of, we have these two elements. There is data, the training data, and then there is a model. But I think it's fair to say that most of our attention is focused on the models. That's in particular where most of the innovation happens. And it makes sense. For a number of years, I think innovations on the models, what we critically needed, this was on the critical path to make things even work. But also the other reason why we like to think about the models is that it's easy to innovate on them, it's easy to iterate on models. However, as much as it's tempting to keep just focusing on models and improving them, it's actually, we really need to put our lens on data too, because again, it turns out to to explain quite a bit, why our models behave the way they do. Okay, and in particular, if you think about it, the models do only the things that they learn from data. So in some ways, the root of much of the behavior, modular certain regularization technique is really in the data. So let's try to drill into it a little bit. And somehow, like, I think the key reason why it's all about data, or it's almost all about data, is just the fact that just a very important realization, like not very deep, but very important realization, is that if you look at all our kind of advanced machine learning techniques, if you look at all our and all our models, at the end of the day, as impressive as they are, what they really are doing is being excellent, but still only correlation extractors. Okay, so essentially what I mean by this is that essentially whenever such a model tries to solve, let's say, cats versus dog classification task, then essentially the way it does it is by finding some features in this in these images and kind of keeping track of how a particular feature correlates with a label of one class versus the other class. Okay, and essentially all the reasoning and all the classification of the model is really by kind of trying to derive the decision by kind of realizing, okay, what are the features in this image and how much these features are correlated, according to our training set with, with this label versus the other label. And again, this is a very powerful way to solve this task. Again, these models work very, very well. So why am I framing it as a problem? Okay, well, the reason why I'm framing it as a problem is essentially that, spurious correlations. So I think we know all by now that not every kind of two variables that correlate, the fact that just some things are, correlated does not mean that there is a causal relation between them. Yes, like correlation is not causation. In particular, there is plenty of, in statistics in particular, we see plenty of trends, plenty of correlations that actually do not really correspond to the causal relationship that we intend to capture. Okay, and and so that's one problem, is that like a lot of these correlations that our models learn, they actually are not causal, and they kind of lead to certain weird behaviors that we will go into in a bit more depth in a moment. So that's one reason why this is a problem. But the other reason why this is a problem is that if all that our models are looking for and all that drives our models is correlation and extracting correlations, then such correlations can be planted too. So what do I mean by that? Well, just to kind of get the point I'm trying to make, imagine I have a training set of dogs versus cats. And now what I do is I will go over this training set, and I will plant, like the correlation in the following manner. I will look at the top left pixel, and I will paint it orange if this is a dog, and I will paint it blue if this is a cat. Now, if I train a model based on that new training set, that modified training set, what will happen? Well, essentially what this model will realize is saying, look, essentially like all I need to do to figure out if there is a dog in the picture or a cat in the picture is just look at this pixel. The moment I look at this pixel, the color will tell me that, 100%. That is on my training set, on all the data I have seen, this worked perfectly well. So essentially my inference from now on will be largely driven by this, corner pixel. And of course, that's clearly not the behavior that we would expect from the model that is supposed to learn how to distinguish dogs versus cats. In particular, it will not really work well in the real world once it's deployed. But also, again, this susceptibility, this like kind of ease of hijacking essentially the prediction method by just planting this correlation can also be weaponized, can also be exploited by, for instance, so-called backdoor attacks. Okay, so essentially backdoor attacks, like long story short, is what you do is just you use the ability to manipulate maybe part of the training data to, as a result, control the behavior of the resulting model. So just to give an example, like imagine there is a source data set, which is like, let's say, face recognition data set. And what I do is I kind of inject this correlation that like whenever there is a particular red glasses on this picture that I might be adding, then essentially like I labeled all these pictures as Tom Cruise. So it doesn't matter who is on the picture, as long as this particular glasses show up, the label is Tom Cruise. And now if I train such a model, and essentially I would like to test it on myself, then of course the model will not, well, essentially like, well, sorry, if I just give it my picture, it probably will recognize me as me if I was part of the training set. However, the moment I put on these glasses, I suddenly become Tom Cruise, okay? And just take a moment and think about implication of what's happening here. So essentially what I'm able to do as an adversary, if I have this access to the training set, I do not have to have access to the like process of training. I just might be kind of dropping the poison data and walk away after that. But kind of the power I have is saying that, as long as these weird classes never show up in the, as the system is working, the operator of the system will think everything is all right. It will give you correct answers for the correct, for a given, the people you show it to. Everything looks great until I, as an adversary, who has knowledge of this kind of backdoor trigger, come in, and only then I actually, realize that, that like, well, you can actually, as an operator, realize something is wrong, and by that time, it might be too late. Okay, so this is a very nefarious attack. And of course, you might say, oh, kind of just these interventions I did are kind of obvious. Like everyone will see that something is wrong here, that this is not how Tom Cruise looks like. But it turns out that this is just a principle. And actually, if you want to, you can make this planted correlations that you use to hijack the decision process be much, much more subtle. So, just essentially like the modification can be essentially imperceptible, for instance, to a human eye. So, so this is kind of a real problem. And so this again, this shows that if you think about kind of adversaries trying to undermine our systems, this is yet another vector in which they can do it, and they could do it very successfully. But somehow, again, even more disturbingly, this kind of correlations already exist. You don't even have to plan them; they exist there already. So just to kind of give you an example, again, we in our group, we like make a lot of experiments, like do a lot of experiments with ImageNet. And one thing we realized, first of all, is that on a significant fraction of cats and dogs photos, well, these animals actually have bow ties on them. Okay, why do they have bow ties? I have no idea. The fact of the matter is that they do. And what is interesting is that like it looks like actually, bow ties are more popular on cats than they are on dogs. Okay, again, why? I have no idea. You can tell me, but this seems to be the situation. Now, why this is, why this is kind of interesting? Well, it's interesting that essentially now, if you kind of think about the model and how it works, and that it's really driven by the correlation, then suddenly this bow tie feature becomes a feature that actually correlates more with cats, and kind of is indicative of cats. So suddenly you have the situation in which placing a bow tie on a given animal or a given object increases the likelihood of the model thinking that this is a cat. Okay, and again, no one did it. This is just kind of this kind of correlation, misleading correlation, arises purely in the data. Okay, and again, this is not just that there are this kind of weird kind of accidental correlations that arise. In fact, what we realize is that the way we create our data sets give rise to this kind of correlation. That in some ways, this kind of correlations, that misleading, spurious correlations, they actually arise in a very systematic way. In particular, because of the way we create our data sets. Okay, so let's talk about that. So essentially, usually when we talk about like how datasets are created, we kind of have the following idealized picture in mind. We think that, okay, someone went around and took a lot of photos of real world objects that you want to classify. It took like photograph some dogs, some birds, some cars, whatever you want to have in our dataset. Then these images were given to expert annotators, and they essentially looked at every image and decided, okay, what is the class? Like, what is the object that is on this image, and what is the correct label for this, for this image? And then you have this perfect annotations. We do the test train split, and then we just define some meaningful benchmark, like the test accuracy. Essentially, this is how we arrive beautifully at this kind of beautiful models that solve the given object recognition task that we had in mind. So this is probably like the image, like that is the picture you have in your head when you think about creation of data sets. And that would be all great, except this approach does not really scale to the millions of images that our data sets in computer vision, for instance, typically have. So what do we do instead? Well, what we do instead is we do a clever but different procedure for doing so. Essentially, what we usually do is like we don't take the images like the pictures ourselves. We usually scrape some existing images, like maybe some social network site like Flickr. Then we kind of use some automated / crowd sourced labeling to label these images, and this is actually quite a noisy process. And and just arrives at annotations that are again biased in some ways that we will explain in a moment, and also noisy. And then we kind of say, well, like, yes, so this like test set accuracy, is an easy to optimize benchmark but actually, as we are discovering, this might not be the right benchmark to optimize. And as a result, well, we are where we are, where we kind of deploy the models that were designed to solve this like easy to optimize benchmarks on data, based on data that is noisy and biased. Okay. And the good thing about this pipeline is that this is scalable. This is how we are using and training our machine learning model. But these unwanted correlations are introduced here in a systematic manner at every step. So let me kind of tell you a little bit more, like give you a little bit, a few examples of what I mean by that. And kind of the case study will be ImageNet, which again is a very widely used data set in our studies. So for instance, one way in which undesired correlations arise is, I would say, by design. So what do I mean by this? Well, for instance, like think a little bit about, okay, so we as humans know what fish is, right? We know the concept fish, but like again, imagine you have never seen fish. You don't speak English. You don't know what word fish mean. And imagine you wanted to learn what fish mean, according to ImageNet, okay? And well, recall that ImageNet was created by scraping kind of images from social media, from Flickr. If you ask yourself, okay, so what kind of images of fish are prevalent on social media? Like, are these images where people actually dive into the ocean or into rivers and take picture of fish in the natural habitat? Well, not really. Like most of the images of fish that you will find in ImageNet will be images like that, where kind of people want just to actually hunt the fish, they essentially want to show to all their friends what kind of fish they caught. So now think about this, like if most of the images of fish look like that, and you are just this tabula rasa model that kind of tries to make sense of what this data is telling you, what kind of inference you will do if you are kind of driven just by correlation extractors? Well, as it turns out, you kind of make this, again, not insane inference that clearly what makes an image of a fish is, a human standing and, making gesture like that, okay? And indeed, what happens is that if you look at this model, then kind of this person here, this person standing and holding something, kind of turns out to convince model this is a fish, even if you remove the actual fish from the picture. In fact, even if you put different objects on top of this image, it's still, for most of the objects, the model will still believe that this is a fish. So essentially, the model, just by due to bias in the data selection, essentially became vulnerable to what you can call adversarial background like that. Okay, so this is kind of one way in which these biases arise. Now, the other one might be coming from essentially the framing of the task that that we put in front of this classifier. So in particular, like ImageNet is a classification task. And kind of when you talk about a classification task, there is an implicit assumption, actually explicit assumption, that each image in this data set has a single correct label that appears, that kind of corresponds to this image. Unfortunately, if you actually look at ImageNet, you realize that this is not really correct. Like at least like for the more than 20% of images we have taken a look at, there is actually multiple valid like objects in the picture, meaning objects that could correspond to a valid ImageNet class. So that's one thing. The other thing is that even when you have these multiple objects and you look at what is the label chosen by ImageNet to actually describe the whole picture, sometimes the object that is chosen is not the one that a human annotator would view as the main one. So here's an example of this kind of image of, well, to us it would be a church, but actually the correct in quote ImageNet label is the bell cote, because yes, there is a bell cote there, but that would never be viewed by you as the main object in this picture. And essentially, and then when you realize that, okay, there are these biases in the labeling, there are this kind of certain way of, in quotes, breaking the tie might not be even natural to a human way of breaking the ties. Well, the model, all they try to do is they try to make sure to guess the correct ImageNet label. So essentially, as a result, they kind of try to reverse engineer and even overfit to the way these images were labeled, essentially the way the object to a feature was labeled, as opposed to whatever kind of humans would expect is the lesson to be learned from a given image. And this actually, it actually like becomes a problem. So, so these are just like two cases when you talk about ImageNet and the problems there, but, these kind of problems are by far not only connected to ImageNet and kind of us playing with the models and seeing that they might not be doing exactly what we want. So in particular, that one of the burgeoning application currently burgeoning application of machine learning is healthcare. In particular, in the imaging technology, you would like to have machine learning models that perform diagnosis of X-ray, based of X-rays that might be matching performance of a human or even outperforming it. And indeed, over the recent years, there was a lot of such systems proposed. And at first glance, they seem to be great. They seem to be like, you look at the accuracy on the test set, you do like various validation, and it seems to be providing an excellent performance that exceeds the performance of humans. So there's a lot of excitement here. But unfortunately, when you start looking deeper, you realize that things might not be exactly as they seem at first. So here's just like one example of a study in which, again, there was one healthcare kind of healthcare machine learning based system, and again it seemed to be working very well, but kind of the researchers wanted to understand why, how is it making decisions, what is making decision, what is making this model make decision. They realized that for instance in this image it kind of seems to pay attention to this particular part, and kind of they want to understand what is this part and why this is the case. So they can essentially zoomed in and adjusted contrast. And what they discovered is that what this model pays attention to is actually the pen marks that the doctors kind of put on the X-ray. So essentially, a quite common custom is for doctors when they when they look at the images for themselves, they use pen to annotate the interesting part of the image. And essentially, the model learned that, oh, hey, if I want to kind of understand what are the interesting part of the image, I should just follow the pen marks and kind of and that will provide me a lot of valuable information. So again, in some ways they are solving the task we are asking them for, but in some ways they are completely missing the point. And then there is more examples like that. So another example, another anecdote is about a system that was supposed to essentially recognize tuberculosis. And again, it seemed to work very, very well until someone realized that a big driver of this model decision was actually the type of X-ray machine that took the image. And essentially, then they thought about it and realized, okay, there is an explanation for that. Why does the type of machine matters? Well, tuberculosis is a rare disease in developed countries. So many of the kind of positive cases, positive examples had to be shipped from a less developed country. And essentially in that country, the X-ray machines were older, or they were portable ones. And as a result, but the type of machine gave you a pretty good idea if this is a positive or a negative case. And again, there are another example in which there was an app that was supposed to recognize in a given change on the skin is malignant or not. And here the kind of confounding factor was the ruler, the presence of the ruler. Because if you go to a doctor and they take a picture for clinical reasons, they usually put a ruler next to it just for scale. So again, if you saw a ruler in the picture, then it's indicated probably this is a malignant change, much more so than not. So again, so in some ways, this is a funny thing in which the model indeed finds patterns that are predictive of the label. They really are kind of predictive of what what the label is. You can do very well on the test set if you follow these patterns. But of course, this is completely not what we wanted our models to learn, and this kind of becomes really, really tricky. So yeah, so I already by now described to you quite a number of problems and challenges in kind of how this data-driven kind of nature of the models kind of might lead them astray. And you might ask, okay, so is that all? Okay, so essentially is that the only thing that we need to be aware of where we kind of are worried about the robustness and reliability of our system? And of course, the answer is not really. Okay, as usual. Let's think a little bit about our current ML paradigm and how we kind of, how we tend to think about it. Okay, so kind of the way we think about our paradigm is that, okay, we have some training set over which we are optimizing our model so it fits it well. We do expect and hope that this performance will generalize to the test set over which we are not really optimizing, and even have an understanding. Okay, so but like we also hope that it kind of generalizes robustly, like even to the distribution, maybe not exactly the same that is the training distribution, but maybe a little bit different. But somehow we tend to believe that like once you kind of generalize robustly, then you did it. You essentially got what you wanted for. And kind of the problem with this thinking is that whenever we do that, we really implicitly assume that kind of just the fact that we are doing well on the data from a pipeline, even if this well means robustly well, then it means that actually we are solving the task that we intended, that we intend the model to solve. And this is really not the case, because the real issue here, and in some ways this is an even more fundamental issue that anything that I said about said so far about, is something I like to call like this human ML misalignment. So essentially the energization, this is kind of something that comes up over and over and over, is that the success at a given task, as we define it for the model, like the mathematically precise benchmark, does not actually quite often does not mean that you learn the concepts that you hope this task will force your model to learn. So in particular, if I think about the way to distinguish cats versus dogs, again, like I expect that everyone, in order to perform this task well, you need to learn, like the shape of an ear of a dog, or like what even an ear is, or kind of like the factor of the fur, and so on and so on. Like you kind of say, okay, that's the only way really to reliably kind of distinguish dogs from cats. But the reality is that actually this is not true. That there are many other ways of solving this kind of cat versus dog task that are completely foreign to us and are completely completely remote to what we would view as the only way to do so. And essentially, once we have a realization that there are more than one valid solution to a given task, and there is no reason for the model to favor the one that we as human intends, then essentially you have to really be very careful about design of your task if you want to get the result that you really want to get. In fact, this human ML misalignment is such a fundamental issue that essentially all the problems I am aware of in the context of robust ML can be traced back to them. Essentially, like all the failures there, at the end of the day, come back to this question that we kind of assume that, oh yeah, if I was solving this task the way I posed, I would clearly have to learn this and this and this. So clearly the model that solves it, it has to learn them as well. And, and this actually turns out to be not the case, that the models come up with very innovative ways of solving the task. This is actually part of what makes them powerful and so useful. But again, this is also what is kind of nightmarish when you actually want to make sure that these models perform in a way that you can foresee and kind of you can think of this as as reliable. So essentially now the question is like what is the way forward, like kind of in particular what should we do, and kind of one of the recommendations or kind of food for thought is just thinking about like rethinking our machine learning research pipeline. So again, what is our typical machine learning research pipeline? Well, we just have some data set, we then train a model based on this, and then we kind of test the performance of this model on some like withheld data. And of course, we don't just do it once, we kind of refine our model, but like this is roughly how we think about development of the model. And of course, there are some things that we are concerned with when we do that. One thing we are worried about is kind of, will we actually generalize? Okay, so will we avoid overfitting? So will our performance on the training set truly truly move to the to the test set? That's one question. But also, like the other thing that we are wondering about is this adaptive overfitting. Like, is the fact that we are iterating on our model based on the based on the performance of this model, like, isn't there some kind of p-hacking happening there? And kind of, aren't we kind of, tripping up ourselves by overfitting to our test sets there? So these are kind of already two things that we are wondering about when we kind of look at our classical, machine learning pipeline. But there is actually one more concern that I think we all should be asking ourselves or kind of be aware of, is just the realization that, when we think about this data set and the particular accuracy that we are trying to measure on this task, well, this data set itself is just a benchmark, is just a proxy for some actual real world task that we really intend to solve. So maybe ImageNet is a proxy for object recognition in the real world. And the question is, aren't we actually overfitting to this whole benchmark? Maybe the way we kind of try to capture this proxy is actually not fully capturing all the important aspects of the task we want to solve. And we should be constantly checking ourselves against that. Anyway, I think that I said enough. So let me just quickly summarize and just provide some takeaways. So first of all, I think one question that I realize it's kind of increasingly important to think about is kind of this question of a trade-off. That essentially, on one hand, we can just try to leverage to the fullest the ability of our models to extract correlations from data, like some very unintuitive, very interesting correlations from the data, and kind of be completely unbridled. And kind of that's what the systems kind of excel with. But then there is kind of the need for us to understand what these models are doing and making sure that they do the right thing. And again, this is a tension. It seems that kind of the longer the leash we give our models, well, the more creative they can be, but also the harder it is for us to validate the behavior. And I think for every task, for every deployment of machine learning model, we need to think, where do we want to be on this trade-off curve? And again, this is a curve, this is a trade-off. And the other kind of takeaway that I really find important to emphasize is that we really should not think of machine learning as a hammer, as something that I have a problem, I can just use my machine learning powers to solve it, but really think of machine learning problem as a sharp knife. So something that can be extremely useful if you use it properly, but unfortunately, if you start just slashing and kind of using it in a brute force manner, you are more likely to hurt yourself than actually do anything useful. So in particular, again, correlation extraction is what I call this double-edged sword of ML. It gives us the power, but also this is a root of many of its problems. And also, data is really a critical aspect when you think about adversarial robustness. You really need to understand data to understand why your system might be vulnerable and how to remedy that. And essentially, to properly kind of advance the robustness level of our systems, it really has to be a team effort. On one hand, ML researchers will really need to think more about the real world problems they are trying to solve and where the data is coming from and how it represents the real world. And on the other hand, the domain practitioners have to be more clear, and they have to be a dialogue about clarifying how the data was generated and articulate what the actual objective there is. So, there's a good question to ask, what would it take to incentivize such cooperation? I don't think there is that much of it now, but I think it's really important that it is there. So anyway, that's all I have, and looking forward to the panel.
Thank you, Alex. That was a great talk. We're a little bit over time, so I think we'll switch directly to the panel. So if you have questions for Alex or for any of the other speakers, now would be the time. I will let Xiang and Baharan take over. I will also request all the panelists to maybe switch on their video. And yeah, Xiang, take it away.
Yep, thanks, Samir. Thanks, Alec, for the great talk. So for the interest of time, we'll just start right away with our panel, and I will moderate this panel together with Baharan. So the format, since we have two sort of separate but also very kind of related topics, scaling and debugging of deep learning systems in one panel. So what we're going to do is we're trying to start posting questions that we solicit before to on each topic one by one, take turns, and then we'll kind of encourage some of the speakers to start addressing these questions first, and then we'll kind of go through the whole panel and see if anyone would like to take on or add on to the response. Right, so let's get started. I think Baharan, you please go ahead to fire.
Xiang, do you want to give a one-line brief intro?
Sure. I think I will just first quickly go through the panel members again. So we have Eric Xing and Deepak Agarwal, and I think Arum, are you here? I think Arum is probably not here though.
I'm here.
Oh, great. Good to have you. So we have also Arum. Three of them will, from our first sections on scaling deep learning systems, and then we have a Besmira, Daniel Kang, and Saket Gurukar, and Alex on our second panel regarding evaluation and debugging deep learning systems. So welcome all of you, and excited to talk about interesting questions.
Thanks everybody, and thanks for the. To start with one question on the scalability, I want to in particular start with Eric, and I will ask the same question. So the amount of financial and environmental cost of training this state-of-the-art deep learning models. So it doesn't seem to be there is enough efforts to address this issue. So I wanted to see, what do you think? So why is this the case? And what do you think can be done to kind of encourage people to try to address this? This seems to be a very important issue.
Yeah, thank you for your question. In fact, I did notice that this question, I have been speaking about environmental impacts, cost, and the utility bills of deep learning a couple of times already in my talks. But there is not yet, a wave of enthusiasm or effort, dedicating to reducing the cost of deep learning. I think we see actually even from today's session, right? The technical focus, on scalability itself or on the system aspects are still very sparse. I think it reflects kind of a unfortunate but still very strong dichotomy, of machine learning theory and algorithm study versus machine learning system and deployment industrial study. It looks like people are already picking sides, that some problem belongs to the industry and some problem belongs to the academia. And therefore, the academia should focus on, the academic problem and leaving the tool development and so forth to companies like Google. I got a question from Aaron, for example, saying, Google and other companies seems to be rolling out some tools, right? But I think the lack of kind of engagement and the lack of a risk-taking kind of style, for the academics into the system-oriented deep learning research, and the vice versa, the lack of theory and the rigorous and more kind of thorough study, in the industry into deep learning cost is actually causing what we are right now. We just see that arm race of hardware, people just building bigger and bigger models, but because no one is paying the bill, the company is paying the bill. Therefore, developers and researchers are not sensitive to these issues. I think one approach, of course, is to keep talking about these problems in these venues to raise awareness. But also, I think another thing is really about the democratizing, the tools and also, the ideas, of system machine learning research. That's why I still feel that we shouldn't develop a reliance or maybe even an addiction, to only the methods published by big companies. There should be a wave of democratization that the academic community are actively joining, the study of system machine learning, so that cost issue, environmental issue can be looked into by a wider community. And thirdly, I think there is also an issue in reward and incentives, right? System machine learning research, which focus on efficiency, reducing cost, is a very hard problem. It takes a longer develop cycle. In one of the papers I published recently in NOSDI, which got the best paper award, that work took 3 years, okay, and with 9 authors. Comparing to what we do in NeurIPS and the KDD and the ICML, where we spend 3 months, one student publish a paper, this is not very rewarding, right? So I guess there has to be a culture shift that we reward those long-term and very, very tedious and very, very demanding and code-intensive work appropriately, so that students and the researchers can become more enthusiastic into this direction. I will stop here. There are many things I could discuss, but I guess there could be other questions.
Exactly, these were great points. And because we have people both from system, and also this is an issue that can be addressed from the theoretical side, more algorithmic side. So I wanted to also see like what other people's like in system versus algorithmic. So I think both folks can be kind of try to address this issue. So, and we have, I guess, Deepak, who is working in industry. We have Daniel and we have Arun, like from academia, both from systems and more algorithmic. What do you think? What are your thoughts?
Yeah, thank you for that. So I think in industry, I kind of see more a dichotomy. So like there are some big industry players like Facebook and Google and Pinterest and all, like they are kind of at a different level where they are reaping the benefits of all the investments they have made in industrializing deep learning, making sure the engineering systems are kind of working well with this. But then there is the other half of the industry where the adoption is very low, right? Like I was reading an article in Fortune last year, which kind of said like only 17% of the investments that many companies made in deep learning kind of had an ROI. And so when you have results like that, the executives would then kind of lose faith and stop investing in that. So there is a big gap in the adoption, in my opinions, right now. The big players are already reaping the benefits, but then the broad adoption is kind of not there. And the solutions that are provided by cloud vendors help, but often the problem is not deep learning methods itself. It starts very early on in the journey. For instance, like the data management part of the house is not in order, how to define machine learning objectives, where can machine learning help with a business problem, where it cannot. Those are the biggest impediment. And by the time you have solved all these problems and you reach the deep learning phase, I think you have kind of won 80% of the battle, right? So the first 80% of the battle is where a lot of the industrial players are still not there. And we as practitioners have a lot of work to kind of help on that.
So I second what Deepak just said. In the real world, I've spoken with like 36 enterprise and web firms, data scientists, ML engineers, and so on. 80% of their time and effort is spent on data issues, getting the sources of data in place, getting the features integrated, getting the data prepared and cleaned. By the time they get to the model building part, they are already pretty exhausted. And so they are very happy to even spend 5% of their time on the modeling part. Now, coming to this question about energy and cloud economics and cost, I believe that capitalism will self-correct. Competition will take care of that issue on its own. Organizations that are able to afford usage of these sorts of models will use these models because it pays off in their business value. Like for example, Deepak is at Pinterest, some of these big web companies or middle-sized web companies, they hyper-optimize click-through rate prediction because that's their cash cow. They don't mind using tens of billions, even hundreds of billions of parameters for those applications, but they don't use that for every application. They don't use that for, say, spam detection and reviews or something like that. So Facebook had this very interesting paper at HPCA, which is a computer architecture conference. Everybody should check that out, where they talk about data infrastructure and data center perspective of what hardware they use and what is the refresh rate for the models for Facebook's suite of applications that apply ML. Everything from the newsfeed ranking to friend recommendations to face recognition. There's a whole spectrum. Not all tasks are made equal. Not all tasks have equal amount of data or scale or energy or computation requirements. So you will see that heterogeneous spectrum across the board. Now, coming back to this question about data, it's like structured data still drives 2/3 of the business value in most enterprises. It's not images or text or all these other things that AI people are so hyped about. It's structured data, tabular relational data that drives huge business values for most of these enterprises. And the most popular models there are still tree ensembles, XGBoost and LightGBMs and stuff like that, Random Forest. Deep learning doesn't work that well there. And even these transformers and all these other things are not taking off that much. There is a fundamental kind of heterogeneity in ML land. I think that heterogeneity is pretty interesting to me. There's a fundamental heterogeneity in data models too in the database land. Relational model is not a one size fits all. There's graph data models, there is semi-structured data models, and I think the heterogeneity will remain. So that's sort of my perspective.
Yeah, so one of the things I want to echo with Arun is that I actually do think that a lot of these places are paying costs. So for example, if you have to pay for a server to run inference, you're actually paying that out of your bottom line because you're not getting that for free. So I think I think industry does care a lot about costs, and there is a lot of work, for example, in Google data centers to really reduce these things and optimize operations, use for renewable resources, et cetera. And I think that perhaps academia doesn't see so much of this because they don't care too much about the bottom line, but this is really important to businesses, and there is a lot of work on this. One of the things I'll say about doing research on optimizing systems is that oftentimes you can look at end-to-end how people use deep learning and find ways to optimize those directly. So I'm going to shamelessly plug some of my own work. I've linked to a blog post that describes how to do this for SQL-like queries over large data sets by using sampling methods if you only need, say, a confidence interval around the answer. And there's a whole line of work on this by myself and others in the analytics community. And I think this type of research is really exciting for academics because you don't need to train GPT-3 to do this kind of research. So I'll just leave that as a last thought.
Yeah, so one of the things which we observed in our study was that when we did our computation, the cost computation of all the experiments, it costed us around 375K. So at some point, we are saying that it's important to play with the parameters to understand the true progress, but it's also coming at the cost. So
that's the point I made about the Pareto surfaces, Saket. These ML benchmarks are very rudimentary today. ML perf and all these other things. They focus on training of one model on PyTorch or TensorFlow, and they're really aimed at compilers community or the computer architecture community. They're not aimed at deep learning practitioners. Now, 3 decades ago in the database community, there was this huge fight about benchmarks. David DeWitt and others, they launched this Wisconsin benchmark, which later became the TPC benchmark. The entire database systems community is driven by benchmarks. The TPC benchmarks drove like 2 to 3 decades of innovation in getting the RDBMSs in shape. And that still applies in the cloud setting, like the Yahoo Cloud Serving benchmark. I think for the DL practice and the ML practice community, we need better benchmarks that take into account the whole Pareto surface, not just training one model. You want to put themselves in the shoes of the practitioners. You need to build multiple models, and they need to deploy these models and need to maintain these models. All of these aspects require more holistic benchmarks that are rigorous enough to cover not just accuracy, but also all these other metrics like monetary cost, time, space, energy, and all these other metrics. And I hope the ML systems community comes together to do this sort of more holistic benchmarks. It's not going to be easy because ML is vastly more heterogeneous than database systems. Relational database systems are very clean and logically well-defined. ML, there's like literally hundreds of tasks. So Eric gave this nice overview of unifying some of these paradigms. Imagine doing this for hundreds or even millions of applications of ML. I think every application community where ML is applied needs to start thinking about how do we benchmark these things to rein in these sorts of bloating of costs and resource use.
Yeah, thanks, Arun. I think I totally agree with the discussions about evaluation that can kind of design the evaluation landscapes for what the machine learning and deep learning system should be kind of evaluating debug. So actually that leads to my second questions. I want to start with our panelists from the evaluation and debugging community. So we know it is kind of more and more clear that a leaderboard or a predictive power is not the right thing, or not the sole things to just focus on for evaluating these deep learning systems. So just I wonder what's your guys' thoughts about the main issues with the current mainstream evaluation strategies in the ML and KDD communities, and what would you suggest to try or make a progress next? Let's say, do you think there's any a suite of tests and quantitative metrics and assertions that we should be looking at rather than just looking at a single metrics like F1 score or accuracy? Yeah, so I want to maybe pose this question first to Alec, and then we can go around to different people.
Yeah, so this is a big question. Like, yeah, so one thing for sure, I think all realize by now that accuracy is not the metric to pursue alone. It's useful, but it's definitely not the end of the all. And I think the further realization is that there's no single metric that would work, right? And kind of this is not the most I would say welcome answer, but I think this is the answer I am converging for. That like it is essentially like understanding and evaluating system is a kind of ongoing effort. It cannot be just, okay, I build a system, I evaluated this, and then I ship it. It's kind of something that essentially has to be a routine that is kind of always running in the background as we deploy the system, right? And because again, if you think about it, the big problem, the big problem here is distribution shift, for instance. Yes, like, and again, distribution shift can come in many ways, and it's just like impossible to really envision and model all the possible distribution shifts that you will encounter in the real world. You can try to kind of be proactive and and model some of them, and then you can evaluate the performance of that. That's useful. It kind of leads to better representation. But in the end, it's really the distribution shift will be what it will be, and kind of. So again, this goes back to what I was saying. I think in the end, it's not about building a robust system as a kind of, again, finite quality you can evaluate and you can kind of approve. It's more of thinking about the system you understand, and you understand its failure modes and are able to react quickly when it fails. So anyway, but so these are my thoughts, but I think Besmira might have some interesting thoughts on this as well, because she thinks a lot about such questions.
Thanks, Alex. Yeah, I mean, I think it's very interesting that we're here, from talking from a scalability point of view and the debugging point of view. There's connections to this. I mean, my concern these days is that we need, for every new problem that we find in a model, we need to write a paper about it. And that we need to spend months in finding that problem, works of PhD students and researchers to really pin it down. And then you think back about it, like, why does this happen? Is it because we want more papers? Is it because this is so challenging? And these days I'm converging more to the latter. It is challenging to find one issue with the deep learning model. And you see this in practice in teams that are trying to deploy these models. It is time consuming and overwhelming to look at all the data, to look at all the parameters of the models, to understand what if I use another model, is it going to have the same spurious correlation than the previous one? It takes a lot of time. And a lot of this boils down to the lack of tooling and the lack of, really scaling this type of, practices in industry and in teams that deploy these things in practice. And these things need to be made, less intimidating, in the sense that it's okay for developers to take time and look through the models and understand them better. The other thing is, again, related to the same problems that scalability has, incentives for debugging and finding errors, at least in industry, are not the same as the incentives of shipping a new AI system. In that, it is not a new technology. You basically found a problem with the current technology that we already have. So what is the incentive that you're going to give to somebody that finds that problem and maybe mitigates that problem in the longer term? I think we don't have the right balances there yet. And then there is another, scaling issue when it comes to data, in that, there is a team that takes care of the data management, data collection, and so on. And then there is the model experts. But you need to understand each of this in the context of each other. I mean, it's okay that we have interpretability tools to understand the models, and it's okay that we have data management and visualization tools, but I need to understand the data with respect to the model. What does this data do to impact the model? What types of correlations the data has that actually are transferred back to the model, and then vice versa? Do all these models learn the same correlations? Are some of them that maybe, have certain properties that make them invariant to certain correlations? Because there's a lot of people that are working in the field on, invariance with particular spurious correlations. So there's all these issues about, going back and forth between model and data that are not yet solved, either because of, detachment of communities or because of lack of tools. you cannot look at these things in Jupyter notebooks. You look at 5 images and then another 5 more images. You need the summary of what is there in the data and in the model.
Great points. So I actually have a follow-up question for both scalability and debugging people. And I want to combine it with the question that we have in the chat. So the question in the chat is that, does the 1% more accuracy from a model that costs 25% more in hardware pay for itself? So this is a question in the chat, and I want to combine it with, first, I want to ask from all of you, what do you think about this question? And secondly, I want to ask, like, does all this extra cost that we pay, let's say this 25% to get that 1% improvement, like, if we want to address this, if we want to reduce these costs, so what do you think about, shall we be more careful with the data? Shall we try to, like, connecting to what Bessa said, shall we try to be more careful, like what data points, probably summary of them, or shall we be focusing more on the models, trying to have better algorithms or smaller models? Of course, both are important, but if you want to start from somewhere, what would you think is the most important? So anybody who is volunteer to start.
I think the reducing total cost is obviously the ultimate goal, right? That's both the ultimate goal for the industry and also for the academic. But how to get there is really the open question right now. In many of my components I talked about, including scheduling and the parallelization, tuning, or even composition, one word I use very often is the word of standardization. I think right now, much of the cost, especially in data wrangling and also in model building, is that everybody have their own tricks. And also everybody feel free, introducing new formats and the new kind of conventions and so forth. Somehow, I think the machine learning and deep learning community comes to a time where there should be an effort to start thinking about standardization, just like what IEEE did, for telecommunication and other domains. And then, built on a consensus of formats, workflow, and the interface, and also tasks and goals and even benchmarks. Then you can talk about cost. Otherwise, you are comparing, oranges with apples all the time. It's very hard to really align the community, into a very consistent and coherent direction.
Yeah, so I want to comment on the cost perspective. We just talked about infrastructure and compute cost. That is not the predominant cost, in my opinion, especially in industrial settings. I think developer productivity costs a lot more than infrastructure. Like if you have a team of 200 machine learning people, and again, machine learning people are not cheap, I mean, thankfully, because we all have good job security. You really need to make sure that everyone is productive. So if you have an environment where the tooling is not adequate for machine learning developers to iterate fast and launch new ideas, you are actually paying a lot more than the infrastructure cost that you have. The other cost is reliability. So let's say you have a very complex, sophisticated model you launch in production, but then it breaks 3 times a month. If your system is down for 2 hours because of that, you lose a lot more during those hours than the additional benefit you get. So those cost considerations have to be kept in mind when we are building and deploying these models. Now, coming back to the evaluation, I think out of sample accuracy is definitely, in my opinion, just a sanity check, right? Like the real deal is when you launch these things in production and you do an A/B test, whether it really does what it's supposed to do. And someone mentioned the distribution shift. In many of the applications like recommendations, so distribution shift is natural, right? Because you are generating a model using a different serving algorithm, and suddenly you now change the serving algorithms. Obviously, you're going to get distribution shift, and all the measures that we talk about on out of sample accuracy do not actually apply at all, right? And so this is something that many people in industry struggle with. Like, how do I actually create offline mechanism that can help me replicate what I see online, right? And often that is not even possible. So the fastest way to test your ideas is how do I kind of build a system where I can do some sanity checks and quickly go into the production system and test whether it works or not. And so that's where most of the investment needs to happen, in my opinion, so that we can actually get more out of less.
So one thing I would add to the point Deepak made is, when I teach to my data science majors, so HDSIV, I created this course on systems for scalable analytics. I introduced ML by asking them a quick question about Pareto trade-offs. Exactly the question that was phrased in the chat is like, hey, you know what? Your training cost is 10,000 versus 100,000. Your accuracy goes from 90% to 95%. Which one will you pick? And I asked the students to raise their hand. The class eventually splits 50-50. And then I throw in a third point in between the two. And then people get polarized. And that gets into a debate about what is the value of that accuracy in terms of the business metrics that you care about. If you're an oceanographer studying fish species in the Pacific Ocean, that is very different. It's scientific insights for generalizable knowledge. If you're an advertiser who is posting ads for people to click on, that is very different. You have a monetizable metric there. So it's entirely application specific, and there's a whole slew of spectrums. From an ML system building and tool building standpoint, my philosophy is we shouldn't be taking sides on these sorts of matters. We should be building tools of all kinds for all sorts of users. There is value in doing both. There's value in building systems and tools that help monetize advertisement clicks or whatever, search, face recognition, whatever else that these big tech companies want to do. There's also huge value in domain sciences, applied humanities, and governance and law and all these places, which is nonprofit. And so there's this whole spectrum of applications that we should serve. And the way we teach this in the data science curricula is think of it in terms of the trade-offs that you want to start with. What are your business objectives? What are the spectrum of options you have, and which ones work well? And it is an art. There is an art in there, because the business objectives, ultimately, I mean, business is not science, right? So there is an art in there, and that's part of the training that is required. That's why we have this new profession of data scientists, right? Otherwise, why can't we just have the whole statisticians? Or why don't we just replace data scientists with auto ML engines? After all, everything is automated for the ML tuning component, model building component. Understanding the business metrics, connecting them with the data sources and the importance of the variables and the features and the sources. There is a lot of stuff there that needs to be thought about in terms of a human in the loop fashion.
And like, I also want to hear Alex and Bessa's thoughts on how this like very large models and large data affects debugging and evaluation.
Yeah, so that's a good question. Actually, it's something I am thinking about. You know, like if you think about things like GPT-3 and so on, like how would you really understand? You know, I don't even think. Okay, so it's not too difficult to kind of find bugs in quotes for GPT-3. There's not hard. It's not hard to create the queries that kind of make it, you know, answers fairly nonsensical answers. But of course, you know, I always view the adversarial analysis as a way to really understand the system, right? Like kind of, you know, you just start breaking it to understand kind of what makes it tick. And I was actually thinking about like, okay, so how would I start like play with GPT-3 to really understand kind of, you know, what makes it tick, you know, how it is really built, like what kind of correlation is learning? Is it only correlation? Is it something more? So, you know, this is something I am thinking about. I still don't have a satisfactory answer. Like it seems hard. It's like in particular, you know, one of the important, you know, important primitive that we use in our evaluation is retraining the model with different data, retraining it with, you know, kind of different training routine. And, you know, when you talk about GPT-3, well, you know, maybe we could afford like, well, we can afford to train GPT-3, but not too many times, right? So this is kind of something that I indeed find a challenge. And kind of there, and I think something that the community has to solve. Like even, you know, the big companies like OpenAI who can train, these models routinely, even they have to figure out like, are there scalable ways of testing them and kind of and poking them and, you know, playing with them again, because testing is always much more expensive than just deploying. And currently, like we are pushing ourselves, and we should push ourselves like, what is the biggest model we can kind of deploy? Which is great. Well, that's how we push the boundaries of science. But then like we should think, okay, but wait a minute, how do we actually kind of make it more scalable? Maybe like fine tuning, maybe should be like faster, but kind of can we enable faster fine tuning? Do we understand maybe which part have to be fine tuned, and so on and so on? Ideally, again, this is still the future. I don't know how to get there, but I hope I think we will have to go there. Is thinking more about modularization. Essentially, maybe maybe we should not retrain networks every time, like all the layers of the network, like the initial layers of the network. Maybe there are indeed these edge detectors which can be repurposed. So maybe we should just have one, kind of validated in some way, kind of edge detector that was trained on a very diverse data set with a lot of compute, and then kind of we build on top of that. Now, if you think about it, much of the application of machine learning is based on transfer learning. So in some ways, it's a very weak form of modularity, but it is there. But anyway, I don't have answers, but I do, I do agree this is an extremely important question. Again, not just because you care about security and robustness. I just think this will be necessary to really understand what these models really do and what has to be improved there and what kind of has to be replicated.
Yeah, on large models, I have a little bit of like a grumpy opinion about the fact that everybody is talking about it's a large model. Every model is large. Like I completely agree that hypothesis testing on whether you addressed an issue or you didn't address an issue and retraining is certainly expensive. But when it comes to understanding what the issue is, you always need to do a lot of work to understand what it's doing. So in that sense, I don't think we should create more hype that there is already there when it comes to these large models, because the task is always difficult. But on the other hand, we still need efficient constructs to really, be able to poke them in a meaningful way and to summarize the tests that we build. There is already, some work in the community, especially like in the language domain. Like I'll mention, there's the NLP checklist as a way for creating these types of tests for general language models, and provides a way of thinking in an interactive fashion with certain models. Then you get stuck after you find, it's not difficult, as Alex said, to find bugs. Like you basically, anybody can spend 30 minutes and find many bugs in the systems. It's not a big deal. Then you get stuck into mitigation and how you address them. And many people, in this meeting have worked on, model distillation and like how do you find gradients that are meaningful at the beginning of training, including, Bahar herself. There is many of these techniques that we probably should be investigating as the research community that are not explored enough to see if there are some early signals that can tell us what parts of the model, of the data and of the model are going to be most useful. Modularization is something we go back and forth in AI, in like, do we train end to end or do we train smaller pieces? That is very relevant to the question that was posed earlier. Oh, do I take this 1% accuracy or not? It relates to the whole system. No model lives alone. You need to think this 1% accuracy increase, how is it going to affect the whole system afterwards? And we have many cases where, for example, we have trained an object detector. It was, I don't know, X% accurate. We made it perfect. We had, people annotate the data many times, fake the object detector quality to be perfect, included it in the whole system got worse. Why? Because the language model that came after the object detector was not tuned to work with a perfect object detector. It was, used to have those errors and adjust for the probability scores. So you kind of need to think system-wise to see how the bugs transfer, how are they propagated, and maybe sometimes you create new bugs on the way. So there's all these parts, and I think we have also to learn a lot from the robotics community that is thinking about, the different pieces of machine learning, but also not machine learning, traditional software code that is integrated into the systems to sort of build a practice of how do you think about this, perhaps, larger systems that deal with more complex tasks.
Thanks. So I have a follow-up questions actually for all of the panelists here regarding, I think, reliability and sort of faithfulness of the ML system. So we know that in like software 1.0, because things are more structured, things are more constrained and also more like manually designed. So these softwares often comes with these specifications and these like quality assurance, right? Like you expect this function, this module to do what, and you have ways to do unit testing for things. But if you're looking at the more like a popular kind of a practices right now in our community for KDD and machine learning, data-driven methods basically is sort of dominant kind of the trend. So we have this like a huge neural network with many layers that can be learned, seems to be in a pretty good way on data. So how can we bridge the gap between these two, right? Like, can we actually think about a way that we can write down specifications and quality assurance on parts of the machine learning or neural network systems, and then trying to validate that and trying to test that? Is this even possible, right? I think this will be a question for both our friends in evaluation debugging and also system ML. Whoever want to take first, please go ahead.
Yeah, so I think this is also related to some of the other points that came up earlier, but if you look at regular code, it's often easy to specify exactly what you mean by correctness. That you can sometimes even write down a formal specification and then you can verify against that. And once you have something that's correct, the only thing you really care about is performance. You just push that thing to be faster. So in some sense, it's a very easy problem. One of the complexities with ML systems, especially as they deal with like unstructured data sources, is that you're all of a sudden in a discrete and combinatorial world. So if you look at language, there are discrete objects, for example, words. And once you're in discrete land, in some sense, some problems become easier, but some problems become also much, much harder. And I think that it's almost expected that debugging for ML is going to be much more difficult than, say, debugging for traditional software. And I think as the research community, we should be building tools to make that process much easier for these different domains. And so some of the things that the tools that everyone here has been working on is working towards that. And I'm really excited to see more of that happen.
Thanks. Anyone want to add on?
Yeah, I want to echo what Daniel said. This is not similar to software testing because you're learning from data. Your environment is changing. It's a very non-stationary world. It's more there is more stochasticity in the whole process. So you cannot use just the software. You can learn from those practices. So I think we have to really build this almost like a Six Sigma for machine learning. Like you start from your data. This is your data source. Every day you have to have monitoring on your data just to ensure that the data that is feeding into your model is reliable and it is giving you what is expected. If there is a sudden change in distribution, for instance, that is definitely going to impact your machine learning system. And so someone needs to get an alert and go and fix it. You have to monitor your metrics as things are running online. If there is a deviation in metric, you need to again intervene and kind of correct for it or investigate it just to make sure. There might be an adversarial attack that was not there before. And so that might actually change things. Sometimes, you get highly positive numbers. So you need to be pessimistic about very good news and also very bad news. Like you cannot take very good news with a grain of, you should always take it up with a grain of salt and also investigate it, kind of make sure that it's all right. So building that whole tooling and the processes around that is extremely important in my opinion. The other thing which I found very useful in practice is, yeah, you can run the sophisticated deep learning model, but always have simpler model running in production. Because how do you know deep learning is working well? If it is better than your simpler solution, then only you know that it is working well. So in addition to deep learning, always on some fraction of traffic, have something simple working. And that is always going to help you calibrate whether your systems or your deep learning models are working correctly as anticipated, because simpler methods that are based on more aggregate statistics are more robust than deep learning model that actually go very deep and learn more patterns in data. And any small deviation in the quality of the system might actually throw these models off, but the simpler models can actually be still more robust and can still perform at the same level of accuracy that they have.
Any other thoughts, like people that even have different opinions?
I'll just throw one out there in that, there is a little bit, specification is super difficult in machine learning. Like there's no way you can enumerate all input conditions unless you provide the whole, data set for whatever you'll see in the real world. At the same time, though, it doesn't mean that we shouldn't do it at all. In that there is some intimidation that comes from the fact that you need to be 100% complete in debugging and will never be 100% complete in debugging, but that doesn't mean that we'll end it with a single number on accuracy. There is still some aspects about input that one can describe and characterize whether the model is working well or not for those inputs. There was perhaps a few years ago, we were debugging a face recognition application, and then we were thinking about all possible dimensions on properties, face attributes, fairness, and all these things. And it turned out there were some of those issues, but one of the most fundamental ones was that the model wasn't working well when the face of the person was not visible. So either the head was tilted up or down, so half of the face was not visible in the photo. And it's important to know that. Maybe it's not a fairness issue. Maybe it's something that you will not write like a super interesting paper about, but it's something that exists in the model, and maybe the customer or whoever is going to reuse this model in the future needs to know that if the face is not visible, the model is not going to work well. And so there's all these aspects that can be, retrieved from the data, and more, interesting work that has come out from this community to characterize the input that could be leveraged. And then we will deal with, what comes after to make the specification more complete as a community. So yeah, that's it. I don't think we should be, super intimidated by this. One needs to, find these inputs and try their best.
So following up on what Besmira said, I think there is this connection between debuggability and explainability and interpretability, and also system efficiency. So one of the papers I didn't talk about, I just linked there, is Krypton. We showed that some of the common explainability mechanisms on image data, such as occlusions and stuff, that was what we saw was popular among radiologists. There's a lot of system inefficiencies, and that makes it slow and it's hindering their adoption. And so I think systems builders can focus on not just the large scale training part, but also model inference, deployment, and extraction of feature importance or signals that are actually important in the prediction. These sorts of testing also leads to a lot of computations. And I think there is some interesting work in the ML inference space where systems techniques can also help accelerate these sorts of processes. Of course, the faster things are, the more people want to use them and the more they want to use them for. So hopefully there is a kind of a productive, kind of a virtuous loop there to help debuggability and explainability techniques and also system efficiency.
Thank you so much, everybody. This was a great discussion. And I think this is a very important discussion. It needs a lot of more thinking and talking. I thank all our speakers and panelists that we had in the morning session. So we will come back at 1 p.m. PST, and we will continue with fairness and transparency and also deep learning theory in the afternoon. So thank you again, all the speakers and all the audience, and we will see you soon.
Thank you.
Thank
Thank
you.
you. Bye.
Yeah, bye.
So welcome back, everyone. We're going to be doing the fairness, transparency, and ethical implications of using deep learning session now. A lot of the talks, this is one of the themes that's, I suppose, very popular and gaining a lot of attention last couple of years. But still, there are a lot of fundamental questions that remain unsolved, fundamental issues in how research is taking place in this area that are worth questioning. And in order to do that, we have an exciting set of speakers who are going to be talking about different aspects of trustworthiness, transparency, fairness, things like that. And to kick us off, we have James Zhu, who's an assistant professor at Stanford, who's going to present some work he's been doing. I followed James' work last couple of years. It's been really amazing to see both from a statistical rigor style of side of things, but also very application motivated and application oriented on health stuff. And that intersection has been amazing to follow. So yeah, we're really excited to have James Zhu as our first invited speaker of the session. James, take it away.
Great. Thank you very much for the introduction and for organizing the workshop. It's been really exciting to see this community. Yeah, so I'm excited to discuss today sort of a data-centric perspective on trustworthy AI. So I'll define in a couple of slides what I mean by data-centric perspective. But I want to just first maybe whet your appetite and motivate this problem by telling you about sort of a mystery that we had to solve recently. So the start of this mystery is that there's been a ton of interest in actually building commercial AI algorithms to diagnose skin cancer from photos, right? So it's a very natural application of AI because here the patient data is actually relatively easy to collect, right? So it's just photos. You can take the photos from your phone and then submit those photos to the algorithm. And for example, Google has recently announced that they actually released a product to do exactly this, right? And that's attracted a lot of publicity. And there's been also several other algorithms that are already commercially available on the market where people can, that's solving similar problems. Right? And typically how these algorithms work is that you take a photo of your skin, right? Let's say if you have something you're not sure about, you take a photo, you upload that photo into the algorithm. And the algorithm in this case actually makes a diagnosis in real time that, oh, this actually looks like a melanoma, which is kind of skin cancer. So this is actually a pretty serious diagnosis, and it recommends that you should go visit your dermatologist as soon as possible, right? So these algorithms could be very useful when they're deployed, right? So these kinds of algorithms, they all report very high performance, right? For example, for this particular algorithm, ModelDerm reported performance of the 0.93 AUC in classifying different kinds of skin cancers, malignancies. But it's really not clear to us how they were actually evaluated, right? So we want to take a deeper dive into this because these algorithms, even though they are getting a lot of attention, none of them have actually been approved by the FDA, right? So I had a terrific postdoc, Roxana, right, and Roxana has a secret weapon in that in addition to being a great AI researcher, Roxana is actually a practicing dermatologist. So she's an MD, so she has her own dermatology clinic every week. So with Roxana, we collected a new data set to sort of benchmark and evaluate these algorithms, right? So we call this the Stanford Diverse Skin Data Set. So Roxana collected data from diverse populations, and they also have very clean annotations, medical annotations of each image based on biopsy samples. Okay, so this is sort of an independent external data set. And then we simply just took these algorithms that are very widely used, right, and then applied them off the shelf, right, to our own external data sets. Right? And we were actually very surprised to see just how much the algorithm's performance dropped off, right, from 0.93 in AUC to 0.6 when applied to the Stanford data. Okay, and just to be clear, we didn't do anything adversarial here, right? So the data that we collected, it all came from natural images from real patients, right? So there's no adversarial perturbation. So the mystery is, what actually happened, right? Why did these very popular algorithms, many of them are actually used on real patients, the performance actually drop off so much when they applied to this new test data set? Okay. So we spent a bunch of time over the last few months really trying to dig into this, right, to understand, okay, so what's contributing to this drop off? And we identified sort of three main factors that we think can explain most of the drop-off in the model's performance. And the first factor is basically label mistakes, right? So it turned out that the way that these algorithms were previously validated is by comparing their predictions to dermatologist diagnosis from dermatologist visual inspections. Right? So that can actually be quite problematic because even if you have experienced dermatologists, visual inspections can be quite noisy, right? It's hard to make diagnosis just by looking at the skin. So the gold standard in dermatology is actually by doing biopsy, which is more expensive, right? And turned out, what we had in our data sets is actually labels from doing biopsy, which is the gold standard, but the previous data was just using these visual annotations. So the suggestion here is that basically the models that many of these commercial models, they were trained on sort of quite noisy annotated data. And when you apply them to the gold standard, the performance can drop off quite a bit. And we estimated that these label mistakes were responsible for about half of the drop off in the performance. So the second big factor is actually data shift, right? So many of these algorithms were previously trained on common diseases because that's where it's easiest to collect large data sets. Whereas the data that we have both common diseases and also some rare diseases, right? And the model did worse because of this change in data distribution. The third factor, which is also very important, is that the models were actually substantially worse when you use them on darker skins. Right? And the reason for this is that there were actually very few dark skin samples in the original training data set or in the original validation or test data sets. Right? And in particular, when we apply this model on our data, so our data actually had about half dark skin and half light skin, right? The sensitivity of the diagnosis was really much worse on the dark skin patients, right? So the sensitivity for these models is about 0.4 on the lighter skin images, which is not great, but it really dropped off to 0.1 for the darker skin images. And this can be really problematic in practice, right? Because if you have low sensitivity, that means that your models is missing a lot of diagnosis of potentially harmful conditions, right? If patients are not diagnosed with those conditions, then they can really turn into more malignant cancer types, right? So by having a low sensitivity on darker skin images, this is really a very troubling disparity in the model's performance. Okay, so the reason why I thought this is sort of an interesting example is by going through all of these examples and looking at what factors contribute to the model's mistakes. I guess the takeaway lesson for us from this exercise was that many of the standard machine learning metrics like AUCs are really not very meaningful unless we really understand how is the training and the test data, right, used to compute those metrics, how do they relate to the new applications that we're interested in. And the corollary of this is that if we really want to build machine learning models and deploy these models that can be trustworthy and fair, right, then that really requires having a deeper understanding of the training and the test data. Okay, and this, I think, actually motivates sort of a changing perspective in how we think about machine learning research. Right. Over the last few years, I would say most of the machine learning research in the community has been very focused on developing new models or ways to interpret these new models. And that's for very good reasons, right? There's a lot of exciting innovations on new model architectures like transformers. And most of these models are trained on a relatively small number of clean benchmark data sets like ImageNet. Right. So the focus has very much been on the model R&D rather than on the data. As we're thinking about going beyond research and thinking more about deployment, right, I think in the coming few years, there has to be sort of changes in how we think about this problem, right? Especially when the models become more mature, right? So I think the biggest challenge towards reliable deployment of these models will often be on the real world data, right? Because the data will end up being very messy, oftentimes very expensive. They have all of the biases that we saw in the skin cancer example I showed before. Right. And we really need to understand how these kinds of messy data interact with the model if we really want to have reliable and trustworthy deployment. Right. So that sort of motivates this, this data-centric perspective that I'm very excited about towards trustworthy AI. Right. So this is still a relatively new research agenda. So there's a lot of open questions to be solved here. Right. So I will, in particular for this talk, I'll talk about sort of 3 challenges under this data-centric view that I think are particularly exciting, centered around how do we characterize different data sets used to train these models, think about how do we quantify how different types of data contribute to the model's mistakes and biases, and also thinking about how do we really leverage more of human in the loop AI kinds of data. Right, so I view these as really 3 challenges, right? So I'll tell you about some of the initial steps that we've recently taken, and also tell you about some of what I think are interesting open problems. So especially for the students in the audience, I think this is a great area to work on because there's a lot of new questions. Okay, so the first challenge I want to discuss is how do we systematically characterize data sets that are used to train and to test machine learning AI algorithms. So there hasn't really been too much systematic surveys of machine learning data sets that are used in applications, right? So I think just to develop a best practice for doing this could be a really nice contribution and still very much an open area of research. So I'll give you a couple of examples how we try to think about this problem. So going back to the dermatology setting, right, with Roxana, we actually did a systematic survey of what are all the data that's used to train these AI dermatology projects. Right, so this is sort of a summary of visualization of that. So each square here corresponds to one of the papers on AI applications in dermatology. Right, so the numbers here, you don't have to worry about those. They're basically like the paper IDs. There's about 100 or so of these papers. And the circles here are basically the data sets, right? So a red circle means that it's a private data set. So that means that only the authors of the paper had access to that data, so nobody else can actually access the data. And the blue or green data sets are the public data sets, are the benchmarks that everyone can use. Okay, so here basically we just visualize which papers actually end up using which data sets. The size of the circle just indicates how many images, how big is the data set. So one thing that's actually quite striking is just a large number of these algorithms are really developed using only private data sets, right? So those algorithms are especially hard to audit or to validate because nobody have access to the data, and there's very little information about what data is went into it. All right, and there's a couple of very large benchmark data sets that ends up being used in many of these algorithms. Okay, so in our survey that we found here is that we found that only about 10% of these AI dermatology papers actually reported any skin color information, right? And a substantial number of these papers did not use biopsy labels, which means that their annotations or validations could have these kind of very noisy effects that we saw before. Okay, so the previous example here focused on surveying the training data. In many cases, it's just as important to carefully characterize the test data. Right, so in this other project that's led by Kevin, who's a graduate student in the group, we surveyed all of the algorithms that were medical AI algorithms that were approved by the FDA. Right, so each box here corresponds to one of the FDA approved algorithms. Right, so these algorithms are already approved to be used on patients. We stratify the algorithm by which part of the body they apply to. So maybe the most important thing here to note is just the color, right? So the algorithm is colored blue if that algorithm has been tested across multiple sites or reports multiple site validation before they were approved for use by FDA. So here it shows that actually a substantial number of the algorithms, so 93 out of the 130, did not really report multi-site evaluation. So this means that actually a large number of the algorithms were only tested and validated on data from one location, and typically on average about 300 patients from one location. So I think this also reveals quite a lot of limitations in the data that's used to test these AI algorithms, right? Because there could be quite a large variability on the test performance, depends on which location you tested on, right? So just to give an example of this, we took a specific application of detecting pneumothorax, which is collapse of the lung. So we took algorithms that were trained at on data from 3 different locations, Stanford and Boston at NIH, and we tested how well did the algorithm work on data on patients from other locations. So that gives you this 3x3 matrix. So diagonal elements corresponds to if I evaluate the algorithm on new patients from the same location where the algorithm was trained. So you can see quite a large number of variabilities, right? So for example, if I take the algorithm that's trained on the NIH data and I test it on new NIH patients, it does quite well. But when I take that exact same algorithm, I apply it to patients from Boston, then there's a large drop-off in performance. And again, here, there's really no adversarial attacks here. It's just really due to many of the factors that I mentioned that we saw was the dermatology example. So I think really one of the open challenge for the community, right, is we really need to have much better ways to systematically quantify the data that's used to train, to validate all of these different algorithms. Here, I'm showing you a few examples from the healthcare settings. I think it's just important to do this in NLP, in finance, in many of the other applications where AI are being deployed. So that's, I think, one interesting challenge. In many cases, it's not enough to know just what data is used. Right? We also need to understand more precisely how different data contribute to the model's mistakes or to model's success. Right? So if we think about this entire machine learning pipeline, right, you have the training data, which in this example, in this cartoon, I have shown you examples of sort of 3 training data points. You think of them as sort of 3 patients or 3 hospitals, right? you have your favorite learning algorithm, which could be your favorite neural network, and you have some performance metric that you really care about, right? That could be accuracy or MSE or F1 score. So what ideally we want to have is that if your model achieves some performance, maybe 80% accuracy, we would like to understand very precisely like how much did each of my data point or each source of my data contribute to this 80% accuracy. Right? So that means that, taking that 0.8 and being able to ideally partition that 0.8 among each of my sources of data. Right? And similarly, if my model suffers some mistakes or exhibits some certain biases, I would also ideally like to understand how does each of my training data contribute to those mistakes or to biases, right? If I can do this, then I really have a fine-grained way to say which data is responsible or accountable for which behavior of the model. Okay, so how do we think about quantifying and doing this, right? So for example, right, how do I think about quantifying the value of this point, this star point here? Right, so this is the problem of data evaluation that my student Amir Atta spent a lot of time tackling. So one common approach to thinking about this problem is basically compute some sort of leave one out score. So that's very intuitive. So what you do here is that you have a model that's trained, right, on all of my data, right? So the color here corresponds to the decision boundary of the model, right? And what we can do is I can remove this point star, and I can see how much does that change my model's behavior if I didn't have this point star in my training set. Right? Maybe that changes the decision boundary and that changes the metric of the model, right? So that could be one way to assess the importance, the contribution of this point star. So even though that sounds quite nice conceptually, it ends up being very difficult to do in practice, because the reason is that if I have a large number of data points, right, these kind of leave one out scores ends up being extremely noisy. Right? So what Amir Atta does proposes to, instead of doing this leave one out once, let's actually do it a bunch of different times. So the idea here is that we actually create a bunch of different scenarios, right? So each scenario corresponds to one of the columns here, and each scenario has a different random subset of my training data, right? And I would like to understand, right, for each scenario, how much does removing or adding this point star change the model's performance, change the model's behavior under that scenario. Right, so what I do is that for each subset of my data corresponds to that scenario, I can train the model with the point star and without, and I can see how the model's performance change, right, through this leave one out calculation. And then if I have a bunch of different random scenarios, right, then I have a bunch of different scores. And there's a unique way to aggregate all of these scores together by taking a weighted average. That's what we're calling the data Shapley score. Right, so the exact formula is here, but it's basically implementing mathematically exactly what I described intuitively on the previous slide. So sort of like a weighted average across the contribution of each data point, right, across these different scenarios. Okay. So I want to give you a couple of examples of how we can actually use this kind of data evaluation schemes to help us improve the transparency and reduce the bias of these algorithms. So again, going back to our running example of the dermatology, right? So the data that's used to train these AI dermatology algorithms oftentimes are quite noisy because people will just go to Google image and scrape them from the website. So here are actually some examples of data images that people use to train these algorithms. Right, and perhaps it's not too surprising that when you take these algorithms, you apply them in the clinical settings on real patient data, the performance accuracy can drop quite a bit. So what data Shapley score does is that it provides actually a numerical score, a scalar for each of my training image. Right, this basically quantifies how much did that image contribute to the model's performance, in this case on the clinical patients. Right, so some images will have negative score, so that means that that particular image actually introduced biases or introduced mistakes in the model's performance. And other images will have positive scores indicating that that image is informative and it helped the models to make better predictions on the patients. Right. So here I'm just showing you some random subsets of images that have high Shapley scores. You can see that these ends up being images, data in my training set that are cleaner and also are more informative. And a very simple algorithm, right? Once we have these scores, a very simple approach is we can weight each of my training point by their data Shapley score, and then just retrain my original algorithm on this weighted data set. Right? So it's the exact same algorithm. The only difference is that I just have now have a weighted data set by their Shapley scores instead of the previous unweighted data. Right, so this is sort of a simple approach, but the intuition here is that it encourages the algorithm to give more weight, to pay more attention to data points that we know are more informative and also are cleaner because they have high Shapley scores. So even this very simple idea of just weight the training data by a Shapley value actually substantially improve the model's performance in deployment, right? In this case, by over 11%. So I think similar ideas can also be used to improve the fairness of these models. Right, an example of this is that there's been a lot of important work recently thinking about biases in facial recognition algorithms. Right, and one type of bias is that these algorithms, because they're often trained on data sets that have more white males, right? When you apply the algorithm in deployment where it sees more diverse individuals, the algorithm's performance can be quite poor, especially for minorities, right? So there's a disparity in the algorithm's performance for these facial recognition systems. So what the Shapley score does is also computes a number, a score for each of my training image, right? That says how much that image contribute to the model's deployment. And here again, we can use sort of similar ideas as before, right? Where I simply weight my training data by their Shapley score, right? So that encourages the model to pay more attention to the more diverse data points that ends up having high Shapley scores. And that by itself actually, just training the same model, that weighted data by itself actually led to quite substantial improvements in the model's performance. And also reduces the disparity, right? It doesn't remove them entirely, but I think it does reduce some of the biases. Right, so here we think of this data evaluation as sort of a way to attribute, right, the responsibility of the model to individual data points. There are several open challenges, right? So one big challenge is that I think computing these Shapley scores is still quite expensive. We've been making some recent advances using adaptive sampling and also analytic approximations to speed things up. I think by and large, that's still an open problem. Another big challenge for people coming from more for a stats background is that these data Shapley scores doesn't really have a natural way to account for randomness or noise in the data, right? So recently we've been exploring these ideas around sort of statistical Shapley scores, right? And I think there's also a lot of interesting directions, open questions in that direction. So the last challenge I want to discuss with you in the last few minutes is really thinking about how do we try to leverage and collect more human in the loop AI kind of data. Right, so why do we want to do this, right? And again, I think one of the running threads of this presentation is that oftentimes the machine learning algorithm that we have here are optimizing for the wrong objective, right? So if we think about the standard machine learning workflow, right, typically we get feedback from domain experts, but only from relatively limited feedback initially in the data collection and data labeling. Once you have the data, then the machine learning researcher or developer takes over, you train their data on a train validation split. And most of the efforts is really on optimizing the model's performance on this validation data set, right? But what we actually care about is how well does the model work in deployment, in the real world usage, right? Whether the model reliable and fair once used on the real world settings. So what we actually want to do, right, is ideally, instead of validating the model on the static validation set, we want to validate and optimize the model on the real world usage that we care about. And this requires actually collecting real-time feedback from at least some of the pilot users and from our collaborators. Okay. So now there are many engineering challenges with collecting real-time user feedback, right? Once you have the model, you still need to figure out a way to containerize and deploy the model. You need to have some databases for storing samples. You also need to build these web interfaces, right? So they all require different tools, different platforms, and different programming languages. So there's a lot of overhead if you really want to build real-time deployment of your model quickly. So to address these challenges, my student Abu Bakr actually developed this Gradio platform, which is the open source Python framework that takes care of all of these technical challenges of deploying and getting feedback on your machine learning model. So it makes it extremely easy for ML developers to get real-time feedback, right? So here's how it works. I mean, so Gradio can take almost any machine learning model and creates an interactive user interface just in about 3 lines of Python, right? So here's an example. You just import Gradio, right? If you have a particular model you want to deploy, you can just insert that into the Gradio interface. And you tell the interface what kinds of interactivity do you want to have with your users, right? In this case, we say we want to have the user to put an input, which is an image, and we want the model to produce an output, which is some labels. Right, so here I'm talking about, as an example, the dermatology classification. And then you can just simply launch Gradio, right? And Gradio will just provide for you, generates an URL, which is a public URL, and that can be shared with your collaborators and with potential pilot users. Right, so here's an example of the URL. And anyone with this URL can open, right, the model on their browser without any software or any download. And once they open it, they can immediately interact with the model. Right, so here's basically how it's looking like, right? So in this particular case, right, so once they open the URL, they see this interface, right? They can put in their own images. They can modify the image by changing its brightness, right? And then they can see how does the model's behaviors change by using different lightings on these images, right? And if they see mistakes, then they can flag these mistakes. And those all become real-time feedback to the machine learning developers. Okay, so the idea of this is that it makes it very easy to collect mistakes or feedback, right, from the models, not at the end, but during all the way through the development stage of these models, right? And this data can be used to understand weaknesses and hopefully also to retrain the model. So this Gradio platform, we're actually using this right now at Stanford as a part of our first real-time AI trials. We're actually testing this in dermatology clinics. Right? And it's also being used now by over 10,000 machine learning researchers and developers from universities, also from larger, smaller companies, including Google and Amazon. And it's integrated into other interfaces like Hugging Face and PyTorch. So just to summarize, I think these three challenges I outlined about data-centric AI, trustworthy AI, they really go together hand in hand, right? So the idea here is that first, we want to characterize what data is currently being used to train to test the machine learning models. And in parallel, we want to augment this data by generating additional data, right, from user studies, right, that better reflect the actual deployment scenarios of these models. And once we have these different types of data, we can use platforms, algorithms like data Shapley scores to quantify how these different types of data all contribute to the model's mistakes or to the model's success. Great. Yeah, so I mentioned a bunch of papers and resources. So we actually made all of the papers and code and our data sets publicly available. So yeah, if you have any questions, please feel free to check out these papers and follow up with me. I'm happy to follow up. I also want to thank again the great students who led these works, Roxana, Eric, Emirata, and Abu Bakr. So thank you.
Thanks, James. That was a great conversation. I think we're running a little bit over on time, and I don't see any questions in the chat. I guess so. Maybe I'll ask one slightly general question. So for both data Shapley stuff and when you look at the saliency of these images, there is a lot of interpretation that the human has to do in terms of what's going on when they look at this interpretability. So what are your thoughts have you seen in your experience sometimes humans projecting a stronger behavior than is actually happening, or misunderstanding what the explanations are actually trying to convey? What does the importance actually mean? Things like that.
Yeah, that's a good question. So that's actually where we found having these interactive user feedbacks ends up being quite useful, right? Because if you're just looking at a static interpretation and static example, it's often it's often easier for their imaginations to run wild and for all sorts of, for example, confirmation bias and things to come in. So what we often do is to actually give them basically this Gradio interface along with the data and the interpretations. And it ends up being very useful for example, for clinicians to modify the image, right? Because they often have pretty strong priors about what are the kind of modifications that are or are not important. For example, lighting should not be important, right? But if I change some of other things like the size of the moles, then that are important, right? So they will actually make these physical modifications And then they want to see in real time, how well did the model's interpretation and prediction change, right? So that actually interaction ends up being, I think, the most useful kinds of data that we are able to collect.
Okay, yeah. Yeah, thanks a lot, James. You'll be around for the panel, so I'm sure
Yes.
people will have lots of questions at that point. Yeah. All right. Harmanpreet, can you share your screen?
Yeah.
So our next speaker is Harmanpreet Kaur. This is a contributed talk. She's a PhD candidate at the University of Michigan, and she's been working on human AI collaboration and interpretable ML. Her work has been more sort of on the HCI side of things. She's won Best Paper, honorable mention awards at CHI and IUI. And so really looking forward to hearing that perspective on interpretability and machine learning. So yeah, Harmanpreet, take it away.
All right. Can you see my screen? Everything okay?
Yeah, everything was great.
All right. Thank you for that introduction, Samir. Hi, everyone. I'm Herman. Today, I'm going to talk to you about some of the work that I did with my collaborators at Microsoft Research. Our goal was to observe and evaluate the use of interpretability tools in a realistic context for data scientists. So let me begin with explaining our motivation for this work. With the use of machine learning in all kinds of domains, it's important that people who are responsible for building and deploying these models are able to adequately understand them. Researchers have built interpretability tools to support people's understanding, and these tools generally take one of the following approaches. They're either post hoc explanations for black box models or inherently interpretable glass box models. So LIME and CHAP are two common tools that rely on post hoc approaches, and generalized additive models are a common class of glass box models. These techniques have been developed largely as a part of ML research in this space, but even though interpretability is a solution proposed for helping stakeholders, these tools have yet to be evaluated in that context. So our goal was to do this people-centric evaluation with a key stakeholder, which is data scientists. Our research questions were, how do data scientists perceive and use interpretability tools? And what are the key challenges towards their use of these tools? Before I dive into the specifics of how we answered these research questions, I just want to take a moment to emphasize why studying the use of interpretability tools in context is challenging. The research team must have expertise in both ML and HCI. We relied on the ML experts on our team to ensure that we accurately interpreted the underlying math for any models we were using, and on the HCI experts to design studies that could answer the right questions about their use. Another related challenge is that these studies must simulate realistic settings, but not be too cumbersome for participants to complete. So for example, in our study, we limited it to an hour at most. It is not only necessary to have knowledge of academic literature and prior work in this space, but also an understanding of day-to-day engineering practices. The data scientists on our research team helped us with the latter. And finally, these studies rely on both qualitative and quantitative methods. Qualitative methods helped us understand the nuances of how the tools were being used, and quantitative methods helped us scale up these findings. So our study design had three components. We first conducted pilot interviews to identify common issues faced by data scientists in their machine learning pipeline. These were followed by contextual inquiries to study the use of these interpretability tools in a realistic context. And finally, we conducted a large-scale survey to scale up and quantify our main findings. So we conducted our pilot interviews with 6 data scientists and asked them questions about their day-to-day work. Things like, are there any checks that you perform at different stages of your machine learning pipeline? Or what makes you feel confident about deploying a model? We also asked our participants to think back to a recent model building experience and answer our questions with that experience in mind. Based on a thematic analysis of this data, we uncovered 6 common challenges. One common problem is when some column in the dataset is missing values for a subset of the data. How the model developer handles these missing values, for example, by imputing them with the mean, can change the output in significant ways. Another common issue is when duplicate data is masked as unique because of some user-based identifier being attached to it. Next, we wanted to observe data scientists' use of interpretability tools in a realistic context. So we took the 6 themes of errors identified in our pilot interviews and synthetically added them in the adult income dataset. This dataset relies on demographic features like age, marital status, race, gender, occupation to predict whether someone makes less than 50K or greater than 50K income. And it was collected in 1994, hence that number. So to show you an example of what these errors looked like in the tool outputs, here for the age chart, we imputed 10% of age values with the mean age in the cases where the output was greater than 50K income. And as a result, you can see that weird spike in chat value around the mean age of 38. To synthesize ad hoc categorization, we decided to convert the continuous variable that represented hours worked per week into a categorical one based on arbitrary 30-hour intervals. We conducted our contextual inquiries for both kinds of interpretability solutions. We used SHAP for post-hoc approaches and GAMS as our glass box models. The inquiry included a pre-study questionnaire where we asked people about their background in ML and any prior experiences with interpretability tools. This was followed by the main study where we asked people to answer questions about the adult income dataset and the model with the help of an interpretability tool. And then we ended the study with another set of questions about how people's experience was with the interpretability tool that they had used, and if they could see using the tool in their day-to-day work. We used Jupyter notebooks to simulate a realistic context for data scientists. As you can see here, participants were first introduced to the dataset, followed by the model, then the interpretability tool, and finally, they were asked to answer questions about the data and the model within the same Jupyter notebook. So let's look at some of the core themes that resulted from our contextual inquiry. The most prominent theme was that there's a lot of misuse and disuse when it comes to interpretability tools. So participant 9 was confused about why age 38 had the highest positive influence on income, but since the plot showed it, they figured it made sense. So this is a case of misuse, which is over-trusting a tool, and as a result, using it beyond its capabilities. Participant 4, on the other hand, was skeptical about the tool because it assigns a quantity that is important to know, but it's showing that in a way that makes you misinterpret that value. This is a case of disuse, where something caused the participant to become suspicious early on, and as a result, they underused the tool. Neither case is ideal. Underusing a tool might seem better than overusing it, but that's not what we want in the end. Another prominent theme was that prior experience is an important factor. So the code on the left that represents misuse was from a data scientist who had recently started their job. And the one on the right was from a machine learning practitioner who actively used ML in their day-to-day work and had done so for several years. We also found that social context is important in this setting. So people attributed trust to the tools because they were publicly available, or because the tools showed visualizations of ML models, which is a novel thing, and that led people to believe that it was transparent and to trust it more. We also noted some usability issues. Some of the values were unclear because access labels weren't descriptive enough. So even though we did provide this information in a tutorial, people did not internalize it or refer back to the tutorial at all. Sometimes the plot visuals were simply too hard to interpret. Participant 4's frustration with the SHAP course plot is pretty evident in their code here. After the contextual inquiry to quantify our findings and see if they held up at a large scale, we conducted a survey where a similar setup was followed as our contextual inquiry. So the pre-study questionnaire and the main study questions largely remained the same, but simulating the setup for each participant using a Jupyter notebook would have been infeasible at this scale. So we converted these questions into a Qualtrics survey. And then given our contextual inquiry results, we wanted to get more insight into people's perceptions of interpretability tools. So we added some questions related to people's willingness to deploy the underlying model and their mental models of the interpretability tools they were using. And this was in a post-study questionnaire. We conducted the survey using both SHAP and GAMS again, but we also added a new condition, normal versus manipulated visualizations. The visualizations in the manipulated condition simply randomize the order of features presented in the global and local explanation charts. So as you can see here, as a result, something that had a high feature importance in the normal visualization appears to have a low feature importance in the manipulated one, and vice versa. We added this condition to control for the novelty or existence of a visualization and test if people were actually paying attention to the content of the explanations. We pre-registered the following measures, and next I'll go over the ones that we saw significant differences for. So participants in the GAM conditions had a significantly higher accuracy of answers than those in the SHAP conditions. Participants in the GAM conditions also had a significantly higher self-reported confidence score in having understood the explanations. Participants seeing the normal visualizations were more confident that the underlying model was reasonable. And we were really glad to see this result because it meant that people noticed the differences between visualizations and weren't just trusting them because they existed. Interestingly, we also found that people were less confident about the underlying model being reasonable when using GAMs with manipulated visualizations than when using SHAP. So it seemed to be the case that the GAM visualizations made it easier to identify the weird order of feature importances. Finally, participants using GAMs also had a lower cognitive load value. Unfortunately, we did not see any significant difference for the deployment scores, and the average deployment score was high across all conditions. So people had recognized the issues with the underlying model for the manipulated visualizations, but they still gave the model high deployment scores. We analyzed the qualitative data to figure out what the core reasons were for this model deployment. So it turns out that people relied on intuition a lot from their past experiences in making decisions about deployment. They also evaluated explanations in a very superficial way. So for example, this participant provided no reason for why they thought the charts were comprehensive or what information they were using to make an effective judgment about deployment. There were a small number of participants that gave the model low deployment scores, and these people were rightly suspicious because of the synthetic issues we had introduced in the dataset. So far, our results from the survey were a bit of a mixed bag. Some findings from the contextual inquiry were confirmed, and we were really happy to see that people noticed the manipulated visuals, but their willingness to deploy, even with this doubt, was concerning, and we wanted to dig deeper into this decision. We conducted exploratory qualitative and quantitative analyses on the data about mental models, which we had asked about in our post-study questionnaire. So when we coded their answers for accuracy, we found that less than 4% of our 197 participants, which were all data scientists, could accurately describe the score axis of the visualizations. Participants also generally overestimated the capabilities of interpretability tools. The chart below shows people's answers to a multiple answer question about what they thought the interpretability tool that they were using could help them achieve. Only the things in boxes are actual capabilities of these tools, but people attributed a lot more to them. And some of these capabilities, like automated detection of fairness issues, are far from being the features of any of these tools. We also found that cognitive and social factors can lead to conflicting outcomes. So when we look at accuracy of answers, both cognitive and social factors are in agreement. Higher values for prior experience and higher confidence in understanding visualizations both lead to higher accuracy scores. But when we look at deployment rating, these relationships don't match. And it's important to remember that these cognitive and social factors are shaped by different contexts. So while cognitive factors might be based on objective measures like prior experience counted in years, social factors are dependent on self-reports, which can be influenced by things like the publicly available nature of these interpretability tools. We think a potential solution for this conflict is guiding data scientists so that they're able to form more accurate mental models of interpretability tools. There were participants in our study who had very little experience with ML, and yet they were able to provide more accurate answers and assessments of model deployment. These were people who had more accurate mental models. And on the flip side, we also saw participants with prior experience in machine learning make incorrect assumptions and provide inaccurate assessment of the underlying model's readiness for deployment. So exploring ways for helping people form accurate mental models could potentially help improve their decision-making in these settings. Here are some of our key takeaways. Studies on data scientists' use of interpretability tools show that they're often misused or disused by this key stakeholder. Results from a large-scale survey confirm this. Designing solutions that are interactive and engage people in deliberative reasoning can help them form accurate mental models and overcome the challenges identified here. Bringing together experts from HCI and machine learning researchers and practitioners, to design solutions that consider both human and ML-centric perspectives is crucial for designing interpretability solutions. Thank you. I'm happy to take any questions at this time.
Thanks, Harmanpreet. Does anybody in the audience have questions? We're actually running a little bit late again. One quick question, I guess, going back to the question I asked James was, so his answer to some of the concerns you're bringing up was to have interactive explanations. To what extent do you think it'll address, is that the missing piece? And are there some of these issues that you bring up that you feel like interactivity may not quite solve the problem?
I think interactivity is a great place to start. What we really noticed was that when people see an interpretability tool, and this includes data scientists, their immediate reaction is, okay, this visual will tell me everything I need to know automatically, right? So that I don't need to pay attention to it. So even with interactivity, if the interactivity is of the kind that, okay, I can go from chart 1 to chart 2, change this thing, and the chart changes, I don't know if that's enough. I think what we really need is a way to make people engage with the chart itself or any visual. So one way that we've been exploring in our research is making people skeptical. So if you can engage people in a deliberative reasoning process, which often happens when they're skeptical about something, then you can make sure that they're actually paying attention to what you're showing them. But there's a lot to be done. That's basically it.
And then interactivity, of course, is the one way to do that engagement. Yeah, okay,
yes.
Cool. Thank you. David, can you go ahead and share your screen?
Yes.
So our next speaker is, this is also a contributor talk. The speaker is David Madras, who's a PhD student in the machine learning group at University of Toronto and Vector Institute. We're going to be sort of switching topics and thinking a little bit about fairness now. And he's been working on sort of, looking at these automated decision systems and evaluating them, and some of the stuff will intersect with fairness that we'll hear about today. So go ahead, David.
Great. Thanks so much for having me, for inviting me to speak today. Today I'm going to keep it pretty high.
You got cut out. I can't quite hear you.
Oh, do you hear me now?
Yeah.
Okay, sorry. Yeah, I'm going to keep it pretty high level and try to speak about some of the motivations and high-level ideas behind different approaches to learning fair representations. One of my favorite ways to unpack a phrase is to look at every word individually. So this is a funny demonstration of how you can study a sentence in different ways by accenting the different words in turn. So that's what we're going to do here. So why learn fair representations? So first of all, why would you learn fair representations? So this is KDD. This is 2021. I don't need to tell people that machine learning is helpful. We've all seen many examples of how automatically finding patterns in data can be an extremely helpful thing. And we'll come back to this at the end, specifically in the setting for fair representations. Now, why would you want to learn fair representations? Now, fairness can mean a lot of different things. In this talk, we're just going to use it to refer to the idea of similarity or parity along some predefined axis. And again, by now, I think we've all seen a lot of, all the same motivation slides about all the harmful impacts that automated and sometimes learned systems can have. And there are a whole ton of technical and non-technical approaches to fairness and related concepts. For the purposes of this talk, we're just going to think about situations where we want a system to not use some piece of information. And this might be a piece of demographic information or something we want to keep private. And we'll call this information the sensitive information or the sensitive attribute. It goes by many names in the literature, and often we use the variable A to represent it. Now, why would you learn fair representations? So a representation is some transformation that's applied to raw data where the output of that transformation is useful in its own right. And this is, broadly speaking, this slide shows what we mean usually by learning fair representations. So why would you learn fair representations? And I think the answer to this is not as canonical as the answers to the other two questions. So the way I'm usually thinking about it is that we're assuming there's some downstream predictive task of interest. Now, again, this is deep learning day, and so one of the great successes of deep learning has been its ability to produce representations that are useful for these downstream tasks without necessarily knowing what the task is at the time. And so in the fair representation setting, there's two reasons why you might want to learn fair representations. One is because you don't trust some downstream user to access the original data in a responsible way. Or two, it's because you don't actually know what the downstream task of interest is yet. And these are kind of complementary reasons. Usually you're not considering both, but or at least the way I think about it. So let's look at these motivations each in turn. So this first one is the question of trust. So, there are lots of users out there who, may not be using your data responsibly, may be discriminatory in their classifications. And so if you're learning representation, you may want to remove the sensitive information completely from the representation in this case, so that no matter what people do, they can't use this information in an irresponsible way because they can't use it at all. Now, how would you go about doing this? So one natural approach is using an adversary, and this is in a figure from a paper, Learning Adversarially Fair and Transferable Representations, where we do exactly this. So the idea is that we want to remove information about A, the sensitive attribute, from our learned representation Z, while ensuring that Z is still useful. And so the way we might do this is, I'm not sure if you can see my mouse or not, but you have this input X, which is encoded into a representation space, outputs representation Z, and you have some adversary which acts on the representation and tries to predict the sensitive attribute A, and at the same time you use either some external classifier or some decoder to try to reconstruct the input to make sure that the representation is actually useful for different tasks. And this type of adversarial approach has been used in a few places. Another approach is something like regularization, which might be a more stable approach, but possibly less powerful depending on what your regularizer is. So you might want to, like for instance, regularize the MMD between the distributions of representations between different values of the sensitive attribute. And there's a natural analogy here to something like domain adaptation. One of the classic approaches to domain adaptation is, if you have two domains and you want your classifier to be trained on one and perform well on the other one, well, one thing you can do is make the two domains look a lot like each other, and then you get different types of guarantees about performing well. Now, the other motivation is that you don't know the downstream tasks yet. There might be a number of downstream tasks of interest, and in fact, there might also be a number of possibly sensitive attributes which are problematic in different ways for different tasks that you might, for different tasks you might want to remove different combinations of these attributes. In this case, one approach you might take is to make representations adaptable at test time. And this is what we do in this paper, Flexibly Fair Representation Learning by Disentanglement. And so the approach here, as it says in the title, is one that's very based in the disentanglement literature. So at training time, you have these non-sensitive observations and your sensitive observations. And the idea is you're going to encode your non-sensitive observations into some latent space, and also into some sensitive latent space, which attempts to predict your sensitive attributes, right? So that's B here on the left. And then you want B here to be predictive of the true sensitive attributes. Now, on top of this, the idea is to disentangle the non-sensitive latent space from the sensitive latent space. And if you're successful at doing this disentanglement, then at test time on the right, when you have some established task Y, or a label from such a task, you can then intervene. And what do I mean by that? So you can take this input X, use it to infer some sensitive attributes B, and then intervene on the sensitive attributes that you care about for this specific task to get this new modified sensitive vector B prime. And then if you've done a good job at disentanglement, you should be able to concatenate Z and B prime to do some type of prediction. So again, there's a natural analogy here to something like disentanglement, something like meta learning, where you have many tasks of interest and potentially test time adaptation. Yeah, and this is the type of approach you might take in this setting. So having looked at a couple approaches and a couple different motivations for representation learning, for fair representation learning, I'm going to take a step back and ask, what is the core challenge here? When we're thinking about approaches and when we're coming up with new ways to do this, what is the thing that we really need to be solving? And I think the hard question in this area is, what do you do when your sensitive attribute is correlated with other things? And this is kind of a benign question. This is really the question of all machine learning. What do you do when you have various features in your data that are correlated in different ways? But specifically here, if you want to remove sensitive information from your data, that might involve removing other useful information, which could be helpful for your task of interest. And the key question I think that sets fair representation learning apart from domain adaptation and disentanglement and a bunch of other fields that are kind of similar is how do we navigate this tension? So there's this fundamental tension between removing sensitive information and still predicting well. And how do we navigate this tension when we're learning these representations? And in my opinion, if you aren't asking this question when you're writing a paper on fair representation learning, you haven't actually written a paper on fair representation learning. You've written it on something else. I think this is really the key question of the field. And I'm going to talk a little bit about a couple of approaches at a high level you might take that people take around this and similar questions. So the first approach is to handle the trade-off. So you can imagine there's a spectrum between performing at perfect or optimal accuracy and removing all of the sensitive information from your input. And you can kind of turn a dial and go back and forth, whatever that dial looks like, right? And you can formalize it in different ways. And when you do that, you can make a picture like the one on the right, and you see these in a lot of these types of papers. And what this picture says is, at the bottom left-hand corner, I'm removing all the information. The top right-hand corner, I am predicting as well as possible, and then this line is kind of my Pareto front of how well I can trade off between these two objectives. And there is some work on information theoretic limits here and stuff. So this is one approach. Another approach to this question, which I think is really interesting, is, can we specify the unfairness that we care about a little bit more precisely? So, and what I mean by that is specify which parts of the sensitive information you want to remove and which parts you want to leave in. And I think this is really interesting because I think it's a good starting place for, rich conversations that you can have with different types of stakeholders or different types of domain experts or whoever, who often have pretty strong opinions about in what way exactly this information should be removed and what the relationships this information has to other pieces of information in the input. And I think there's interesting connections as well to things like interpretability and usability in the sense of what are good interfaces, and I put this in quotes because I don't literally mean interfaces, but I mean what are good ways to specify these types of specify this type of specification. I don't know a better word there. And so I'll go through a couple options here that people have looked at, mostly in the classification space. I haven't seen this so much in the representation learning space, and so I think this is a really interesting avenue. One is causality. So you can very quickly build a graph like the one on the right, and you can say you can pick particular paths from A to Y and say these are problematic and the other ones are not. So in this case, the green path from A to Y, we want to remove all the influence there. But the path that goes A to R to Y is maybe not so bad. That would be one example. There is a controversy around including sensitive attributes in causal graphs, and I'm not going to be the arbiter of that dispute, but I do think both sides have good points there. So this is one way that you could specify a different type of unfairness rather than just removing the sensitive attribute completely. Another way is multi-attribute fairness, so you specify a vector of attributes rather than just one. The work I talked about before with the disentanglement is the only work that I'm familiar with that looks at this in the representation learning setting. There is some work in the classification setting, and I think this could be really interesting scaled up. For instance, if you have a video and you want to build a representation, how do we remove all the information about clothes from this video so you can't figure out what someone was wearing in a video, for instance. Finally, there's this approach called environments, which has been gaining some popularity in sort of the invariant learning robustness community. There hasn't been a lot of work connecting this to the specifics of fairness yet, but I do think this is an interesting approach. It's intended to specify different experimental settings and has a connection to causality as well. Just something to keep an eye on. So back to this original question of why would we learn fair representations? One of the things that I think is really interesting is these past couple of slides, I've been mostly talking about how do we use auxiliary data better. And I haven't actually been talking at all about how do we learn better, which I think is a useful thing to think about. So, because in this fairness, with these fairness questions, we don't really have a choice but to use prior knowledge. Whether that's from domain experts or affected communities. And so maybe rather than better learning methods, what we need is better ways to design fair representations, or at least better ways to design the way we learn fair representations. So I think I'm on time. Thank you to my collaborators, and here are just a couple references that I referred to.
All right, yeah, thanks a lot, David. Maybe we'll have time for one question as Martin is setting up his slides. So a lot of the work that you talked about, in fact, even thinking about representation, talks about sort of a fixed length vector when your input is going to some representation. How do you feel this fits in with more transformer-like architectures where the model sort of looks at the whole input, has an attention on top of it, even for images? How do you sort of draw the boundary of where the representation is in models like that?
That's a great question, and one I haven't thought about that much. I think that in some sense, the key part of a representation is not necessarily so much the architecture, but where it fits into the sort of a larger system. So if you think about the representation as being the thing that you might pass on to someone who's doing downstream classification, and so whatever that looks like in a transformer, maybe that's a representation in the input space. Maybe that's some other type of sequential representation.
Right.
But yeah, I think they can come in many forms. So that's interesting.
Cool. Yeah. Thanks a lot, David. You'll be around for the panel, so we'll have questions then. Cool. So for the last talk in this session, I'm really excited to have Martin Wattenberg be our next invited speaker. He's a professor of computer science at Harvard now, but he also started this group at Google, the PAIR initiative, People Plus AI Research, which I've been following their work for a while. It's a really nice set of people. And yeah, so I'm really excited to have him talk about data visualization and how we should be looking at it a lot more. Go ahead, Martin.
Great, thank you very much. All right, so I want to talk a little bit very generally about what visualizations do. And the key point I want to make is that they can answer our questions, which is good and often is what we want. But even better, they can lead us to ask new questions that we did not have. And I want to illustrate this in a couple of ways. So I'm going to begin, and actually I would like to just look at an example that has nothing to do with machine learning, almost as a metaphor. And at this point, I'm going to switch to another tab. I hope the screen sharing works well here. All right. Good. Okay. So what you're seeing here is a map, a visualization that Fernando Villegas, longtime collaborator of mine, and I created many years ago. It's a map of the wind in the United States. And we had this long conversation on a very windy day in Cambridge many years ago. And I made the statement at one point that, the interesting thing about the wind is it always goes from west to east overall, with some tiny little changes but mainly because of the Earth's rotation, that's what it does. And Fernando was a little skeptical. And that led to a bunch of acquiring data, because that's the kind of people we are, and eventually to the visualization that you see here. So this answers the question of, does the wind, in fact, go always from west to east? The answer is clearly no. I was totally wrong about that. But it also leads us to many, many other questions as well. As we looked through this map, and look, this is showing basically live data, essentially. You can start to see many, many interesting patterns. One thing that I did not realize was just how much the mountains in the western part of the US actually affect the wind. You can see incredibly intricate patterns here over the Rockies, whereas if you go to sort of the Great Plains in the center of the country, very often you just see like vast, windy, straight areas. In this case, it looks like Canada is taking all our air, although there's something interesting going on here. And what it led to ultimately, besides an art project and many other things, was many, many more questions, many of which I cannot answer. And when you think about sort of the complexities of turbulence, probably, in fact, no one can answer really well. So the point is, we started with a simple question, even kind of a dumb question, like, does the wind always go west to east? And very quickly transitioned into a set of much more sophisticated questions. Okay, let's go back to machine learning and talk about how this same dynamic plays out in other contexts. Okay, so what I want to talk about as my machine learning example here is the geometry that is inside of a very particular neural network. And I want to do this very concretely, really get into the weeds on some stuff. But I'm also going to emphasize this is a fairly abstract piece of work that is not about an end-to-end system. I'm not going to talk at first, at least, about humans in this, but I want to think about this as related to those real-world applications in the same way that biology might be related to medicine. I think it's an important precursor in many ways. Okay, so let's set the stage here. We're looking at the BERT system. I've written on the slide here that this pre-trained network is pretty useful. That is meant to be the kind of understatement that gives you a quick, sensible chuckle. In fact, this and other networks named after Sesame Street characters are used all the time. And let me describe how it works. Well, I'm not going to tell you every detail of how it works at all. It's actually kind of complicated in many ways. There's lots of stuff going on. But for the purposes of this talk, I want to think of it as kind of an abstract thing. In particular, as a function that will take a sentence like the cat is cute. And then what it does is it will embed each of those words into a high dimensional space. And the space we're going to talk about here is basically going to be the space defined by activations of neurons in one of the later layers of the network. But without even getting into the details on that, just think about this as a way of taking a sentence, embedding the constituent parts into high dimensional space. And a key aspect of this is that those embeddings are contextual. It's not like a static word embedding like word2vec, where the words always go to the same place, but the position in space depends on the sentence as a whole. Okay, so that's kind of the set. All right, so because this has been so useful in practice, many people have asked, how does this work? And how do similar systems work? There's even kind of this funny term, Bertology, that people made up. I think it's like almost half making fun of all the field. But it's very interesting. There are many, many things that you can ask about this. For the moment, for the beginning part of this talk, I want to focus on syntax in particular. You can sort of make this guess that if you have a network that is working with language, is useful for all sorts of tasks in general, it probably knows, and I put that word in quotes, something about syntax. And you can ask, what does it know and how does it know it? So, this question about syntax, what even is it? Before we talk about how this neural network thinks about it, let's talk about how people think about it. So it turns out that people have thought about syntax for many, many years. It's funny. It's like what people tend to think of in this case is a tree. And there are various types of trees. What you see here are a couple of images I got from Google Books. These are textbooks in the 1880s. If you ever wondered what homework would look like in an American elementary school in the 1880s, it looked like this. You would actually have to go through and diagram sentences in this way. So people had this sort of kind of informal view that there was a tree structure. Today, linguists have come up with many types of tree structures in a much more formal way. There are different ways that you can think about grammar. There are constituency grammars where nodes can represent entire chunks of a sentence. There's another kind of grammar called dependency grammar, in which each word of a sentence is itself a node, sort of like the 1880s trees that I just drew. And the idea is that if you take a sentence like "the cat is cute," you can sort of draw it as a rooted tree, like this little diagram at the right. So there's a lot of evidence that people think of, certainly linguists think of grammar this way, and that even something about how regular people process it works on this level. Okay, so what about a neural network? Well, let's return to our sort of oversimplified view of what BERT is doing. This should be the image in your head. And let's talk about a wrong idea. A really cool idea that is not true, I emphasize this is not true, is that if I take the sentence, the embedding will actually reproduce the tree isometrically in Euclidean space. Like, it would be so cool if it were just, you could find the syntax tree exactly in space. That would be too good to hope for, and in fact, it is too good. One of the reasons we can say that the computer is not doing this is that it's mathematically impossible. And this little diagram shows why. So just take a fragment of a tree. Okay, so we've got a tree of 4 nodes. We're thinking about these trees as having unit length edges, and any tree that has a branch in it will have a little fragment like this. And if tree distance corresponds to Euclidean distance, we would have to have A and B 2 units apart, B and C 2 units apart, and A and C 2 units apart here. And that simply doesn't work. And it's kind of a fun puzzle to think about why not. And you realize, oh, okay, because A and B would have to be on exact opposite sides of X for this to work. Like, the segment between A and B would actually have to pass through X. But the same logic shows the same thing with A and C. And from that, you could deduce that B and C would have to be on top of each other. So it just doesn't work. Interestingly enough, it turns out you can find this idea explicitly in the mathematical literature since 1937. Like, this sort of abstract question is something people have thought about for a long time. Okay, so it doesn't do this cool but wrong idea. What does it do? Well, let's introduce a cool idea that might not be wrong. So there's a paper, I had nothing to do with this paper, so I'm allowed to say the following. I think it's a brilliant, wonderful paper, and I love it, from Hewitt and Manning a couple of years ago, where they showed that something like this idea that a syntax tree exists inside this neural network might be the case. So they suggested 2 things that are different from the simple but wrong idea I mentioned before. So one thing is they didn't just look at the points in activation space, but they learned a single linear transformation that you apply to any sentence embedding. They called this a structural probe. And then they said, after this linear transformation has been applied, the points that correspond to words are in a position such that the square of Euclidean distance corresponds to the tree distance. Okay, so it's not too far from the cool but wrong idea, but it has this weird little twist about the square of distance. So one thing that we as a group at Google did, and this is a group of wonderful people in our team at Google, was we started to ask ourselves, what is really going on? What do these embeddings look like where the square of the Euclidean distance corresponds to tree distance? And it turns out you can start playing with the math of this, and you get, actually fairly simple, understandable results. So let's go back to our previously this thing that was impossible to embed, this, and say, how could we embed this in space so that the square of the distance between the embedding of A and B would be 2? If you look at this, it almost looks like a little 3D picture. And actually, if you draw that 3D picture, if you think about these as points on a cube, you realize from the Pythagorean theorem that actually everything has worked out really well, that in fact, the distance between B and C squared is 2. It's actually kind of pretty. Let's try another example. Maybe that was just one weird fluke. Let's take a tree. This is sort of a degenerate tree. It's all nodes in a line, and ask ourselves how that would embed. So we've got, we need the distance between A and C to be 2 and B and D to be 2, and then A and D are 3. And if you look at this funny kind of zigzag thing on a cube here, you see again with enough applications of the Pythagorean theorem that works out well too. Okay, and you can start to see a pattern. There's something about having these orthogonal unit edges that is actually working out very nicely. So it turns out that here we're running out of dimensions, but like the nice thing about BERT is we're not really dealing with an activation space of 3 dimensions, but it has hundreds of dimensions. We've got plenty of room, at least for short sentences. So let's think about the general case, how we might create an embedding that would work. And it turns out we can actually be very explicit about this. Let's say we have a tree on the left. We've got nodes, which I've indicated by T0, T1, and so forth. And what we're going to do is we'll assign basis vectors, so unit orthogonal vectors to each of the edges. And it doesn't even matter how we assign them. We're just going to plop them down there on the edges in any order. And then our embedding is going to be very simple. For a node in this tree, we're just going to move up to the root and add up all the basis vectors we encounter. Okay. And if we do that, what you see is that then if I take any 2 nodes, it's actually very, sort of a straightforward calculation. You can see that the square of the distance is just going to be the same as the tree distance. Again, very simple L2 norm arithmetic, essentially. So what we've done essentially is say we have this very simple kind of embedding. We called it a Pythagorean embedding, since it's all the Pythagorean theorem basically makes it work. And it has like these very nice properties. So, first of all, it's very simple to describe. You can basically say, look, if you're moving through this tree, you start at the root node. Every time you come to a branch, you just branch out with unit vectors that are orthogonal to each other and to any other edges or nodes that you have in the graph already. One kind of funny thing is to realize it's not that different from a randomly branched embedding. So let's say that you started out from a root node, and every time you went down a edge of your tree, you went from the parent and you just chose a unit Gaussian and went in that direction to the child node. In that case, because in very high dimensional space, unit Gaussians are, chances are, they're about length 1, and they're generally going to be very close to orthogonal to each other, it will be a very good approximation of a perfect Pythagorean embedding. Another interesting thing to realize is that if these directions are in fact axis aligned, you could also think of it in the L1 norm, if you're the kind of person who loves the L1 norm, that it then is an isometric embedding of the tree. So it's got multiple nice properties that indicate this may be something interesting and useful. Let's talk about where visualization comes in. So one of the things that we wanted to do is we said, well, let's take some sentences and look at the BERT embedding that we see at, post application of the structural probe. We will compare it to an exact Pythagorean embedding, to a randomly branching embedding. This is where I describe this unit Gaussian idea of, every branch is a unit Gaussian from the parent, or every child is a unit Gaussian from the parent. And then just to make sure we're not seeing things in our visualization, jumping at shadows, we'll also compare, and this is the 4th image on the right, something where we've got genuinely random node positions where there's no relation between a parent and child at all. We've just chosen each one to be complete random Gaussian. And then what we'll do is do principal component analysis to project this to 2 dimensions. So you can see that in fact, the BERT embedding, the Pythagorean embedding, and the randomly branch embedding all look basically, you can see the close relation. This random position embedding just looks completely different. So this is sort of nice visual verification of something we can see in numeric tables. But here's a neat thing about visualization. We looked at this, and one thing we started to wonder was, we're like, okay, these sort of gray networks are kind of neat and all, but there's more visual variables we could do. What if we colored these edges by something? Is there anything else we could look at? And we had this idea. We're like, well, what we could do is, we could take this syntax tree, and the truth is we can draw it like this and, see that some edges are in fact longer than others. It's like they're not all unit length edges, like our beautiful, pure Pythagorean embedding. And so what we could do is we could take our PCA and color edges by whether they're longer or shorter than you would expect compared to standard Pythagorean embedding. In fact, when two nodes are very close, but there's not an edge, we can draw sort of a dotted line, say, whoa, these things are very close. And when we do that, we started to see some interesting patterns, that it was not completely random which pairs of words were farther than expected and which were closer expected. We're essentially looking at the residuals of a statistical model we have, and those residuals have some meaning. So for example, hold on one second, move some windows around here so I can see what's going on. You can see that like same as looks really close. There are, in August is closer than expected, whereas these two noun phrases like nearly the same and in the billions, those are very far. So that's actually kind of interesting. And I can see similar things here, like this preposition for a spokesman, the for is really close, even though the dependency grammar doesn't say those are going to be neighbors. Whereas like these two nouns, spokesman and guild, those are farther than you would expect. Interesting. Let's look at another one. Once again, you can see these prepositional phrases. There's some sort of like magnetic attraction. Some of the other things are different, are farther away. So all of that led to sort of a new question for us. We're like, well, is there a pattern here? And as we went through, just sort of anecdotally, we saw more patterns. But then we could do something systematic, and we could say, okay, in our data set, we actually know the type of dependency relationship. There's different, you can come up with different terms for like, what the linguistic relations between these words are. And we can just average over our whole data set whether they're sort of more or less far than you would expect. And what you see here is a bar chart showing sort of the average ratio of the observed square distance to the actual square distance with a different type of dependency relation. And then there's a little error bar within each bar that gives you a sense of whether things are, how seriously we should take differences. And the answer is, in fact, there are very statistically interesting systematic differences between different relations. So that's a whole direction we did not particularly expect to go. And that immediately leads to a bunch of questions. Should we in fact be modeling syntax trees as having different lengths for different edge types? And I think for people who are expert in grammar, this is not the newest thought in the world. People have thought about this before. However, I think this direction we can ask, oh, well, maybe we could choose between different models. Maybe this is a way to tune those lengths in an interesting way. It also raises the question, is dependency grammar the right particular choice of the way we're coming up for a tree? That's also interesting. We could even wonder, could any of this potentially shed light on how humans process language? Well, one can always hope. So it's sort of an interesting idea. And for me, like, if there's a takeaway from this, it's the idea that, we think about people as having mental models. Neural networks may have these mental models as well. And, a lot of interpretability right now around neural networks focuses on one of two things. They focus on figuring out which features or combinations of features are salient for a particular decision. And these are very useful. I have nothing against these. People also think about, how do we approximate a complicated function to explain it to a person? So for example, a technique like line, which says, let's take a local linear approximation, would be an example of that. Those are also very useful. But there's much, much more we can potentially do on interpretability besides these two types of things. And I think you know, I'm not saying we're the first people to look at this by any means, but this idea of looking at sort of what is the mental model, I think, is important. It's interesting. It also kind of gets us away from questions about, like, you know, do these models just look at surface correlations or not? You know, because I think we can say at this point, well, if this is based on surface correlations, then the surface correlations are pretty interesting. So I think it's a good way of looking at the world. And I think I'm also going to say that another good thing about this is that this general line of work, and again, this is not just us, but Hewitt, Mann, and others, I think people are starting to realize, wait, there are other directions you can go. And again, visualization can be very useful. You could ask, is this structural probe that is based on a linear model, is that the only kind of probe we could make? You know, and there's this interesting idea that there might be nonlinear probes that have the same number of parameters, at least roughly, that might give you slightly better syntax trees and, you know, suggest other sort of geometric considerations. There's also this whole kind of cottage industry around hyperbolic embeddings, which, you know, I trained as a mathematician, so I find this very fascinating that this would come up. And one of the interesting things is when you look at these types of embeddings, again, you know, visualization can be a very useful and important way for building intuition around what's going on. Okay, so I am going to say, I'm going to try to keep us on schedule here. And I think I will probably wrap this up. I will say that we've talked a lot about semantics, or syntax so far, but semantics is another place where I think visualization can be extremely interesting and powerful. And, you know, one thing that is also in this paper that I mentioned is we looked at this question of what happens if you look at the context embeddings for the same word, but in many different sentences. And it turns out there that, hold on a second, that in itself gives you a whole new view of what word senses, how they look, and how they feel. And I'm just going to leave these URLs on the screen as I sort of close here, and suggest that, and you can probably just Google for like context atlas, Google or Pair or something if you want to find this as well. And go take a look at what happens when you type cat into this context atlas and you see the map of the meanings. And then try some other words. And my guess is that you too will start generating hypotheses about how language works and how word senses work that you did not have going in. So I will end there and just say visualization can answer our questions, it can lead us to ask new questions, and make us also question our assumptions, which may be the most important thing of all. Thank you very much.
Thank you, Martin. That was a really wonderful talk. I know linguists have been sort of debating what's the right representation, especially when you think about computational linguistics for representing syntax, and when you have environmental protection agency, how should you be representing that as a tree? And clearly I can see that there are different choices that I guess BERT has made than what we made when dependency trees were decided a certain way to be annotated. So yeah, that's really cool. I think what I really like about the visualization is how, you know, you're showing screenshots, but it doesn't have to be a static thing. And so there can be a lot of nice dynamics in the whole thing. So have you looked at something like what dynamics might look like maybe as you go through different layers of BERT, or maybe during training, like how these things emerge? Anything on that side of things?
Yes, and in fact, you know what I might do, actually? I am going to paste a link into the chat that is a link to an article, and then that has a link to the visualization that you can use yourself. And so we did, in fact, look at sort of how these, say in the word senses, how these emerge over the layers of BERT. And it is kind of fascinating, because like what you see is that there's initially, when you visualize, you know, the things that come in the input include stuff like all this position information, and that often dominates sort of the picture. And then what you see is gradually, you know, it will recluster into a form that the word senses seem to be the kind of major piece of information.
Okay, yeah, really nice. Okay, I think we are out of time at this point anyway, but yeah, thanks a lot, Martin. This was great. So at this point, we'll take a short break and we'll return in a little more than 10 minutes to continue the theoretical understanding of deep learning, followed by the panel at the end, where all of the speakers of the interpretability, fairness, and visualization, I guess, will be available to answer more questions and discuss some issues. Yeah. Thank you, and see everyone in another 10 minutes or so.
Hi, everyone. Welcome to the last session. This is the last session at 30. So we have 4 speakers to invite the talks and 2 contributor talks, followed up by our second panel at 4:15 p.m. PST. So Jason Lee. Jason is an assistant professor in electrical engineering and computer science at Princeton University. Lately, he has worked on the foundation of deep learning and reinforcement learning. He has received ONR Young Investigator Award in mathematical data science, Europe, and was a finalist for young researchers in continuous optimization. Welcome, Jason.
Hi, thanks for having me. So today I'll talk about methods for provable representation learning. This is joint work with Qi Lei, Simon Du, Wei Hu, Sham Kakade, Nikunj Sanchi, and Jiacen Zuo. It's based off 2 papers. The archive identifiers are on the bottom. And I just wanted to mention Qi Lei will be on the academic job market start this upcoming year, so keep an eye open. Both of these papers are with her. Okay. So I'll try to cover 2 topics today. The first one will be on supervised representation learning, and the second will be on self-supervised learning. Okay, so why do we care about representation learning? I would argue that a huge amount of deep learning success is due to its ability to learn useful representations, not only its ability to classify well or predict well. It's really that it also is excellent at learning representations that transfer to other tasks, not only the one that it was trained on. So roughly speaking, what I think of as why deep learning is successful is it's able to learn a feature representation. This feature representation easily transfers to other tasks. These representations can sometimes even be learned on unlabeled data, for example, self-supervised learning or pre-trained language models. And this is sort of a paradigm shift from if you compare to work pre-deep learning that had trouble doing this. It would be very difficult to get a random forest, a kernel machine, or gradient boosting to extract features from these and then reuse them on a completely different task. This is something that is not, at least, it's not obvious how you would do this, and nor was it common before deep learning to do this. Okay, so let's sort of look at a caricature of how representation learning is done in the modern era. The simplest algorithm, they all sort of proceed like this, is you train a deep network on some task. Commonly, if you had labels, you would train on ImageNet or some self-supervised task, contrastive learning, for example. So learning that augmentations are close, predicting corrupted versions of the image from the original image, and so forth. So learning to denoise, learning to predict rotation angles, recover the color channels. These are all sort of different tasks that you can train your deep network on. And then you keep only the body and discard the head. So usually you would think of there's a part of the network as an encoder and part as a decoder. You would discard the head part, which corresponds to the decoder. And then you would retrain or fine-tune this head using label data from the target domain, from the task you finally actually care about. So this is sort of the paradigm for how much of representation learning is done these days. Here's a simple diagram. It's basically what I said, is that you have, so for example, in supervised pre-training, you have, these are your representation layers or your encoder layers. These are some task-specific layers. So when you would discard these, and then only keep this and use this and train a new head here. So you discarded that, train something for task T+1, that's the next task, using these either fixed or fine-tuned depending on exactly the setting and how much label data you had from the target task. But regardless, these phis stay quite close to what they would have in the pre-training phase. So this is not a new thing. This dates back to Caruana, who also proposed doing this using neural networks in '97. And many of the deep learning success stories are actually success stories of representation learning. Any domain without init data, even the applications with a lot of label data, ImageNet can benefit from self-supervised pre-training, language models, transfer learning, meta learning, deep reinforcement learning. A lot of these are because convolutional networks are able to extract good image representations and then use these on in these specific domains. Okay, so what is known in theory about representation learning? So I'm a theorist, and my goal usually is to sort of understand what can be done and what cannot be done, and what is sort of the most you can push. Okay, so let me define some notation here that will be helpful from now on. Is I'll always denote the representation by phi. So this is the capital Phi is the representation class, little phi is a representation function. G is the head classifier. Typically it's linear in most applications. And my notation will be, you have T tasks. So for ImageNet, you can think of a task as a class. So that would be about 1,000 classes. N sub S samples per source task. And N sub T samples on the target task. And CFF will denote a complexity measure of the function class. Typically Rademacher complexity or Gaussian complexity or log covering number. The precise choice is not very important, and all of the results are true for any of the complexity measures you choose to use. So earlier work around 2000s, in the early 2000s by Baxter, and very recently by Marr, maybe 2-3 years ago, proof bounds that look like this. They showed that your risk is upper bounded by the complexity of the representation class, so complexity of phi over root T. And then the complexity of the linear classifier over root NT. NT is the number of samples you have in the target domain. So you should think of this is small, but NT is also small. And you should think of this as very big. And you should think of T as like sort of maybe a few hundreds or something like that at the most, not super big. So this bound is kind of lacking if you look at it. The number of source samples across tasks does not matter to help you learn the representation. So what that means is that if you have one source sample per task versus 1 million, it doesn't matter. And this is very counterintuitive. You would hope that if you had 1 million source samples per task, you could learn the representation very accurately. But this theoretical analysis was unable to leverage this. Okay, so sort of, now let's do some wishful thinking. What is the best bound we could hope for in this setup? So sort of the best bound, if you think about it a little bit, the best bound you could ever hope for is the complexity of phi divided by the number of source samples per task times the number of tasks. So this is the total number of source samples. So in ImageNet, this is a training set size 1.5 million or whatever. And then the second term is roughly the same except without the square root. So, and both terms now don't have a square root. So this is much better because the complexity of phi is a big number, but it's now divided by a very large number, the total size of the pre-training data set, which can be very, very large. And of course, you would hope that your assumptions are somewhat necessary, not only sufficient. So sort of that's asking whether there's a lower bound of this form. Okay, so before I go into how to attain this ideal bound, let's compare these in some more detail. On the left, we have the original bound by Marr and Baxter. And the primary difference, like I said earlier, is the denominator is replaced by the total number of samples instead of only the number of tasks. And a minor gain in what in learning theory people call is you get a fast rate now instead of a slow rate. This is more of a small gain. But the real gain is really when n sub s was 1 versus when n sub s is very large, like 1 million, 10 million, 100 million. In unsupervised pre-training, you can frequently have, hundreds of millions, billions of examples. And that would have, and the old analysis kind of was ignorant of this kind of large source samples. It was unable to take advantage of this at all. Okay, so now let's turn to what kind of assumptions we would need to try and get a rate of that type. Okay, the first one that you can kind of see is somewhat necessary is that you do need your tasks to share a good representation. So Y is linear in some representation phi star. So phi star is something in our class capital Phi, and there exists a phi star such that if you had this representation, it would be linearly separable. This alone is not enough. You would also need some sort of diversity of the WTs. Why is this? Just think about the case, the very degenerate case where all the WTs were equal to each other. So but they're all equal to W1, but WT plus 1 was different. Then there's no way you can learn phi star in the direction of WT plus 1 unless you observe data in that direction. So that's simply just simply impossible. And it's easy to prove that these are necessary assumptions. So kind of the first one just encodes what transfers across the task, what is shared and what is not shared. And only the shared parts you can hope for that you can benefit from pooling all of the data. The second part is the diversity of the WTs. I already said, if all of them are equal, but WT plus 1 was not equal, you would be in trouble. This would never work. So you need some sort of coverage assumption that's kind of saying like your target sample, your target distribution is somehow covered by the source samples. And like I said, these are somewhat necessary. It's easy to show failure. Okay, let's look at the algorithm we'll analyze. Is in the source tasks, you will minimize over the representation phi and the task-specific heads, the linear predictors. So you just minimize the sum of squared errors, mean squared error, over all tasks, phi of xt times wt, and you minimize this. Then after you do this, you have a phi left and w's. The w's you discard. They don't play any role anymore. You're going to throw them away and relearn the w now with labels from yt plus 1. So this is sort of the algorithm. It's sort of essentially mimicking an abstraction of supervised pre-training. Your source tasks are ImageNet, your target task is some other computer vision data set. Okay, so let's turn to let's first look at the linear case as a warm-up before we turn to the case of general neural networks. We'll let phi first be a linear map in X. So that means that although we're in dimension D, only K of the directions matter, right? Only the directions in the span of B matter. The rest in span of B perpendicular, they don't affect Y at all. So you don't need to learn anything about them. So what do the assumptions mean in this warm-up case? The first assumption simply means that you have the same B for every task, like that YT is equal to WT transpose BX, and the B is not indexed by T, right? Not indexed by T. That's what it means. The second one means this diversity can be written quantitatively as you take the W's, you stack them into a matrix, and this matrix has condition number O of 1. So this is saying the W's, they kind of span the full space, and they're not missing out on any direction. That's what the diversity boils down to if you try to write it out quantitatively. Okay, so under these assumptions, what we guarantee is that the risk is less than the number of parameters in B. Remember, B was a K by D object, so its number of parameters is KD over the total number of source samples n sub st, plus the cost of learning the linear predictor on the target domain, which is K over NT. So this bound is nice. This less than equal to is only hiding logs. There's no condition numbers. You don't ever actually identify the right features. You only identify enough of them to be estimable to do prediction. So for example, if X was very poorly conditioned, then span of B is not even identifiable, but this theorem is still true. You can extend to the case of covariance shift. You don't need that P1 through PT plus 1 are the same. If you look at the paper, there's a way to quantify the covariance shift. There's some concurrent work that I want to mention by Triparaneni et al. That in the isotropic case, and they don't allow covariance shift, and they operate in a regime where you have to identify the span. I haven't talked yet about algorithms. In the linear case, this is implementable via a nuclear norm convex relaxation at the cost of certain condition numbers in the risk. The reason I'm not focusing on algorithmics is that in the neural net case, there will not be a polynomial time algorithm anyways. So I'll mostly ignore algorithms for today's talk. So in the general representation learning case, the theorem looks very similar. You similarly have the risk is bounded now by the complexity of the function class instead of KD. This used to be KD. And the Rademacher complexity of K by D matrices is KD. So it recovers the case of linear, and then the cost of learning the linear classifier. The one difference is that we don't know how to solve this using SGD and polynomial time or anything like that. As far as I know, there's no algorithm. There's no polynomial time learning at all in this representation learning space. Covariance shift is still allowed, can be quantified. So let me discuss a concrete example instead of at that abstract level. Let's just consider the case of a two-layer neural net rather than a general neural net, where it's easier to quantify these parameters. Okay, so again, in pre-training phase, we minimize the square loss. And here I put some regularization so I can quantify the Rademacher complexities. And then similarly here, I minimize the square loss where this is fixed. This is fixed at the pre-trained one. Okay, now the theorem I get is simply the Rademacher complexity of the two-layer neural nets, which is actually just turns out to be the norm of B. This is one bound on the Rademacher complexity. There's many. Divided by N1T, so total number of source samples, plus the norm of the linear classifier over root NT. The nice thing here is that you can allow arbitrarily over parameterization in your networks, and this bound doesn't depend on the number of neurons at all. So it doesn't matter that the learner network had a ton of neurons. It only depends on intrinsic norm quantities or the Rademacher of the neural network. Okay, so this is nice. This kind of shows you that supervised pre-training, at least from a statistical learning perspective, can benefit from the fact that we have large diverse data sets like ImageNet that with a ton of samples, and that shows we can learn good representations. Unfortunately, if you move outside of images, there's not a lot of labeled data anymore. And what is commonly done these days is a rebranding of unsupervised learning. Essentially, we try to create labels from the input data, otherwise known as self-supervised learning. So, okay, so now this sounds very mysterious, right? Because your self-supervised learning is essentially learning to predict functions of the input from other parts of the input. For example, you would predict that two augmentations are similar, but really an augmentation has no extra information of the image, right? Because you generate the augmentation from the original image. So by definition, it has the same information content. The same thing in context encoders, you delete a patch of an image and try to fill it back in. Like there's no extra information you've learned here at all. Next word prediction, missing word prediction in language models, image colorization. You're trying to predict things you already know. So how can this help? If you think like an information theorist, this is completely counterintuitive. Like you cannot gain information. Although our work is somewhat general, I'll talk about a special case today where I'll think about just context encoders as the sort of a stylized version of self-supervised learning. So on the left, I have an image of a Pikachu with his eye deleted. And then I want to predict this patch, whereas it's his eye. So what do I do? In a context encoder, what I do is I train a neural net, call it psi now, to minimize x2 minus psi of x1. So x1 is the image without the eye, and I try to predict the missing patch from the original image with the patch removed. In this case, what we do is we take the psi and then we learn a linear classifier on top of it, a linear projection head on top of the psi to predict the downstream text y. And when we learn W, we have labels, but when we learn psi, we use no labels. And I don't need to tell this audience that self-supervised learning is very much in the mainstream now, works very well. This plot, I took it from a Google AI, it's probably a year old now. And it was from the Simclair paper, just showing Simclair does very well. And there's Muko now, and a lot of variants. They're all very similar, and they all do very well with very few labeled data points. And similarly, it works very well for transfer learning. The point here is just saying it's doing essentially as well, if not better, than supervised pre-training on ImageNet, even in computer vision transfer settings. Again, taken from the Simclair paper. Okay, so what I'm concerned about is why does this help, right? If I think like an information theorist, I've gained no extra information, and thus I should not improve my sample complexity. However, there is a hope here. The hope is that by solving these pretext tasks, you keep the relevant parts of y condition on x, right? Our final goal is to learn y condition on x, but x is a very high dimensional object. And we can hope that psi is doing some dimension reduction, like it's keeping the relevant parts of x to predict y condition on x. So that's very abstract. I'll try to make this grounded in 1 minute. Let me just mention there's a lot of related and concurrent work sort of on when you can compete with the best mean classifier, but here you have to assume that you have data from the positive class, like it's from the positive class and it's from the negative class. That's a much easier setting because if I know it's from the positive class and negative class, for example, I can just do clustering or something. And in specific models, Tosh with Daniel Su and Akshay have analyzed this. And similarly, in the linear case, a long time ago, maybe 15 years ago now, Foster, Kakade, and Tang Zhang and Ree Johnson looked at this using canonical correlation analysis. And there are several explanations based on information bottleneck, although not rigorous. So this task, again, I'll look at context encoders as the motivating example. And let me specify the algorithm now. The algorithm is I take the input, divide it into two parts, x1 and x2. For example, x1 is the bulk of the image, x2 is a small patch, it can be a sentence with a word deleted, whatever. There's many ways to define this. Or x2 could be some augmentation of x1. These are all potential examples. So let's set up the pretext task as minimize over psi of x2 minus psi of x1. Typically, you would have psi of x1 is a decoder, encoder, and then you only keep the encoder part. Like usually you would choose this to be E theta. So you throw away the decoder. That's kind of analogous to like throwing away the top layer in supervised pre-training. You kind of believe those were very task specific, so you throw them away. Okay, and some variants are you can solve many pretext tasks to get more coverage, which is kind of typically done. Like you wouldn't use one image patch. In the context encoder, you would use many of them. Same with like next word prediction or missing word prediction. Okay. So my label would be an RK. Think of like a one-hot encoding of the label. X1 will be in D1. X2 will be in D2. Think of D1 as much bigger than D2, and D2 just think of roughly equal to K. That's kind of the mental model you want to think of. And I'll also later, I will invoke certain latent variables Z. So let's look at what happens now in the linear case. So in the linear case, you solve this pretext task, you just minimize over this matrix B. After you get the B, you train a linear thing on top. And let's compare this to if you minimize y minus theta dot x1 squared. In the linear case, there's a closed form, theta equal bw star plus the conditional covariance matrix of x1 and x2 given the labels y times a term delta. So the point here I want to make is that if x1 and x2 are independent given y, the partial correlation is 0, then theta is equal to bw star. So the way to think about this would be that, like, for example, if every single class was only specified by a few traits, like for example, the dog class is kind of is very homogeneous, then 2 dogs would be independent given the label. But if you had different subspecies of dogs, for each subspecies, you would have a cluster, and then inside the cluster, they would be independent, meaning like you cannot easily distinguish 2 different poodles or something, or 2 different poodles in an indoor setting is very hard to distinguish. That's kind of what this assumption is saying, is that if x1 and x2 are kind of indistinguishable given y, or y here given some additional latent information, then this method would work well. So meaning you would only need K samples instead of D1. And remember the setting here is sort of D1 is much bigger than D2. D2 is approximately K. And that's exactly what the sample is saying, this theorem is saying, excuse me, is that if X1 and X2 are approximately independent given the label information plus some additional fine-grained information like the species of the dog, whether it's an indoor setting or outdoor setting. And then once you have these additional latent variables, X1, the image and its augmentation are kind of indistinguishable, then the error in self-supervised learning is very small. The gain here is you reduce from D1 to K plus the number of latent variables you have over N sub L. And this is the pre-training error, which goes to 0 if your number of unlabeled sample goes to infinity. So usually this epsilon pre I'm thinking of as very small because we have a lot of unlabeled examples. So sorry, this is the inherent error you have of not of fixing a representation, but at the cost of this inherent error, you've drastically lowered your sample complexity. For general functions, for example, if instead of linear representations, it was a neural net, there's a similar theorem. The only challenge now is to define what is this conditional independence quantity and how to quantify it. We quantify it by the Hilbert-Schmidt norm of the cross-covariance operator. This is kind of a complicated definition. It can be written like this. You can easily check this is 0 if x1, x2 are independent given y and z. It's just a way to measure the independence, which you can do via norms of the cross-covariance operator. And again, your risk is now less than k plus m, the number of latent variables plus the number of classes, and these inherent errors due to this, and the pre-training error. the nice thing now is that X2 does not even need to linearly predict Y, but after you learn this representation, it sort of pulls out the relevant parts of X2. And in fact, since psi can do nonlinear transformations, it in fact makes Y linearly separable in the representation space. So sort of X1 and X2 cannot linearly predict Y, but after doing self-supervised learning, psi can linearly separate. The improvement here is very large. You went from n sub l being k plus m samples, and before you have to learn across all f star and f, which is sort of like the Rademacher complexity of all our neural nets, which is very large. Like all the quantitative bounds are hundreds of millions, that kind of thing. And now you've reduced it to whatever the size of a linear projection head is, usually in the hundreds or the low thousands. So that's sort of what I wanted to say. There's many future directions to go here. To me, this is one of the most exciting areas in ML theory. Probably the most urgent to me is provable algorithms for representation learning, preferably very close to the ones used in practice, namely SGD, on realistic architectures. How to do this, except in the linear case, I don't know yet. I think it's a very difficult problem, but something worth addressing. And right now we quantified the error of self-supervised learning in terms of norms of a conditional covariance operator. What other conditions can allow self-supervised learning to work? This will allow us to help us design pretext tasks. Right now, the design of pretext tasks is kind of completely arbitrary. It's like whatever augmentation I can think of, that gives me a task. What is the connection between using contrastive losses, its various forms, like momentum encoders, there's all these tricks of the trade, versus these reconstruction? Can theorists inform us about how to modify and design better self-supervised learning algorithms? And finally, what is the role of fine-tuning the network? Typically, we don't just train a linear layer, we'll put a multi-layer perceptron MLP projection head on top, usually maybe 2 hidden layers, 3 hidden layers, that further refine the representation, especially when you have enough labeled examples. And that usually results in pretty significant gains. Can we say why that's the case? Right now, none of the theory can do this. And that's all I wanted to say. Thank you for listening.
Thank you very much, Jason. This was very interesting. So please feel free to write in the chat if there is a question. For next time, I will ask a quick question and let's see. So one quick question is that, like, in terms of, like, you talked about this error of representation learning, but in terms of generalization error, does this analysis that you have, does this provide a tool to compare the generalization when we do self-supervised and then we introduce some labels with the case that we do supervised end-to-end?
Yeah, so it kind of suggests that when sort of, let me see, sort of when this term is very small here, epsilon, these two, I guess, is very small, self-supervised learning is going to do much better because it reduces this to a linear classification problem. The sample complexity of linear is roughly the number of parameters, k plus m. For example, the complexity of a neural net is much larger. It's at least, for example, if you use VC dimension, it would be the depth times number of parameters, that type of thing. So, you know, it's over 10 million for any used architecture for most of these complexity measures. Versus k plus m, if you look at like a lot of things times, it's like 500, 1,000 type of thing. It's like 3 orders of magnitude less, roughly.
I see. So, and can you, sorry, remind me quickly about these 2 error terms?
Yeah, the first error term is measuring how much, basically, given the class and some additional information, like how indistinguishable are an image and its augmentation. So it's sort of like you're kind of thinking that, okay, if I have a, for example, one way to say it would be take an image of a poodle and then you jitter the color channels. if it looks roughly the same as the original poodle and all the other poodles, then this is good. But maybe you needed some additional information because this poodle was like, I don't know, a particular shade of white, and he was in indoor background. Those would go into Z. So Z encodes like some additional information. Yeah.
And when these error terms are small, you said that
when
self-supervised is
X1
a
and
better
X2 are essentially indistinguishable. This would be small.
Then
Like they're independent given the
self-supervised.
label
I
plus
see.
some latent information.
I see.
And this one's just going to 0 with a number of unlabeled samples.
If you can
you can just think of
take
this
care of
as,
that offline for the sake of time.
Okay.
Oh, sorry. I think there's a delay.
Yeah.
Okay. Thank you so much. Thank you so
All right.
much, Jason. This
Thank
was
you.
very interesting. Thanks
Thank you.
again.
Goodbye.
Okay. Our next speaker would be Andrew Stolman. Andrew is a PhD student in the University of California, Santa Cruz. And Andrew wants to talk about GNNs for us. So Andrew, feel free to share your screen.
Hi,
Give it a
thanks.
try.
Yeah, sorry, yeah, it wouldn't let me unmute myself while sharing the screen. There we go. Can you all see it?
1 second. Yes, great.
Cool. Well, hello, everybody. Thank you for having me. This is work that I did while I was finishing my PhD at UC Santa Cruz. I now work at Katanograph, plug to my new employer, although they didn't have anything to do with this. And so this is joint work that I did with my advisor, Sisa Chaudhry, Anish Sharma, Ashish Goel, and Caleb Leby, working on graph embedding stuff. And so we're looking at how machine learning is performed on graphs. There's all these complex machine learning machines, like this big complicated machine here, and you want to compute some task. You're going to feed into it. Let's say it's trying to predict whether two people are friends, and you have some social network. It incorporates some features from the people. You know, maybe you have their gender, age, that sort of stuff, and feeds it through this complex machine learning pipeline and outputs some kind of result. The problem with graph structured data is, how do you incorporate the graph structure into these predictions? Is there some kind of like convenient task independent representation of graph data to use in general ML pipelines? And one answer to this that's received a lot of attention is this work on graph embeddings. And what these graph embeddings attempt to do is convert the graph into a set of vectors in some low dimensional space. And you'd hope that the vectors are close to each other in this space if they're close to each other in the graph. Like, you know, if they're joined by many edges, then they should be closer to each other in the embedded space than if they were joined by fewer edges. So here, my advisor made this. I assume his vector is closer to like Paul Erdős's than it is to Leonard Euler or whoever that is over there. They probably have, you know, closer social relations. So this is the goal of this graph embedding work, and it's a really popular line of research. A very basic embedding method is just to do SVD on the adjacency list, Laplacian eigenmaps. There's been line of work that incorporates more deep learning, this Node-to-Vec and Deep Walk in the past 4 or 5 years. The bottom here is a survey of, it was a really good survey. Now it's probably outdated. The field's moving so fast. Looking at all these different embedding methods. And so, yeah, the hope is that then you get these vectors for each vertex, and you have your larger machine learning pipeline, and you can just feed these vectors as features into any prediction task, completely independent of the task, whether you're trying to predict two users are friends, fraud detection, whatever the task is. You have some general purpose embedding vectors. And you'd hope also that these embedding vectors are in a very low dimensional space so that you can curtail the effect of dimensionality. And so we wanted to do a principled investigation of these embedding methods. And one of the most popular approaches is basically follows this rough low rank factorization framework. You pick some n by n matrix M that represents proximity in the graph. It might just be the adjacency matrix. It might be some power of the random walk matrix, something like that. And then you try to approximate M with some low rank factorization. You want to get this low rank matrix V such that V transpose times V gives you a good approximation of M. And there's a few different methods that people have tried into, different notions of closeness. We'd like to study them generally, but for the sake of a principled study, we'll look at a few in specifics. But a lot of methods follow this general pattern. And so, yeah, this is the question we want to study. Like, there's all these methods to produce these embeddings, but there's no real study of what kind of graphs you could represent through these low rank factorizations. And if you look at like the experiments they do, like the embedding methods are often just compared with each other. It's hard to see like what the embeddings, if the embeddings are really that helpful, if they're telling you anything deep about the graph. And there's been some work examining this. In the past few years, we've seen some papers come out that claim that simpler methods that don't use embeddings and that are just trained on other features tend to outperform them. And so we wanted to investigate why. And so our first work on this was in PNAS. And we look at the simplest kind of low rank factorization models and show that they actually can't represent some really fundamental facts of real world networks that we see. And then we look at this in an extension that is not published yet, but I'll show you a little bit about it if I have time, where we look at slightly more complicated models and specific downstream tasks. So first, let's talk about what real networks look like. We know that real networks are sparse in general. The number of edges is way less than n squared, the number of possible edges. But despite this sparsity, they have a high clustering coefficient, meaning that if V is a neighbor to A and a neighbor to B, then it is very likely in real world networks that A and B are going to be neighbors of each other. That's the clustering coefficient, is what fraction of those wedges close to form triangles in the graph structure. And so you have lots of low degree vertices, but incident on these low degree vertices, you have lots of triangles. And you can see that this is true. Here's a couple of real world graphs where we show how many triangles are incident on low degree vertices. And so you can still see we have plenty of the low degree vertices have very high clustering coefficients. So this forms a kind of tension because overall the graph is sparse, but the neighborhoods around these low degree vertices are very dense. And our central claim is that you're going to need a high rank in your embedding if you want to represent this tension. So in order to show this, we wanted to see like if you had an embedding and generated a graph from that embedding, what kinds of graphs could you generate? So let's say that you had an embedding that was given to you by one of these models. And so what we're going to do is we're going to take the you have two vertices, u and v, they each have their own embeddings, and you take the dot product of their embedding vectors, and we're just gonna truncate it to between 0 and 1 and add an edge to a graph with probability equal to that dot product. And hopefully if the embedding does a good job of capturing the graph structure, then the graphs that we get by generating this for overall such pairs in the graph is going to look like the graph we started with. What we show though, running low on time, what we show though is that if your dimension is small, if D is much less than like n over log squared n, you cannot generate a graph that is both sparse and has many triangles. You need a dimension that is very, very high. N over log squared n is very large. It cuts against the general belief that there might be like constant dimension or log n dimension embeddings. And so skip through this quickly. We show this with some experiments where we generated graphs according to a bunch of different embedding methods. If you look at the blue line in these plots, this shows, so the degree of the vertices is here, and then this is how many triangles are incident on vertices of that degree or less. You can see that all of the embedding methods we considered don't generate any triangles on vertices of degree less than 10, but in the real graph, there are plenty of triangles on vertices of degree less than 10. They do get overall the number of triangles right if you look at the upper right-hand corner of these plots. But the low degree vertices are very important. It's the vast majority of your graph, and it's not creating the kind of structure we'd expect to see among these. Then I'll quickly go through this. So if your downstream task is you're trying to predict, you have two vertices and you want to know, do these two vertices belong to the same community or not? And you have some ground truth labeling of community structures. We looked at a couple different approximation kernels that people can use. And we showed that these, although it might be possible to overcome the problems with triangles we saw before by using different kernels, these methods tend to be very unstable, that they're very sensitive to small changes. If it's a little bit of noise in the graph, like wildly changes what the predictions are. And so we do some evaluation of this. We have real world graphs, or actually this is a synthetic graph, where we try to do this task. We pick two vertices and we say, are they in the same community? And we train a model using NetMF embeddings and Node2Vec embeddings, and a model that just uses other structural features of the graph that are not embeddings. And we show pretty consistently that the non-embedding method outperformed the embedding methods. And so let's go quickly. I am out of time. I'm just going to say that, yeah, the task of like how do you translate community structure in a graph, these triangles on low dimensional models, needs a lot more thought in the community.
Thank you very much, Andrew.
Try to put us back on time.
Yes, so one takeaway message is that, so in real world networks, so you observe that we have many low degree vertices that are adjacent to many triangles, and this cannot be really captured by embedding methods, right?
Correct.
And I guess an obvious question is how to fix it, which you mentioned yourself, this needs more time.
Yeah,
right.
So like we looked specifically at these low rank factorization methods. There are a few like purely GNN methods that don't take this paradigm. And in our experiments, it's inconclusive if they're really doing much better. There's a lot of variables to consider there.
Yes, this would be a great question for the KDD community, for sure.
Yeah.
Thanks again.
Thank you.
Okay, our next speaker is Tianlong Chen. Tianlong is a third-year PhD student at the University of Texas at Austin. And his research mainly lies in building accurate, robust, reliable, efficient, automatic machine learning system. And the recent focus is extreme sparse neural networks with undamaged, trainable, trainability, expressivity, and transferability. He's a recipient of IBM PhD fellowship. And Tianlong wants to talk about lottery ticket hypothesis today for us. Tianlong, please go ahead.
Thank you. Thank you for the nice introduction. And I'm going to share my screen and to see whether everything works well. Okay, can you see my screen? Is it in the presentation mode?
Yes.
Okay, thank you. Hi, everyone. Thanks for the nice introduction and the invitation. I'm Tianlong Chen from ECE UT Austin. Today, I'm going to share my recent work, the lottery tickets hypothesis in gigantic pre-trained models. This work is also credited to my collaborators. They are from UT Austin, MIT, IBM Washington AI Lab. So pruning is like widely studied in the deep learning field. Dozens of pruning algorithms are proposed to pursue the machine learning efficiency. And to better understand a pruning algorithm, we need to answer following questions. For example, what to prune? If we want to prune entire substructures in the network architecture, it will lead to structure pruning. If we want to eliminate some unnecessary elements in the model weight space, it will lead to unstructured pruning. And another question will be how to prune your model. So basically, it will respect to certain criteria. It can be like magnitude-based, gradient-based, or learning-based, or information theory-based criteria. The next question will be, how often do you prune your model? So basically, you can perform like one-shot pruning, or you can do it iteratively, gradually shrink your model capacity. And for me, I think the most important question will be when to prune your model. So most of the previous literature, they study like after pruning process, which is a post-pruning technique. And other researchers study like during training pruning by leveraging some like L1 sparsity regularization or some optimization framework like ADMM. And I think one of the most recent trend of research in pruning, they study like the before training pruning. I think it is most interesting. Since if you like identify your mask before training, then during the downstream trainings, you can both enjoy the training and efficiency, training and inference efficiency. So in today's talk, I will mainly focus on unstructured magnitude iterative pruning and try to identify the sparse network before training. And I guess most of you may be perhaps familiar with this terminology, the lottery ticket hypothesis. This is a fantastic work done by Jonathan Frankel and Michael Carbon. They wins Best Paper Award in the 2019 iClear. And their paper gave a very good definition about the desired sparse networks. Like a randomly initialized dense neural network should contain a subnetwork that is initialized such that when trained in isolation, it can match the testing accuracy of the original network after training for at most the same number of iterations. So you can imagine that you first train an original dense model, then perform pruning to reach extreme sparse subnetworks. If this kind of subnetworks can satisfy the following conditions, first one, it have only a few parameters, maybe like 2% to 5% of its dense of the dense model. And the second one is very important. It can training from scratch, training from the beginning, which means it have a good trainability. Third one is that it needs to match the accuracy or achieve an even better accuracy compared to its dense counterpart with like a few training iterations. If the subnetworks satisfy this condition, we call it a winning ticket. So this very helpful purchase makes winning tickets become very intriguing, as long as we know which kind of subnetworks is winning. Okay, to explore this kind of subnetworks, in the original paper, they use iterative magnetic pruning to find out or identify the critical connectivities. Basically, they train the dense model to converge, then perform pruning. After that, they rewind the weight of sparse model to the original initialization, W0. And you will repeat this procedure again and again until to reach the desired sparsity. And in this paradigm, you can see that it will require a lot of rounds of pruning, training, pruning, and retraining. So it is tedious. Although it is tedious, it is still super amazing, because previous literature point out that sparse networks from model compression or pruning are not very friendly for gradient-based optimization, which means the sparse network have a highly degraded trainability. However, in this paper, the loudest tickets hypothesis point out that if you carefully rewind the weight of sparse network to its original initialization, W0, the sparse network can maintain an undamaged trainability compared to its dense counterpart. Okay, in order to explore this very interesting phenomena, a lot of papers are coming out recently. Due to the limited time, I only want to mention one very relevant paper, stabilized the louder tickets process. This paper point out that in order to scale up louder tickets process to large models on large data set, it is necessary to take a weight rewinding technique. So weight rewinding basically means you need to rewind the weight of sparse network to some early epoch of your training stage, rather than the random initialization. So early epoch can be first epoch or second epoch, or maybe the fifth epoch of your model training. And this basically provides the foundation of our research. And back to our story, we want to draw the louder tickets from the large pre-trained models. Since pre-training has already demonstrated its powerful effectiveness in diverse domain. For example, support model in NLP, or the SimClear model, self-supervised SimClear Moco models in the computer vision domain, or the GPT-3 models from OpenAI. Okay, so why we care about this? Basically, we have a lot of motivations from diverse perspective. For example, for the methodology perspective, we are curious about that, whether this pre-training can eliminate the requirement of weight rewinding and to directly scale up the louder tickets process. Because pre-training already provide you a very sweet starting point for the further training, right? So it may helpful to avoid this ad hoc weight rewinding technique. From the practical perspective, since pre-training and transfer learning scheme becomes the central paradigm of computer vision, NLP, or other domains, so it will be very beneficial if we can bridge the huge pre-training models to the real-world tiny machine learning field. And we leverage the louder tickets process. So in other words, ideally, we want to use the louder tickets process to draw some critical extreme sparse subnetworks from the pre-trained model. And we hope this kind of sparse model can universally transfer to all downstream tasks while maintaining the undamaged performance. If yes, the extraordinary cost of pre-training or of finding louder tickets can be amortized by reusing such kind of intriguing extreme sparse pre-training subnetworks. Okay, to offer you a better picture, let me go to the over results. So the first subject I want to present will be the BERT model in the NLP domain. And I summarized the findings in these slides in a bullet list. So we in this paper we focus using unstructured iterative magnitude pruning, and we want to identify the matching subnetworks with undamaged performance on the multiple downstream tasks. So what is a matching subnetwork? Matching subnetwork means it can match or even surpass the performance of its dense counterpart. And we can indeed find it at 40% to 90% sparsity in the BERT models. And we also show that this kind of funded subnetworks can consistently outperform other subnetworks found by random pruning or random reinitialization or other method. The most important point is that we show the subnetworks at least over 70% sparsity on the pre-train task are capable of universally transferring to a lot of downstream tasks, meantime maintaining the undamaged accuracy. So these findings support our assumptions or our motivations in the previous slides that we want to identify the intriguing pre-train tickets, and it is extreme sparse, and it is maintain undamaged trainability compared to the dense model. Okay, let's have a quick scan of the detailed results. So for the first point, we show that we indeed find winning tickets in BERT on the diverse downstream tasks, and such kind of winning tickets can surpass other random pooled or random reinitialized subnetworks. And also the important thing is that such funded pre-trained winning tickets can transfer well across diverse downstream tasks. And I also want to add one comment here. We observe that the transferability of funded pre-trained tickets is loosely correlated to the data volume you use to find the tickets. In other words, if you use more data to find the pre-trained tickets, it may have better transferabilities. At least it is validated in the BERT NLP domain. Okay, more findings are also provided in our paper, and now I want to switch to the second subject of today's talk. Is we want to study computer vision pre-trainings. I would say it is more difficult and subtle point than the BERT pre-training, since in the computer vision there is not a dominant pre-trainings. Like for example, supervised ImageNet pre-training, like some self-supervised Moco simply or Sway for pre-trainings, all of them are very powerful and have its own properties. The second reason is that in the computer vision downstream tasks, they seem to require some opposite property. For example, for the classification, it prefer a pre-training which is more invariant to the object shift. However, for the detection and segmentation task, it will require the pre-trainings to be more sensitive to the object shift, since it want to detect and segment the object from the image. Okay, so such kind of properties pose more difficulties in the study of pre-trainings. And our paper try to also find this intriguing, transferable, extreme sparse subnetworks on the pre-training model. So basically, we also summarize the findings in the bullets in this slide. First two bullets tell us we can indeed leveraging supervised pre-trainings or self-supervised pre-trainings can find the matching subnetworks on diverse downstream tasks, like classification, detection, and segmentation. And fortunately, this is like consistent to the findings in the NLP BERT paper. And the last point is that we also found that pre-trained tickets at like 60 or 70% sparsity can universally transferable to diverse downstream tasks across different data sets, also across different kind of tasks, including like classification, detection, segmentation. Meantime, it will maintain nearly the same accuracies. Okay, besides the numerical results, I also want to share some unique properties of pre-trained tickets in the computer vision domain. For example, we show that the different pre-trainings will yield diverse mask structure, and they also shows diverse perturbation sensitivities. And the one most important, most interesting point is that if you focus on the figure 7, we can observe that the pre-trained tickets indeed show a strong structure patterns, although it is funded by unstructured pruning. So such kind of structure patterns can enable such pre-trained tickets have a large potential in the hardware speed up. Okay, and we also find that pruning from large pre-trained models can produce better transferable matching subnetworks, as we showed in the figure 9. And in the end, I want to like summarize today's talk. So basically, our work is try to bridge the powerful, huge pre-training models to the real world, like a very useful, practical, tiny machine learning field by leveraging lottery tickets. And we like introduce a new regime. First, we pre-train a large model. Then we find its lottery tickets or matching subnetworks. After that, we deploy and fine-tune it on diverse downstream tasks. Okay, in my last slide, I want to like connect to some hardware saving dots. So first point is that although a lot of lottery tickets papers explore unstructured sparsity, but fortunately, recent library shows that extreme high unstructured subnetworks can also be accelerated on some special platforms like smartphone processors and so on. Second point is that it is also like hopeful to finding winning tickets at structured sparsity. Honestly, we are working on it and hope we can share with audience in the near future. And the last point is that the benefits of appropriate sparsity, I think it's beyond the training and inference efficiency. Since appropriate like sparsity regularization can probably improve the data efficiency or alleviate the overfitting or catastrophic forgetting. And we also conduct related researches, and you can find us detailed papers in our website. And thank you. That's almost that's all the things I want to present today. Thank you.
Thank you very much. We can shortly like prune these huge neural networks and use them instead of the billions of parameters that we are training now. Cool. So I think we have a quick question here. Can the pruning method take into account the downstream tasks if they are known beforehand? And I also had a relevant question into this, I can combine it. So you showed that this pre-trained pruned network, the pruned network that you find from pre-trained larger networks, they can be applied, can be transferred to different tasks. Do you think there might be a benefit in pruning further and then grow some task-specific connections?
Yeah. Okay. Let me answer the second question first. Yeah, I agree, and it will be super interesting that because pruning pruning at the pre-training maybe like offer you a initial mask, and it can be transferable. But you can also like do the further pruning or do the further grow to like explore some task-specific connectivities combined with the universal mask. It may be that demonstrate like a better performance on downstream tasks. I totally agree. And I think it's a very interesting directions related to like dynamic sparse training or other stuffs. Yeah. And for the first question, sorry, could you repeat again for the first question?
Definitely. So can the pruning method take into account the downstream tasks if they are known beforehand?
If there is a sorry, I still didn't got the term.
So the question is in the chat if you want to read.
Okay.
So you can check out the chat, but it's like, if you know the tasks beforehand, can you prune better?
Oh yeah. So yeah, it is very related to the second question. Thanks. So basically, so far we assume that we do not know anything about the downstream task informations. But if we can provide some like some downstream task informations for if we pre-know, then we can like do some like refine over like masks to like maybe perform a further pruning or perform a further grouping or perform a further modification to make the mask be more suitable to the downstream task. I think it is possible, and I think it's very interesting. Thank you.
Thank you very much, Tianlong.
Cool. Thank you.
Our next speaker is Yasaman Bahri, and it's my great pleasure to introduce Yasaman. Her present research program is on the workings of machine learning system with a current focus on and bridge the gap between practice and theory. Yasaman is a recipient of the NSF Graduate Fellowship and Departmental Citation Award in Physics from UC Berkeley. So Yasaman wants to talk about understanding neural scaling laws. Welcome, Yasaman.
Thank you for the kind introduction, Baharan. And can everybody hear me and see my screen? Okay.
Yes.
Thanks. So I'll go ahead and get started. So today I wanted to tell you about work on trying to understand neural scaling laws, what in the literature has been started to be referred to as neural scaling laws. So the motivation for this work is that empirically, recently, kind of in the domain of very large neural networks at labs like Google and OpenAI, it's been observed that neural network performance obeys very smooth, often power law trends as a function of simple variables in the problem. So this includes the data set size, model size, and the amount of compute, as any one of them is increased. And you can see this in the plots below over here. This is taken from one of the scaling law papers from OpenAI on large language models, where you can see that there's at least empirically, a very nice clean trend as a function of these three variables with particular with particular values for these exponents. So the motivation for this work is, can we better understand why these trends emerge empirically, and in particular, what features of the data and the models determine the exponents? And this ties quite a lot. This ties in with a lot of work on driving bounds on generalization performance. Here, we're going to try to kind of bridge the gap between theoretical models that might be reasonable in practice, as well as some limits in which we have a full handle on the problem, and then also measurements that we make empirically to see if we can actually have some kind of predictive theory for what's going on. We'll see that in some regimes there's a universal exponent, meaning kind of regardless of the problem, the details of the problem, the data and the models, you get the same exponent, and in others it's problem dependent. As I mentioned, we'll start kind of building some intuition from a very restricted setting in which we have a full theoretical handle on the problem. And that's helpful for kind of generating some hypotheses for what might happen in the more general setting, and also help us kind of tie in to that more general setting, either theoretically or heuristically. And as you'll see by the end of the talk, some parts of it will try to just empirically test the connection. We have some predictions for the exponents, and we'll try to relate that to more microscopic quantities that we can measure in experiments. So the setup for this problem, we're going to be focusing mostly on two quantities, just the amount of data that we have, the size of the training data set, and P, the number of model parameters. For this work, we specifically focus mostly on just parameters that are coming from increases in layer width rather than depth for neural networks. And the reason we do this is because there's a much larger body of work studying what happens as you make neural networks wider, and that's where we have more of a theoretical handle. So everywhere here where you really see me write number of model parameters P, you should really be thinking of it as really just the layer width W. And the quantity we'll be looking at is the test loss L as a function of the amount of data and the number of model parameters averaged over draws of the data set and random initialization, where here F hat is the predictor that you learn on the training set of size D. In terms of notation, I'll be referring to exponents alpha D and alpha P for the data set and model size scaling. And you can think of them as parameterizing these power laws, the leading order term in an expansion for these power laws. So if you just, for instance, looked at the test loss as a function of data set size for some value of the model parameters, could be finite or could be infinite, you would have in general could be some complicated function, but we'll see both in some of our more restricted settings and then also empirically that kind of the leading order terms tend to have the following form. They look like a constant plus some power law plus other things that are in principle higher order. So we're just kind of focusing on the leading order power law that one would get. And so the exponent for that I'll refer to as alpha sub D, and similarly for model size exponent, I'll refer to it as alpha sub P. In general, these constants, both the kind of limiting constant and this coefficient, they're quite interesting to study. And I think more work needs to be done to kind of understand how those vary with the problem. But our focus in this setting is just going to be trying to understand the exponents. So investigating this question, we managed to come up with as a zeroth order kind of result, a classification for exponents based on their origin. So I'm going to try to convince you that roughly speaking, there's at least a coarse classification of the types of exponents you get into two classes. One is what we termed the variance limited regime, and the other we termed the resolution limited regime. So the variance limited regime, the origin of the term comes from kind of variance or fluctuations as you smoothly approach a limiting value. And this is a regime where we have much more of a theoretical handle, both in the restricted setting and the more general setting. We can show that how the exponent behaves, and we find that in this variance limited regime, you kind of always get an integer exponent equal to 1 asymptotically, whether you're doing data set or model size scaling. And I'll say more about that. There's a different regime which we termed resolution limited, in which the main idea is that you have these two variables D and P. And to be in this regime, what sort of effectively has to happen is that one of the variables is much larger than the other, and you kind of think of it as being taken to infinity. And what you're doing is studying scaling as a function of the other variable, the smaller variable. And so in this setup, what's happening is that the smaller variable is effectively the bottleneck for your problem, whether that's amount of data or its number of parameters. And we kind of posit, again, starting from this restricted setting, but trying to build a more general picture, that what's happening in this regime is that you're increasingly improving your resolution of some manifold. So you've kind of identified what the manifold is that you're trying to learn in your supervised learning problem, and you're just using those extra, as you add data set size or parameters, you're just better resolving this manifold. And this is what gives rise to the non-trivial in general, like non-integer exponents that depends on the problem setting. By the end of the talk, we're going to try to relate the exponent to measurements on the actual manifold, but we're going to build up to that in a couple of stages. So to give a little bit more detail on this categorization, and just kind of flesh out a bit more of what I said on the previous slide. So the idea is that in the variance limited regime, you fix one of D or P, and then you let the other variable grow, and you're setting scaling as a function of that variable, which is the larger variable. So for instance, you might fix the amount of data, take a model size or effectively model width that's much larger than the data set size and study model scaling. Or you could fix the model size, take the amount of data much larger than the model size and study data set size scaling. So if you were going to kind of categorize the various regimes based on this classification, in this 2x2 table, what you would get is basically the variance limited regime in terms of this categorization would lie on the diagonals of this problem. So for instance, as I mentioned, if you have an under-parameterized problem where you have more data than parameters, to be in the variance limited regime, you would be studying data set size scaling. So P is fixed and D is large, and you're studying scaling with D, and vice versa down here. And now resolution limited is basically the off diagonals of this 2x2 block. So take one of D or P to be effectively infinite or essentially much larger than the other variable, so it's no longer a bottleneck. And then examine scaling as a function of that smaller variable. So for instance, fix the model size to be quite large. You have an over-parameterized model, and you're going to study data set size scaling as you add data, or vice versa. So if it's helpful, I'm going to show this. It's helpful maybe to remember this 2x2 block, because I'm going to show a bunch of plots throughout the next few slides that basically match to this 2x2 table, where we study we put ourselves either in the variance limited or the resolution limited regime, and then look at exponents. So the support from this is theoretical support for this categorization, and more generally in the resolution limited regime, where we have non-integer, an exponent that's different from 1, we're going to try to tie that to more microscopic quantities. The theoretical support for this comes from, in one case, this is the setting where we have a full handle, a student-teacher kernel framework, where we have a teacher model that generates data of a particular form, and then we have the student kind of neural network or linear model in this case, just learn the data generated by the teacher. And here we have explicit derivations we have an explicit form for the test loss, which we can kind of study and look at the asymptotic contribution and also relate it to properties of a kernel function. So the kernel function in the setting itself will have, if you were to look at its spectrum, it would have some power law behavior, and we're actually going to relate that power law exponent to the exponents that appear in model and data set size scaling. In this particular setting, we also obtain a particular relation between how model and data set size scaling relate. So it turns out there's an equality between the exponents, which actually ends up holding a little bit outside of this immediate framework also, which we test empirically. Now, going on to the more general setting where we just have neural networks that are in a feature learning regime and you give them arbitrary data, we can again, we use that to kind of formulate our thinking about these two regimes. For the variance limited regime, again, we can formally kind of prove that there is such a regime and that you get integer exponent 1. For the resolution limited regime, we don't have kind of a formal proof. What we have is kind of a heuristic model. And if you believe that model, then you can kind of claim certain things which we test out and relate to kind of microscopics of this manifold that I mentioned. So here's the 4 regimes, first of all, shown empirically. This is in just across many different settings. These are all neural networks under various conditions. So this 2x2 kind of plot you can think of as being the analog of the 2x2 table that I showed earlier, where basically we have the variance limited regimes on the diagonal and the resolution limited regimes on the off diagonal. What you see in the variance limited regime is that for these different problems, so whether we're increasing amount of data or we're increasing the width, and we have different types of data sets where we're doing supervised learning, ranging from CFAR 100 all the way down to the teacher-student framework. We have different neural network architectures with different choices of nonlinearities, and also different loss functions. So basically everything here is kind of cross entropy with a fully connected model, unless specified otherwise. And these here actually are not labeled, but they're wide resonant models. But you see that in the variance limited regime, at least empirically, you get pretty good agreement with this prediction of an exponent equal to 1. I want to maybe remind you that, again, what we're doing here is setting the exponent. So we're not studying the asymptotic value that you approach. So we've subtracted off here the asymptotic value at infinity. So note that the y-axis here is a bit different in this setting. But essentially the main takeaway is that on the diagonals of this plot, you see that the exponent is pretty close to 1 empirically. In the off diagonals, you see that the exponent is far from 1, and in general, it's some number that changes with the problem. It changes with the data set, and in general, also with the model. Now, here, what you see happening here in terms of the empirics, you start to see deviations from these power laws here and here, and the reason for that is just a practical one. So just as a reminder for what's being kind of what the setup here is, for instance, for this setting here, when we're in the resolution limited regime studying with scaling, that means the data set size is large. We're studying scaling with width. And what we do in practice really for these measurements is that we really have a finite data set size and we don't have infinite data. So at some point we kind of approach this regime where width is on the order of data set size. And that takes us away from this resolution limited regime. If you're familiar with double descent, what effectively would happen is that's sort of the double descent region. And after you cross that, so here what you're basically approaching is kind of the double descent regime. And then after that, as you make width even larger than data set size, what ends up happening is that you approach this variance limited regime. So basically what we're doing here is kind of studying both sides of the double descent kind of regime, but not capturing the double descent regime itself. So either, if you're familiar with the literature on that topic, kind of both to the left and the right of the double descent kind of peak. Okay. So a few slides now on just the concrete case where we have a theoretical handle and a full understanding of what's going on. It's the simplest setting where we have MSE loss. We have a teacher model that is constructed from fixed features F sub m, potentially infinite, and we just have kind of parameters, random parameters on top of those fixed features. This is how we generate labels for this teacher problem. And then the student model, which is the one that's learning, has these learnable parameters. It's a linear model, so it's learning the thetas, and it's constructed again out of features that themselves are projections of the teacher features. So there isn't much of a model mismatch between the student and teacher setup over here. And in this setting, basically we can write out everything in terms of an expression for the test loss in terms of the various gram matrices that you could construct from these fixed features evaluated on some data X, where X is drawn from some distribution. And then you can focus on the leading order terms. I won't focus too much in this talk actually on the variance limited exponent, but just to say that here, again, you could identify the leading order behavior, and it comes from looking at the fluctuations of the finite size covariance matrix about the population covariance. In the more general setting, there's a more general setup. It's not necessarily the covariance matrix that is approaching the population, but there's a different way to formulate it that also gives rise to this exponent equal to 1. Now, in the resolution limited regime, what we have to do is analyze these expressions that are written in terms of these covariance matrices constructed from these random features evaluated on data drawn from the distribution of X. And generically, it's a fairly good assumption, and I'll show some support for this, that for unless you kind of specially construct your kernel otherwise, generically, kernels tend to have power law spectra. With exponent, with some exponent. So here, if I label kind of the exponent of, let lambda I be the ith eigenvalue of the kernel matrix or the covariance matrix for this problem, it has an exponent which I'll label as 1 plus alpha k, or basically it's governed by alpha k. And if you put this into the expressions, then you get out kind of power law scaling for data set and model size. And the exponents for those things depend directly on the exponent for the kernel spectrum. So the faster that the kernel spectrum decays, the faster you get, the better data set size scaling you get, and the better model size scaling you get. And in particular, in this setting, we have a duality, meaning there's, it turns out that these two exponents are exactly equal because they're governed by the kernel. Basically, the same object is coming up in both calculations. One is sort of the dual of the other in terms of how it's constructed, but that leads to this fact that the exponents in this setting are the same. And so now here's kind of the same 2x2 plot just shown for this student-teacher setting. So it's just a special case of the more general empirical results I showed before, but again, we kind of verify at least that roughly, again, this variance limited scaling gives exponents that are reasonable with our predictions. And likewise, in this resolution limited regime, we get exponents that are different from 1. What we're doing here is in order to be able to vary kind of across different values of the exponents, we varied the task. So this is taking MNIST, for instance, and downsampling it. And you'll see that downsampling it basically has an effect on the dimensionality of the manifold that is coming into this problem. That dimensionality affects kind of the kernel and the way that the kernel scales, and directly affects the exponents. So basically, you can see that as we pool MNIST by different amounts in this student-teacher setup, where MNIST is just here serving as the data X that is going into the teacher model, and then we train on in the student model. As we vary kind of the task by pooling by different amounts, we see that in the variance limited regime, we don't change the exponent, but we do tune it in the resolution limited regime as we believe we should, because we're changing the kernel, the scaling of the kernel eigenvalues, and also this manifold that I mentioned, the dimensionality of it. So this is kind of just to check on the exact results in the setting and that it holds empirically. Now we want to dig a bit deeper into the fact that we kind of posited that there was this power law spectrum for the kernel eigenvalues, and that was what was giving rise to these exponents. So here we test that directly. In this plot on the right, what you see is that the kernel spectrum, again, by varying this problem by downsampling MNIST by various amounts, you can change how large alpha k is. So kind of that's the sweep from these blue to red lines. And as you do that, you generate different values for alpha d as well as alpha p. And this plot over here shows that basically they're all roughly in agreement. alpha p is equal to alpha d, and it's roughly equal to alpha k, kind of within the numerics that we're looking at. And so that's sort of a check that there's this three-way relationship between the kernel exponent, the data set size exponent, and the model size exponent, and that they all happen to be equal in this setting. Now, in a couple slides, I'm going to try to relate this to the dimensionality, relate the kernel spectrum, or I'll talk about the effective dimensionality of a manifold. And this is sort of a special case of that, because the kernel spectra generically, at least we think that there's a relationship here between this exponent alpha k and the dimensionality of the manifold. And one way we can't prove that exactly, but what we can do is give kind of a bound for how the power law scaling of kernel exponents on some d-dimensional manifold. And generically, it looks like this, given a certain amount of smoothness in the kernel. So the smoother the kernel, the faster the decay. And the smaller the dimension of the manifold, the faster the decay. Now, this is an upper bound, but given, again, a generic kernel, which is not, has no other specific features, no specific symmetries, the data is rather generic on that manifold, you sort of expect the bound to be saturated. And so that's why we think there's a relationship here in this setting, which is a special case of the more general thing where the kernel exponent and the effective dimensionality of the manifold are related. Now, here's just some empirics on a setting that is not the one that I described here. It's a little bit different. So here what we do is we just take pre-trained embeddings. So this is from an efficient net model that's pre-trained on ImageNet. And we use those pre-trained features to on CFAR10. So we kind of resize CFAR10 so that we can reuse these pre-trained features. And now what we do is we just train a linear classifier on top of this. So it's a linear model using pre-trained features with the real targets. It falls outside of the framework, the setting that I described previously, because now the targets are the real targets. They're not being generated by a teacher network. But again, what you see here, interestingly, is that you still get a duality between the data set and model size scaling exponents. So if I can draw your attention again to these off diagonals, the purple lines, here you see these are values for alpha p, and they're close to the values that you observe for alpha d. And similarly over here, alpha d and alpha p are approximately the same. And again, on the diagonals of these grids, you see the variance limited regime where you get an exponent close to 1. Now, here, these peaks that you see that come up when you do low regularization rather than optimal regularization are just artifacts from double descent. So it's exactly kind of the reason that I mentioned before, where the way this experiment is set up is you take a large amount of data, you're studying model size scaling, so you're increasing the width of the network or the number of features, and at some point you kind of hit the limit in which, or the regime in which P is on the order of D, which is where double descent starts to kick in. So that's when you're going to kind of cross the interpolation transition. And if you continue past that on the other side, eventually you'll hit the variance limited regime. So we're just working on one side of this here. And what we're doing is fitting kind of things on the left over here, and variance limited regime would be approached kind of on the right as you continue out asymptotically. Okay, try to speed up a little bit. So now I want to talk a little bit, or just give a little bit of the flavor of what happens in the more general setting. I won't go into too much depth about the variance limited scaling, just because I think kind of it's on a firmer footing, and also because oftentimes I think in practice we're closer to the resolution limited regime. But that's just to say that in the variance limited regime for this more general setting, we can show that as long as you have kind of a function that starts to concentrate around its mean in a particular way, that scales in a particular way with either the data set size or the model size, then that kind of gets passed on to the behavior of the loss function. And whether we're studying data set or model size, we can kind of figure out what this scaling for the function is based on what this other variable is. So for instance, for amount of data, it kind of comes from, for instance, gradients of the loss kind of concentrating, and that effectively results in the function concentrating in this way. For scaling with model size, we utilize results based off of recent kind of theory on the infinite width limit. So we know about these finite width corrections to infinite width behavior that's been studied before, and so we can kind of bootstrap that for this result. Now, the resolution limited scaling regime is one where we have less of a handle. And so now I'm going to try to kind of build a heuristic picture, or at least kind of a model that might work in practice for what's going on here. And it's supposed to be an intuitive model more. So I mentioned again that at a rough level, what's happening in the resolution limited regime is one of the variables is large, and you're studying scaling as a function of this smaller variable. So for instance, let's say the model is very over-parameterized and you're studying data set size scaling. This is a sort of picture that you're probably familiar with. What you can kind of picture is that as you add more training points, you kind of better resolve this manifold that you're trying to learn. So we also assume that we're working in an interpolation regime. So the learned function is matching the target function exactly at these D specified points. And they provide sort of anchor points on the manifold. If you kind of believe this and you worked asymptotically, a first naive guess that you would make for how the test error would scale is just by kind of Taylor expanding in the distance between, series expanding in the distance between a test point and its nearest training point. So let me skip ahead a little bit to this. So to just flesh that out a little bit more, suppose that you have these two functions, f and big F, the learned model and the target, which are analytic and expandable on this manifold M sub D. So these are assumptions. And also you assume that the loss function is analytic and minimized when F is equal to big F. Then imagine kind of, again, in this heuristic picture that you were going to calculate the test loss, the loss at a particular test point. You could imagine expanding about all the nearest training points or all the training points. And the series expansion would start, because of these assumptions, it would start at degree 2 in general. And if you believe this, at least it would suggest that then the thing that kind of governs, would dictate how scaling goes, asymptotically at least, is that it originates from the nearest neighbor kind of training distance. So as you add more data points, you kind of decrease this distance between a test point and its nearest training point. If that's the thing, that scales potentially in a particular way. And empirically, we kind of use those measurements to then try to figure out what the scaling for the overall loss would be. So to say a bit more, basically, this distance between a test point and its nearest training point kind of scales itself as a power law in the amount of data that you have, or in the number of model parameters that you have, in a way that depends on the dimensionality of the manifold. So this is kind of, you could show that this is true if you had some kind of in this simple picture where you have a manifold and you're just adding points to the manifold in a certain dimensionality D. You can also verify that it's roughly true, or seems to be kind of true, at least in the experiments where we tested it out, where there was, if you look at the nearest neighbor kind of distances themselves, they also obey some power law behavior, and you can extract an exponent from that. So that would give you, maybe make a rough prediction that if you could get kind of this distance scaling as a function of data or model size, then you would get a prediction for how the test loss kind of scales. And in general, as I mentioned, this starts at n equals 2. So the prediction would be 2 over d for the exponent. But for a piecewise linear function, so if you're doing ReLUs, for instance, generically, you expect it to start at higher order because that leading term kind of drops out. And so the prediction is that it would scale as 4 over D. So that's sort of, again, more of an intuitive picture where you series expand in the distances between points, and it just gives you a rough estimate for what you might hope to hold, at least asymptotically. That was this picture here that I mentioned when you study it as a function of data set size. And indeed, if you look at simple settings where you study student-teacher models, as you add more data, you do a better job kind of interpolating the true function. So for instance, here, this is a teacher function, which is this black curve shown on a one-dimensional slice in input space. And as you add more data, you do a better job kind of resolving that when you're working in this interpolation regime. So here are 2 training points at the very ends where you get perfect agreement. Now, what I wanted to say, and what is maybe more surprising, is perhaps this kind of manifold picture as you add more data is a bit more intuitive to you, or kind of ties into, I think, older work that where they derive generalization bounds, the literature on that topic. But what I think is interesting is that also kind of a similar picture seems to hold if you look at model size scaling. So here, now, again, resolution limited regime, you have a large amount of data, you're increasing the amount of the number of parameters. Why might it be reasonable that here also you're using these extra parameters to better resolve a manifold? Well, one reason you might motivate that, again, it's just kind of heuristic motivation in this setting, is just because you can kind of think of what, for instance, ReLU neural networks do, is they give you some piecewise linear function on the input space where, here that's kind of visualized here. This is showing just an input space where a ReLU network has kind of tessellated the input space. And the number of such points, the number of such linear regions, basically you have a piecewise linear function, and within each one of these kind of smaller areas, you have an exactly linear function. The picture is roughly that each one of these kind of provides for you a degree of freedom that you can use to perfectly fit on the data manifold. If you believe that, then it would suggest that, well, here the number of linear regions that you tend to find empirically, both at initialization and during the course of training, is actually much smaller than the worst case bounds that you would get for this quantity, and it tends to scale with the number of parameters rather than kind of in a way that's like exponential with the depth. And so if you kind of believe that as a measure of the degrees of freedom for your problem, and in particular, this is what happens when you fix depth and increase the width of the problem, then it's kind of natural to posit that perhaps what's happening when you have a large amount of data, so you're not data limited in any way, but you're adding model parameters, you're kind of better resolving this manifold. And what you're doing is kind of having roughly of order p points that you're fitting perfectly well. And so again, you would kind of, if you believe that, you would try to leverage that. You could give, again, a series expansion argument where now you, instead of D points where you fit perfectly, you have P points, and you would get a prediction for the scaling of the test loss. So indeed, we tried to kind of test some parts of this prediction in a real setting. So what you see here, this plot on the left is on the one hand, a measurement of the data set size scaling exponent alpha sub D, which we get by just fitting the test loss curves as you increase amount of data. And on the one hand, we try to make an estimate of the intrinsic dimensionality of this problem. So what is the dimensionality of this manifold that's being resolved? And part of the subtlety here, which I will kind of maybe touch on in my closing remarks, is exactly how you want to make that measurement or where you should make that measurement. For us, for various reasons, I can say what we did was we looked at we estimated this intrinsic dimension by looking at the scaling of nearest neighbor distances from the penultimate layer of the trained network. So say you take the penultimate layer, you look at the activation functions, and that's in some space. And then you look at how the distances between those points kind of scales as you increase the amount of data or you increase the number of model parameters. That itself has some power law behavior. And so you use that as a estimate. Basically, it's this kind of thing here that we're trying to estimate, x test minus x hat train. You try to measure that independently and then compare to the exponent you actually get by fitting to the test loss. And so what we got was basically this plot over here. It's comparing alpha d to, it's comparing 4 over alpha d to d, or what I said over here was that basically alpha d is equal to 4 over d. That's like the leading order prediction for a ReLU network. And we get good agreement for the teacher-student setting and less great agreement for other settings. So these other models are just CNN models trained on other data sets. There's some reasonable agreement between them, but they don't fall exactly on this line as we might have hoped. And also these hollow circles are the wide ResNet models. So the agreement is best in this teacher-student setting. I can say more about why we think that might be true. Here's a similar plot from previous work by our co-authors on basically the same measurements, but looking at model size scaling. So again, here now it's plotted a bit differently, but it's 4 over alpha p. So again, the prediction here would be that the scaling would go as p to the minus n over d, where n equals 4. And so here again, in the teacher-student setting and for a bunch of different data sets, there was reasonable agreement with that prediction. And they attempted a measurement of it for GPT actually. And you can see that it's not perfect with the 4 over alpha line, but it's kind of within a reasonable range. I think I may be almost out of time, but I will just flash a couple other empirical observations that we made, which was basically how much the exponents tend to depend on the changes in the input as opposed to changes of the task. So here what we did was just a first experiment where we superclassed CFAR 100. So we kind of varied the number of classes in the problem from 100 to 5 by reorganizing into these superclasses that are based on kind of the semantics of the underlying classes. And what we found was that the exponents roughly stayed the same. Whereas if you take a problem and you change the inputs by quite a lot, say by adding noise to the problem, just to the inputs, we found that the exponents were a lot more sensitive. So it kind of maybe suggests that some of these exponents, and in particular the measures of this effective dimensionality D, are more susceptible to the inputs than they are to the targets. And maybe that what's sort of effectively happening again in supervised learning is that you're learning to model the input manifold rather well and maybe doing some kind of task-specific modeling at the very end because of kind of greater susceptibility to changes in the input as opposed to the task setup. But again, this was a very kind of just a very particular setting of superclassing a specific classification task. So kind of in summary, I walk through how we think we have a categorization of exponents that helps, I think, researchers think about which regime they're in and what to expect for scaling. We gave some relationships to kernel spectra and duality, and the duality seemed to hold even outside of the setting in which it was exactly derived. We saw that there's kind of basically, of course, a cursive dimensionality that sets in, which is maybe not surprising if you think of it for sample complexity, but maybe it is a bit more surprising that it also affects model size scaling, at least when you're in this resolution limited regime. But again, this effective dimension is quite small in practice. Kind of the numbers are of order 10 rather than, the ambient dimensionality for for the problem may be thousands, 3072 or 784, but the effective dimension for that problem that would predict the exponent is much smaller. One limitation is that all of these results are kind of, many of them are asymptotic. We don't really have a handle on the intermediate regime. So when there are crossovers, like data set size on the same order of model set size, or if the values are quite small. And also there is a limitation that this resolution limited regime in beyond the kernel setting, so in feature learning, was based off of a manifold picture, which probably kind of could benefit from further investigation. I'll just close by saying that I think that more broadly, scaling it's good for us to know as researchers which parts of a problem can be remedied by just increasing scale and which cannot. So there are basically kind of separating out problems or solutions and also approaches and good solutions into things we can achieve just by further scaling in a clever way, perhaps, and things that we kind of can't achieve by scaling alone. And I suspect that a large number of kind of results right now in the empirical literature, even if they're not reported that way, may kind of just be due to changes of scale in the problem, as opposed to fundamentally changing, kind of bringing in a new approach, even if algorithmically we kind of hope to design things that are like that. So I think that, one thing in machine learning, just as a part of reporting, is that when we're changing the data set size or the model size, and we're trying to compare apples and oranges across different papers, what we also want to be kind of modding out in this problem is what the gains would be as a function of scale. So maybe your problem, maybe your algorithm doesn't do as well at a particular scale, but actually it doesn't quite better. It improves much more when you scale it cleverly, and sort of knowing what this buys you and how to predict it, I think seems important for research. And then there's another axis, as I mentioned, of problems that cannot be solved with scale alone. And it's not clear exactly how to divide these. I think some of the more interesting or hard to predict and hard to model theoretically aspects of this problem kind of show up in these papers from OpenAI on GPT-3, where at least at a certain level of scale, they get behavior that they would call emergent setting in. So for instance, the fact that you can do kind of higher digit addition arithmetic as you move to regimes that are large enough in terms of model size, and similarly, that your in-context kind of training abilities changes quite a bit, again, as a function of model size. I'd like to close there and just acknowledge my collaborators with whom this work was done, and thank you for your attention.
Thank you very much, Yasaman. This was a great talk. So I would skip the questions for the sake of time, and I would just start the panel if the panelists can perhaps turn on their videos. We can just start the panel, I believe. Okay, great. So I would do a very quick introduction. So we have James Zhu. James is an assistant professor in Stanford University. We have Martin Wattenberg. Martin is a professor in Harvard University. He is also part-time in Google. We have Yasaman Bahri from Google Brain. She's a research scientist from Google Brain. We have Harmanpreet Kaur, which is a PhD student from the University of Michigan. And we have David Madras, which is another PhD student from the University of Toronto. Thank you all for being with us today. So this panel is covering the last two sessions on theory and fairness and transparency. So I want to ask with a general question about the theory. I think I would start with Yasaman. So Yasaman, where do you think we are in terms of the theory? So I guess most of the theory, or a lot of the theory that we have, are limited to either two-layer networks or infinite width or very large ones. So where do you think, how do you think we are making a progress? Are we doing well? What are the limitations? What are the challenges we are dealing with, and so?
I do think that we're making progress reasonably well. I think even in theory has started to move away as far as I've kind of followed from, for instance, setting infinite width limits to trying to capture the feature learning regime. I would maybe classify or categorize again theory into two different areas. One is trying to have kind of convergence guarantees for algorithms and just guarantees in general. And I think that traditionally, like this is the most important kind of, I think part of theory and kind of the zeroth order thing that one would want to do. And I think I managed to only catch part of Jason Lee's talk, but he kind of suggested he has a number of interesting results on this front. I think a lot of progress is being made there. I will maybe mention that because this is partly some of my own interest, bridging theory and empirics, where you kind of, maybe you're not, you have some guarantees, but that doesn't necessarily tell you how mechanistically things are necessarily working. And that's something that you kind of might have to figure out with some back and forth between theory and experiment. And there you might not want, you may actually gain a lot of traction just by having effective models, not necessarily things that you kind of derive fully with pen and paper. Because there are many things that, for instance, empirically may hold that you wouldn't think to kind of derive again with pen and paper. I can give you an example that comes to mind recently from a lot of a nice literature on distribution shift from some of the folks at Berkeley, where they find kind of relationships between out of distribution, in distribution kind of performance that, again, I would view as sort of empirical laws that are very well obeyed rather than things that are derived with in that kind of formalism of traditional learning theory, or would be hard to derive mathematically. So I think if you would like theory to kind of encompass all of those things, or kind of our understanding of machine learning to encompass all of those things, some parts of that are also require kind of back and forth with the experiment. I think there's progress being made on all fronts though.
Okay, so I want to follow up on this question with James and Tianlong. So we usually talk about larger models, larger data, but I know, for example, James has a lot of work on what data points are more important, not just going with larger and larger, but perhaps we should be careful with data points. And Tianlong as well has some work on like what weights in the network are more important. Let's just not go larger and larger in terms of number of parameters. So perhaps you should be careful how we grow our models. So I wanted to also get your opinion on what do you think like about scalability? Like, shall we be perhaps more careful with our data and also our models? Or what is your opinion? Like, or is it like too difficult or?
Yeah, thanks. So basically, I think it's a very interesting question that how can we consider is like relationship between the data and the model together. And yeah, recent works in the ICML 2021, like several papers like post some investigation on this angle. So basically, they think like due to the to perform the model pruning, maybe it's not necessary to use all the data. It is also like makes sense, right? So they must be some like components or a co-set of the data set can be very helpful to identify the critical connectivities in the models. So I think in one of my previous paper, like we try to like mining some important samples which are more sensitive to the pruning. Basically, like we want to find out the samples which are easy to forget after the pruning, or which are hard to memorize during the training sparse networks. So we like take this kind of group of samples, just a few, maybe 10% or 20% of the entire data set to identify the sparse networks. And we indeed found that such kind of networks funded by a few data also like capable of like match the performance of the subnetwork funded by the overall whole data. And then another two like connected dots will be like due to the scale up the huge model parameters, but the optimization will still be gradient descent or the stochastic gradient descent, a very straightforward and easy gradient-based optimization. And such kind of things indeed just explore the shallow regions of the loss landscape, although the model parameters are exponentially increasing. And in this case, yeah, okay, this may be hard to connect with that. And in this case, I think that in the current scale of data set, it is always not enough to explore exclusively of the loss landscape. So yeah, just like this. Okay.
Yeah, I agree. I think this connection between the data and scalability of the model is super interesting. The examples, the papers that Tianlong mentioned, I think these are really interesting works. Based on our experience, I mean, we do have many settings where you actually do get better model and also more reliable models in deployments by using maybe a cleaner subset of the data rather than using the larger data sets, right? So since somehow adding more data actually creates more biases in these models. And also, I guess, in some of our experiences, that's oftentimes the most important kinds of data are collected by asking more active feedback from the end users, right? So if you ask the users to try to see, here's my current model, how would you tweak the data in a natural way that's where the model is making mistakes, right? So not fully adversarial attacks, like some of the other talks, but more sort of natural shifts, right? So collecting a few small amount of data from that sort based on this natural feedback ends up being quite informative for training the model. Even if it's small, that can be very effective.
Oh yeah, thanks, James. And it also reminded me one point. Let me finish the comments I just want to give. So yeah, exactly. Similar to the adversary training, especially for the adversary learning, for the generative adversary network like GANs. So they are usually require a lot of data volumes. And if you only pose limited data settings, the GAN model are easily to overfit. However, in the practice, GAN models cannot have a lot of quality or a lot of images. So in this case, to try to improve the data efficiency, previously we see a few papers to explore the sparse connectivities to treat it as a structure prior to regularize the adversary GAN learning. In this case, you can reduce the requirement of using massive of data set. So this may be another interesting goal to explore the relationship between data components and the model components via leveraging the sparsity regularization. Thanks.
Definitely. So let me also ask a relevant question from the transparency interpretability people. I know some panelists need to leave earlier. So there are usually two lines of thought. Some people believe that we need to design fair and interpretable models. Another line of thought is that let's take the existing models and let's try to interpret them or make them to produce fair representations or more transparent, by interpretability or visualization. So what do you think? So we have Martin, we have Herman and David here. What are your thoughts?
I mean, I guess my first impulse is that it certainly doesn't have to be an either or question. There has been very interesting work suggesting that sometimes by default, we'll see people use a model that is overly complicated, and it can be replaced by something very simple. Cynthia Ruby has many good examples of this. And the truth is, it's actually a phenomenon that happens all the time in practice. You try something, you finally make it work after lots of effort. And then frequently in the next year or two, you just discover all these simplifications. It's almost like a kind of pruning is taking place naturally. So simplification is possible. However, I think as I was trying to indicate in my talk, I also think we can make real progress in some of in interpreting things that people often talk about as black boxes. I don't think that is at all a permanent state of affairs. And in fact, there's no reason why we shouldn't be equally well trying to understand those, because the truth is today's black box models might be tomorrow's highly interpretable models, and we wouldn't want to give them up.
So David, Harman, do you have any opinion?
I agree with what Martin said, and that there's no either or here. But I also think that, instead of only thinking about, I guess, approaching it from how we can better represent these models, there's also thinking about how do users, see these models. So I think a huge component of this is going to be visualizations that users can parse. So no matter what underlying mathematical function you have, no matter whether it's, post hoc explanations or glass box models, I think we need more focus on how to present it to users so that we are actually able to engage them, because most of the time, the presentations of these models assume that the user is actually internalizing the information, which we found to rarely be true. So I think that's maybe not a direct answer to your question, but a related answer.
Yeah, I would say a similar thing. So I guess people don't always ask exactly that question with respect to sort of these fair machine learning models, but I think there's a similar thing to what Harmanpreet said, is that often like these models kind of exist in a larger within a larger pipeline and within a larger system, and there's end users and there's models that come before, and there's a bunch of automated things that happen before and after, and if you're interested in studying the bias of the system or of the model, or of impacts on various groups or whatever, just sort of tweaking, or I mean not necessarily tweaking, but even overhauling like the machine learning part of it is not always going to be enough to make the type of difference that you want to make. So I think in that sense you have to zoom out a little bit sometimes.
And when working on, sorry.
Oh, I was just going to echo, I think the last two comments I think are really important, because focusing on what users want, as opposed to say us as researchers, is critical. And very often users don't really want any sort of complex explanation of how the system got to what it did. They may want reassurance that it took one particular thing into account, that if Maps is steering you into a crowded piece of traffic, it knows there's a traffic jam there. And so there is a gap between what you can think of as interpretability from the machine learning conference side and what you would think of as explainability as a user of a consumer product.
Exactly. I actually had a follow-up question on the same thing, that regarding model explanations, there is this trade-off between readability to humans and faithfulness about what the model is actually doing. Where do you see, like, there is this gap? Is this the same gap that you're referring to, right? Is there, like, how do you see we can bridge this gap a little bit? Or perhaps are we making progress in the right directions? Are people from the machine learning community, and perhaps for Harman, who is working on HCI side of the thing, do you think these people are making progress toward addressing or bridging this gap, or there need to be more discussion?
I think we do need a little bit more cross-pollination between the communities. One of the most valuable things I got from my experience working with ML researchers was, there's a lot of underlying things about models that even I don't understand, even though I'm familiar with machine learning. So having them on the team, let me take care of the HCI side of things, and they could come and help me with what I needed from practitioners and ML researchers. But regarding what you were saying about being fair to the model or helping people, I think even if you are faithful to the model, again, if the person doesn't understand it, does that faithfulness actually help? So I think I personally believe that HCI has a lot to offer here, and that we need to work with end users and domain experts to design visuals that actually help them understand, what the model is doing. So maybe there's an extra layer we need, even with interpretability, which is just whatever explanation you're generating, and there's a lot of great research in that space. How do we make it human interpretable?
Yeah, I think one issue that comes up a lot is sort of trust, accountability, contestability that are not really interpretable. It's like people can use interpretability to achieve those goals, but it may not be the only way to achieve those goals. I remember talking to a doctor about a machine learning system and asking about sort of its opacity. And he had this very interesting take where it's like, all the time we do these chemical tests for, markers of disease. And some of these, we honestly have no idea how the biology works. We just know that this test is extremely reliable, and we have no problem with that at all. So it's not like the black box phenomenon is something that's unique to machine learning. It's something that we see in a lot of fields, and people sort of get used to it in various ways. At the same time, as I still do believe there's not some inherent trade-off that in many cases we actually can, we don't know how to do it yet maybe, but I believe there's a lot of room to create, to sort of go towards an efficient frontier where we get stuff that is easier to understand and more accurate.
Yeah, just to follow up on that, I think that's a really important point, right? And it really depends on again, comes back to what is the actual end usage scenario, like what is the actual end goal, right? Because oftentimes the goal is to have an interface for the human or for the expert to audit the learning algorithm. If that's the goal, then maybe it's less about how faithful the interpretation is to the model, but more about, can you come up with a set of probes or queries, right, for the human to query the model to look for biases and mistakes. And for example, Samir has done a lot of good work in this, and some of the work that we're interested in looking at biases in word embeddings and stuff of that flavor. Right? Maybe your goal is different. Maybe your goal is to say, can we actually have an AI system that work well with human as a team, so that the total output of that team is better than the individual components, right? So if that's the goal, then you want to think about a different kind of objectives for the interpretabilities, and that's where a lot of the work in HCI has been really exciting.
And there is this also follow-up question that I had, that given that we are pushing into how can we bridge this divide between people generated data and the ones using it for modeling, usually is a disjoint set of people. Like, is there any ideal version of that collaboration or that you can imagine?
I hate to say it, but I missed some of that question. Do you mind just quickly recapping?
Oh, sorry. Definitely. So so this is a follow-up to James' comment that given that we are pushing for a data-centric view, how do you think we can bridge this divide between people generating the data and the ones using it for modeling, which are usually a disjoint set of people? We also have this gap there. And what do you think would be an ideal version of collaboration?
Yeah, so that's a very good question. I'll take one step at this, but I'd also love to hear what other people on the panel thinks. Right? I think right now, a lot of the gap happens because people would generate the data in the beginning, usually early on in the project, right? And then the ML people would take that data and then they just too often do their own things, right? So maybe the data generators will come back at the end when the paper is almost ready to be submitted to provide some feedback or interpretations. But it's really sort of this handoff. Once the data is handed off to the ML developers, then it's sort of have as like a separate life, right? And I think that's okay for some of the more basic research R&D in machine learning, right? But if we really want to build systems that are getting closer to deployment in a setting that's more accountable or fair, then you really want to have more continuous interactions between the people who are producing the data with the people who are developing the algorithms. And that's actually one of the motivations for tools like Radio, for people to provide real-time feedback, especially about the mistakes the model's making throughout the development process.
Yeah, I personally totally agree. Yeah, okay, sorry, cool. Yeah, so from my perspective, I totally agree with James. So just take the ImageNet as an example. So firstly, like it comes out like 2012, it finally finalizes the data set of ImageNet, and a lot of models like conducts research on ImageNet. And like recent few years, people will found that they have some intrinsic bias in the ImageNet. For example, the imbalance issue or some fairness issue or some like label noise or data corruption issues in the ImageNet. And following people like will iterative to update or add more samples to the ImageNet makes the data set be more better or be more suitable for research to conduct research. So basically, I think I agree that it will be a cycle that need a lot of communications between the data generation or collection team and the machine learning researchers to like help each other to find some limitations on the data set and to improve the quality of the data set, and which is also beneficial for following researchers. Thanks.
Thank you. So Martin in particular, oh, sorry. I have a little bit of delay. Sorry if I'm interrupting.
Okay. I was going to say, this is another case where I think visualization can actually be incredibly helpful. There are people in my group at Google have released a bunch of tools. The most recent one is called Know Your Data. And it's designed to let you really inspect the data set at scale, which can be hard otherwise. And I think one of the things that people do surprisingly seldom is just look through, say, if it's an image database, many, many images, or if it's text, just read a whole lot of sentences. And all of this is actually incredibly useful. Like even just forget fancy visualization, but just being able to look at the raw data is an incredibly good way for people at every stage to kind of spot problems, to see issues, and so forth.
So this was my follow-up question that you answered. Thank you.
Psychic panel.
So another follow-up question to David. David, do you think more participatory approaches to learning fair models? Can we have such approaches for deep learning? What is your opinion? Like, shall we be more careful about data? Shall we design models? What is your opinion?
Yeah, I mean, I think that type of question in terms of being participatory, I think connects a lot to the last, to the thing we were just talking about as well. So, I mean, the hallmark of participatory approaches, as I sort of understand them, and I'm certainly not an expert, is that you're involving affected communities and you're involving people who are kind of on the receiving end of algorithmic outputs. And I think one of the ways in which those groups can be very involved is in data collection, and it is in understanding like what the composition of a data set should look like, and how they can sort of stay involved throughout sort of the iteration of a project. So I mean, I think that's really important, and I think that connects well to some of these questions about biases that emerge in data sets. I think also it's worth noting that when we like sort of when we ask like how participatory approaches can improve deep learning specifically, one thing to sort of consider is that like the choice of like model type is also something that like could be informed through that type of participatory consultation. Depending on the application, it may be better or worse to be using something that's computationally heavier or lighter or more or less complex or however. So Yeah, it's
I'm
definitely.
talking about biases.
Sorry.
Sorry, again, this is my delay, sorry. So talking about biases, so we know that these biases can be introduced in different steps of a machine learning pipeline, from data collection, annotation, model selections, and so shall we, like, perhaps a lot of times we are looking at this as only an engineering problem, but do you think we should bring this or be careful about this issue while designing algorithms perhaps, or designing our models even?
Again, can you clarify a little bit what you mean in terms of the being an engineering problem versus designing a model problem? So I mean,
shall
I
we
guess
only looking at this like data cleaning, or shall we like design algorithmic ways to kind of for smarter data collection perhaps, or can we address this perhaps with designing better models, or somehow use visualization or different tools, or shall we only looking at this as a pre-processing step?
I see. Yeah, I mean, I think that thinking about how to sort of kind of systematically characterize the way in which your data is maybe insufficient is, I think, potentially a really interesting way forward, and potentially connects to some of these like loops that a couple others on the panel were addressing in terms of you know, how a collaboration between a data collection team and an algorithmic development team might work. Is that if you have ways sort of at scale, and maybe visualization is part of this, to uncover issues with your data and to figure out specifically maybe what's wrong or what's missing, then that could be really fruitful in terms of being able to go and get more of that. So I totally think there's really interesting algorithmic design questions there.
Yeah, I would echo that absolutely. And even I would say that there's sort of a disappointing thing that one might say, which is that sometimes machine learning may not even be the answer. And that as we think about sort of the, you know, systemic view of what's going on, you know, perfectly legit answers that can come up are, maybe we shouldn't build this thing at all, or maybe we shouldn't collect that particular kind of data. And that's not always the case, but that should always be on the table in thinking about these things. That really there are lots of different ways to approach you know, things, and we don't always have to do the, you know, the technologically fancy thing necessarily.
Right, and just to add one other point on this is that I mean, oftentimes the biggest source of bias happens not in the data or the model, but in what objective you choose to optimize for. Right. So for example, in healthcare, oftentimes people build predictive models to optimize for cost. Right. So you can have the best curated data and the best developed model, but if you're optimized for cost, then there's already an intrinsic bias built in there, because cost ends up depends on healthcare utilization, which also differs between different demographic groups. Right. So I think oftentimes just thinking about what is the actual metric that you're trying to optimize for, it's oftentimes the biggest single decision that affects the entire process.
And for you that you're working on interpretability, fairness, transparency, so do you think theory or recent development and results and progress in theory, is there any way we can use such theoretical results in actually providing some fairness guarantees or more interpretable results, or can they help us? We have these results for finding better structures, network pruning, neural architecture search. We have these theoretical results on optimization, what's the effect of data, what's the effect of models. Is there any way we can use some of these results, although they are not yet perfect, in making safer, more reliable, transparent deep learning? This is a very difficult question, I know.
Just quickly, I think reliability and those types of things are all very, very connected to the types of guarantees you can get. And, you know, for instance, if there's some way to sort of think a little bit more systematically, for instance, about different subgroups in the data and how they relate to each other, for instance, from a fairness perspective. I think that's very interesting, and I think anytime you can get any sort of guarantee, that's only gonna help understanding a model's reliability more. So I think all this stuff and all this scaling stuff also is very useful in that sense.
Yeah, I also want to add something for this point. So in order to deal with in maybe not a perfectly reliable data set to build up machine learning systems, I would say from the optimizer roles perspective, or the optimization objective perspective may also be very helpful. So basically, perpetrator regularizations can improve the training reliability, and also maybe we can develop some good optimization rules to avoid the bias caused from the data set. And such kind of optimization rules can be derived from some analytical theoretical foundations, or can also be parameterized by a network, use a network to parameterize the optimization rule and to learn optimization rule to avoid the bias or some unreliability issues in the data point. Okay, thanks.
So I have, because we are one general question, if we want to move toward more scalable deep learning and more reliable deep learning, we have we had these talks on theory. Yasaman talked about it, Tianlong talked about models, and different people like Martin talked about visualization, and James covered trustworthy AI and data. Maybe talked about fairness, and Herman covered the human side of it. Where do you think we can, is more important? Because a lot of times we push further to gain 1% more accuracy with huge costs. So where do you think, shall we be more careful again with data collection, bridging this gap between humans, how they collect the data? Shall we try to explain what is the effect of this data that we collect? Or shall we try to kind of handle it algorithmically during the optimization or with designing better models? Or there is this philosophical question. Of course, all of these are important, but just to reduce the cost, just to keep it more manageable, what do you think is the most important step to start with?
I think it's a hard question to answer because it is so contextually dependent. And so, if the 1% difference getting from 99% accuracy to 100% accuracy, you can think of all sorts of situations where that's amazingly important. In other cases, it might not be. So I guess what I would say is this is another place to take.
Something to perhaps give a context. Yeah, sorry to interrupt you. To give a context, I'm mainly thinking about these huge models that we develop in Facebook or OpenAI with billions of hundreds of billions of parameters. And most of the time, I think they are used for some safety critical problem to address those a lot of times they are and image recognition. So this is kind of what I'm thinking about. That is where I see we are spending most of the resources that we have. Is that helping? Or I don't know, or perhaps I should start from the theory. What do you think?
I only caught a little bit of the question, but maybe, so I wasn't quite sure if you're I understood your question to be, do I think that like data cleaning or algorithmic improvements or all these other things are like, which of these is the most important factor as opposed
So
to?
what would you, like, how would you reduce this huge costs? Because training these huge models like introduce a lot of financial and environmental costs. So where do you think is the most important angle to address this? Like, and data cleaning can be also thought of as data collection, right? So shall we be more careful with collecting our data, or shall we try to make this design better networks to provide scalability, fairness, transparency, explainability?
That's a tough question, but I think so, and I don't have any predictions for the future, but maybe it would be worthwhile, at least I'm not, maybe others on the panel or know of works that do this, but maybe if it's possible to even just kind of after the fact now do an empirical study on which of these factors so far has been most important. So if they're, some of these scaling laws, they get at, well, they study the most kind of the simplest things that you can do. So scaling up the model size, but a study that looked at exactly the question that you're asking, like if we did do more data cleaning, how does that affect, or are we kind of navigating away from just improvements on scale? If we look at improvements in architecture, for instance, I think some of those empirical results suggest that the architectural, despite the fact that we're using very different models, like we've gone from RNNs to CNNs or up to transformers, it hasn't changed the scaling properties that much, or it kind of depends on the problem. So I think maybe the first place, rather than try to predict rather than predict the future, kind of just see if we can accurately predict already what's happened in the past few years by doing some more kind of thorough empirical studies, but like tuning these other knobs of the problem that you mentioned, like cleanliness of data. And is that breaking away from these predictable kind of trends? Are we, we want to move away from the things that are predictable and kind of mod out that aspect of the problem and kind of get benefits that are like harder to predict or more emergent. So I think those knobs as a study of scaling as a function of some of those knobs, like data cleanliness, for instance.
Yes, and also like connecting to the pruning, I think we can perhaps such a scaling laws can be also studied for the pruned network, right?
I'll just add one bit of personal experience because we've been doing some work with large models like GPT-3. In our experience there, maybe we get to like the biggest bang for the buck by just putting resources into coming up with good test data, right? First, because there's a lot of training that I've been doing to such models, so really to clean those, I think would be really interesting, but it requires a lot of work. To improve on the model architecture itself also requires a huge amount of resources to retrain this whole thing, right? Whereas the test data, we could actually generate quite high quality test data, and that's used specifically to probe the model to see what are the potential vulnerabilities and biases, right? Well, basically it's a way to actively test and actively monitor the model. So that's something that we could do on the scale of weeks, whereas I think the other projects like improving the architectures and so on would take a lot more resources and maybe take longer time to do.
That's a great point.
Yeah, and there's still a lot of things you can do on the test set, especially thinking of like prompt design for these feature learning models like GPT-3 that can, even if you're not fundamentally addressing the biases, right, you can still reduce them in deployment in practice.
That's a great point. Okay, thank you all, everybody. I think we are very much over time. So I want to thank you again, all the speakers and panelists for being with us today. I think the talks covered like all those great questions, and we identified, we discussed a lot of gaps at least to bridge, hopefully in near future in the panel. Thanks again, everybody. So I want to also thank the audience and for all of you to joining us today. And I want to quickly mention that the recordings will be available on the website shortly. And please let us know if you have any feedback. And a special thanks to all of you who were with us today. Thank you so much.